How's on? I say to all the around the world, good morning, good afternoon, but who got people from International Space Day, and again, can't and share the chair and accomplish great opportunity. So state Alabama, all the home moon. We made the here in Huntsville is space vision. I want to hear space. For you today. Further to introduce the Huntsville battle who had a
all of you, welcome to Huntsville. Sitting here, every large reason and out of our more engineer great what and days not be not our thing but very side fits with fun work being to do time activity when you part of our thesis part of our for being here for being here time. Thank you much.
Thank you, man. Sack up your we have as from and Marie. They're gonna talk about what the challenge is. Is everybody ready for the challenge? Around the world, this morning, or more energy out of the room. Ready? See it?
Thank everybody coming out today. We excited to be once again the main stage for the NASA Space Apps Challenge and represent Huntsville. No better place than the Rocket City. I am not going to take up a ton of your time, but I do want to make sure that I thank a few really key players and sponsors. Obviously, we are so excited to have Work Bay here. So they're going to be the ones that are going to be poking around and live streaming. You might, get a camera in your face later. And they have actually traveled all the way from Canada to be here and sponsor this event. event by producing our live stream. This beautiful building that you're in is the I2C. It's one of H's newest buildings on campus. It's beautiful. They were kind enough to sponsor our event with this amazing location, and so we'll be here throughout the weekend. So we definitely want to thank RigVed and the entire I2C team for letting us crash their party for a couple of days. Along with that, they have some key sponsors, which are Maynard Cooper and Gale and Warren Averett, and they are amazing and have been really supportive throughout this entire event. And then I want to more. How many you guys are going to be actual hackathon art? That's awesome. So that money sponsor, so that $10,000, right? You can clap for $10,000. Okay. exciting, right? We want to thank Steam for sponsor our prize money and just being here and being a part of it. Amazing. They're a wonderful nonprofit. Thank to it research technology afternoon 7 and a long sponsor all and space apps since it's been and thankful for their continued support and for them to be a champion of what we're doing here. We also want to thank Heed Martin as well. You'll hear from them in just a second. Same thing, they have been just an amazing support for not only space apps but also Urban Engine as well. I want to make sure thank you space to the US tech for $3,000 underneath a Saturn V rocket. Nobody yet? Okay. Well, that'll change, hopefully, right, by the end of the weekend. So the U.S. Space and Rocket Center was amazing, and they have donated our space for our finale event. So we're really excited about being there, and you guys have opportunity to win the underneath the Saturn V, which is just such a opportunity. I also want to make sure to thank Flourish for PR. We want to thank sponsor. We also have all our sponsors that you'll see signs for and who really just made this possible. And most of all, Huntsville, right? Like that has been a trip, an amazing journey to space apps to Huntsville, and we're really excited about having not only to be a part of the hack it that we've spent the last 3 or 4 months put together showcases what we're all about. So I'm going to pass things over to Marie from the Global Organizing team because she's got a few things to talk to you about too. And I hope that you guys have a wonderful day today.
Thanks, Sierra. What a kickoff. Welcome, everyone, to NASA's International Space Apps Challenge 2019 in Huntsville, Alabama. My name is Marie Mimiaga, and I'm honored to be here today representing NASA's Global Organizing team. You're going to hear us referred to this weekend as the GO team. Can I hear a GO team from everyone? Go team. Awesome. That's the energy I want to hear. So I first want to kick things off by thanking and acknowledging the incredible leaders of this event. Let's please give a round of applause to Sierra and the entire Urban Engine team that made this experience possible for you. And I want to let you guys in on a little secret. This is a very special moment for me because this is actually my very first Space Apps Challenge. Who else is attending Space Apps for the time? All right, the majority of us. Okay, we'll stick together this weekend. So I want you guys to think about a moment. It may be this moment, it may be a moment last week, last month, last year, where you did something for the very first time. I want you to ask yourself, how did you feel before you did that thing? And what were your fears? What were you most excited about? Now, how about what you experienced while you were doing that first thing of yours? Who did you meet along the way? Who did you ask for help? And lastly, when you were done accomplishing that first, how did you feel? Is there anything you wished you would have done differently? Anything you wished you would have asked? Anything that was blocking you from being your best self? I want to encourage each and every one of you to go and sweet experience. Open your mind and make them every again and talk to somebody you don't know and put yourself out there. And while it may space and many for all of you, this is not the first Space Apps Challenge. Since its instant International Space Apps Challenge has become the world's largest global hackathon, engaging thousands of global citizens to use NASA's open data to build innovative solutions to challenges we face on Earth and in space. NASA's opened 18,000 people from 75 countries in 200 cities around the world participated in last year's International Space Apps Challenge. And this year, drum roll, we have over 200 events in more than 80 countries and counting. So the challenges change each year. Some of the most popular challenges last year included space apps, spacecraft inspection, monitoring disasters, and among many others, exploring the beauty of the universe. And this year we have challenges on subjects ranging from cleaning up orbital space junk, to visualizing sea level rise, to designing marketing materials for the futuristic space travel. And Space Apps inspires local communities to come together. That's why we're all here today. We're here to think intensely and create solutions to important problems. And each year, Space Apps engages thousands of individuals in cities around the world to work with NASA's open source data in a 48-hour sprint. I'm ready to go. Teams of technologists, scientists, designers, entrepreneurs, and others are going to collaborate to answer some of the most pressing challenges on Earth and in space this weekend. Participants are going to hack solutions to challenges that NASA proposes, creating games, smartphone and computer apps, videos, teaching tools, and much, much more. Space Apps inspires collaboration, creativity, critical thinking, and fosters interest in Earth and space science and exploration, and encourages the growth and diversity of the next generation of scientists, technologists, designers, and engineers. And that's all of you. I'm so excited to be here this weekend, spending this weekend with all of you. One of my favorite parts about Space Apps is that all are welcome. The common thread among Space Apps participants is that you're interested in space science and exploration, you are creative, and you want to solve problems. And most importantly, you want to do that together. And it's so incredible every year to hear how Space Apps is a platform for building connections. As a part of Space Apps, you are a part of a global hackathon community that embraces collaboration across borders, sectors, and cultures to bring about paradigm-shifting innovation. So a couple weeks ago, I was listening to a TED Talk from Kara Anderson. She is an Emmy-winning former NBC and Wall Street Journal columnist for Forbes and Huntington Post. TED Talk was all about creating opportunities. It was called Be an Opportunity Maker. I'm going to repeat that. Be an opportunity maker. That is what all of you are. You are here this weekend doing something smarter together for the greater good. And Space Apps is your opportunity to do that. I want you all to reimagine a world where we use our talents together more often to accomplish greater things together than we could on our own. So ask yourself today, what kind of opportunity maker do you want to become this weekend? Thank you all for welcoming me into your community and for seizing this opportunity. I'm so excited to share my very first Space Apps with all of you, and I can't wait to see what we are able to create together. Thank you.
Thank you so much. And now, Mr. Jim Rogers from Lockheed Martin with his remarks.
Thank you.
Good morning, Jim.
Good morning. Well, good morning. I appreciate the opportunity. I'm with Lockheed Martin. And the big question is, why do we support such an event? 48 hours crammed into what you all are going to believe. Well, sleep is optional, all right? So the whole idea is that you're creating and problem solving and you're critical thinking, whether you want to become an engineer in the future or you want to become a journalist or you want to become a financial genius. It takes everyone on these programs to make this work. You are here because you care around the world to try for this challenge. I mean, the money doesn't hurt, don't get me wrong, but it's really because you care and you're up to the challenge. And that's the people that big business, small business, it doesn't matter where you go, that's what they're looking for. Self-initiative, problem solving, critical thinking. That's why we support you. We support the challenges that you have because the challenges in the future for our world are going to be even harder than you thought possible. So thank you all for going after this, attacking the challenge, and good luck. Thank you.
Thank you, Jim. Next, it is a real honor to introduce Dr. Lisa Watson Morgan. Because I think back, and I think why Sierra asked me to MC today, because I may be the only person old enough who remembered on July the 20th, 1969, when Neil Armstrong and Buzz Aldrin descended the ladder of the lunar lander onto the surface of the moon. And here we are 50 years later, and we have Dr. Lisa Morgan, who is now going to be in charge of the next human landing opportunity that we're going to have on the moon and beyond. So I think we're at a special place at a special time to be in HSV today, to have such great talent. NASA's in her veins. She grew up here. Her father was a graphic illustrator for NASA. I can't imagine what her artwork must look like on the walls of her office in her home. So without further ado, Dr. Lisa Watson Morgan.
Thank you very much. Good morning. How's everybody doing today? Yeah, I'm going to need a little bit more. That's good. I'm happy to at least get some of that. So I am really excited to be here today because, you know, I was once very much like you, and I was very younger, you know, when I look in the crowd and see these young faces. And so I hope that you can look up here and say, you know, one day I want to be leading the program that sends us to Mars. Because really, you know, everything we're doing for the moon is just the next step in technology, in preparation, in software, avionics. Everything that we're doing for the moon is a precursor for putting human beings on Mars. And that really is, from an international standpoint, just a major goal that I want to see in my lifetime. I won't be the program manager for that, but maybe one of you will be. Maybe somebody in this room or somebody who is watching today. So thanks for having me here today. As an engineer with over 30 years experience in aerospace here at NASA and at Marshall Space Flight Center, I've seen this agency accomplish amazing things. We've taken on challenges, we have been innovative, we are great at solving problems. And that's one thing I really like about the Space Apps Challenge. It's all about problem solving. And that's why people become engineers. But I also don't want to lose sight of the arts. I love STEM, science, technology, engineering, and math. I also love STEAM. You put the A in there with the liberal arts, and then you really have a powerful, diverse team. And that's what it's going to take. It's going to take everybody for these just magnanimous types of challenges of putting humans back to the moon and past the moon onto other bodies that we want to land. So, as you know, as you heard, I was recently named the Human Landing System Program Manager for NASA, and that's great. I'm working across with all of the NASA centers to try to get the best skills, try to get the right ideas, try to get us going forward. HLS, though, is a partnership. We call it HLS because, you know, at NASA, we all have acronyms. That's just the way we talk. But so the Human Landing System, it's a partnership between commercial industry and government. And the whole purpose of that is to try to use the best practices of industry, because industry has the ability to move fast, to be very efficient, and maybe to not have as much red tape, let's say, as the government does. And so the government now brings in the human spaceflight experience that we've had for, you know, since basically our inception of getting humans safely to the moon. So we have our safety culture and we have the human spaceflight experience. And so when you bring those two diverse types of thoughts and design and construction standards together, that's what we think is going to promulgate us successfully to the moon. So we initially, just so everybody knows, and you know, everybody loves a good challenge, we were planning on going back to the moon in 2028. That's, you know, that was the initial NASA mission where we thought we were headed. And in March of this year, here in Huntsville at the Davidson Center at the USS Space and Rocket Center, the Vice President came and said, you know, had a great bold challenge. He said, and I want to see America take us to the moon, landing the first woman. That's also a big change, and the next man on the south pole of the lunar surface. And we were all going, yeah, right, we got this. And then he said, and I want you to do it in 2024. And we said, hold the truck, you know, because that isn't what we had planned, you know, not at all. But, you know, becoming, I would say one great thing I think about education, NASA, industry, is that the challenges seem to be bigger, but I think I think humans collectively are better prepared for those challenges. I really do. I look at what my middle schoolers and high schoolers are learning right now versus what I learned, and I see that they are better equipped. And that gives me a lot of hope, because when I look at your faces, I know that you're better equipped than I was, which tells me you will go further than I will. And that gives me great hope for the future. Another thing that gives me hope is I see diversity in this room. We all don't look alike. We all don't talk alike. And you know what that's going to do? That's going to bring the best ideas forward. In a room and we have the same opinions and we all think a certain way, that is not the way to success. We got to get somebody in there that says, well, wait a minute. Did you think if you do this, this could happen? And someone go, oh, no, I didn't think about that. You know, why would you, you know, where did that come from? Well, I had an experience, or I had this. And so that whole diverse thought, I think, is another thing that these Space Apps challenges and hackathons in general bring about. So definitely embrace the diversity of teams. It may take you a little longer to gel as a team, but once you do, I'm telling you, you will be so very successful. So for HLS, for the Human Landing System, we have a lot of challenges that we're trying to overcome right now. You know, in looking forward, we have to survive the South Pole. We have to survive the night. That is going to be a big challenge for us. As everybody knows, there's extensive dust on the lunar surface, the regolith, and it's electrostatically charged. So what that means is, you know, all over, kind of ubiquitous everywhere. Everywhere the astronaut steps, dust then just cling wraps to his and her boots and feet and hands. So as you are trying to pick up something, lay a sensor down, set up an experiment, you're doing it with this debris all over your hands. So that's a big challenge to overcome for human spaceflight. And it was mentioned earlier, of course, that I am from Huntsville, you know, yay. So we hope you guys come back next year, you know, love Huntsville. Definitely an innovative town and center for sure. I was able to, when I was young, to go to Take Your Child to Work Day at Marshall because my father was a contractor that worked out there as a graphics illustrator and artist. So yay, the arts. And I was able to see drawings of rockets and spacecrafts, and it really did inspire me. And then later on, I decided, through his, counsel and all, to go into engineering. I'm very glad that I did. I was also able to be a cooperative education student or an intern, a paid intern at NASA. I highly recommend that for anybody. Love to have y'all at NASA, but also, Lockheed. There are tons of other companies. This is a big, big city for aerospace. Technology in general. We have the Toyota plant coming. We have lots of industry, lots of wonderful jobs. Interning and working part-time while you're going through school, an excellent way to do a test bed of whether you fit in their culture, whether you're going to, succeed there. Highly recommend that. Okay, I want to switch gears just briefly and talk about Apollo. Apollo, everybody knows, we just had the 50th anniversary of, the human landing on the moon. And, Apollo really changed the world. I mean, it really did. Over the summer, watching all the specials on TV, it really just brought up, that deep, visceral type of feeling of pride of just being a human being. Of wow, look what we can do. Look what we did. And so, it established, it had over 300,000 people to help get Apollo to the moon. And those are highly skilled technical workers. So that is a game changer for any nation, and especially now when we go international, for the International Space Station, NASA has tons of outreach. We have tons of partners. We don't do this alone, as everybody knows. So earlier I mentioned, we've been talking about human landing system. It's being coined Artemis. Maybe y'all have heard of Artemis. It's a series of all that we're doing for exploration to get us to the moon. So what is important to me is inspiring the Artemis generation. And you are the Artemis generation. And I am the Artemis generation. And imagine the skilled workers that we will have after we successfully land the first woman and the next man on the south pole of the lunar surface. Later on, there will be, series of successful podcasts, live stream. So, you just look at what we have now from a media standpoint. It's just a media, type Thanksgiving for people. And it's a great opportunity, and it's a great opportunity to work together to overcome the challenges that we need. Now, I will say, I think everybody knows NASA works for the administration, for the president, and our budget is decided by Congress. So having said that, I don't know what's in store for us from a funding standpoint. My hope and my goal is that they see the benefits the way we do for education, for what Artemis, for what the human landing system can bring to the nation and internationally. And I hope that they fund that, because I guarantee you, when the astronauts landed on the moon, they never considered what was to come. They knew it would be great, but all the technological offshoots, all the technology, all the people coming together, the unity, the oneness. I don't believe that they had that in mind. And it's hard to put a dollar figure on that, for sure. So, to me, in closing, I want to tell you what the moon represents. So to me, the moon represents equality and unity. And it's because the moon does not discriminate. Its beauty is up there every night for every human being, no matter where you are on this earth. You can look up to it and realize no matter what you're feeling at that moment, I guarantee you there is another human being feeling the same thing. And I think that's really powerful. So you're never alone, ever. I also want to say that the moon gives us that creative desire. I think it's that inspiring spark for innovation. And we need all minds. We need everybody teaming together for challenges like this, for helping me with the whole dust thing that we got going on the moon, all the different challenges that we're going to have. So with that, I just want to close and say thank you guys for being part of this. I look forward to hearing what comes out of this, and even more so, I hope to see your faces in the future in aerospace and other technological fields, whether you're helping with media, whether you're helping with the arts, with marketing, whether you're helping with thermal designs, avionics, regardless of what it is, everybody's ideas are needed and welcome. And with that, thank you very much, and I hope you have a great day.
Thank you
Right
so
back to you.
much.
Thank you.
How incredible is she? Thank you all so much. I mean, and wow, what she is going to do. We're going to take a little bit of a break now for a set change, I believe. So everybody just kind of chill, enjoy your space happy morning, and let's say hello to the rest of the world. Hello! Come on! Yay! So, little break, chill, we'll be back.
Negative, Christina. But we're going to wait until you are out of the way, and then we'll start motion.
Oh, okay. Sorry. I thought we were waiting. I thought it was the other way around. So I will go ahead and start translation outward. Hi, Jessica. I am to the ORU, so I would be ready for you to start, for both of us to just kind of start slowly making our way. Okay. It looks like it's in a great config. Okay, copy that. I'm going to just move slowly, and if you are close enough to get to that back end, I've got a little plane change coming around the corner there. Okay, copy. And if at any time we want to stop, put down the local or any orientation or anything, that's fair game. Okay, copy that. I think you've probably got a better view of the box than I do, so I'll have you call it. Okay.
Cook and Mir now both on their way from that P4 site where Cook got off the robotic arm to the P6 site where the old battery charge discharge unit is waiting to be replaced. While they make their way, we have a few more Ask NASA questions. This one from a 7th grade class in London asking how long the astronauts have been on the spacewalk at this point, and they had just made it to 2 hours and 43 minutes so far. The entire spacewalk's planned to last about 5.5 hours, though that is a little bit fluid based on how much they get done.
Steamer Jessica, this is Drew and Luca. It was a pleasure working with you guys. We are ready to start the motion, and after that we will go quiescent.
Copy that, Luca. It was awesome working with you on the arm. Thanks, Luca. Thanks, Drew.
See you guys in a couple hours.
Sounds good.
Luca Parmitano wrapping up his activity for the day. He's been driving the robotic arm with Christina Cook on the end of it, but now that they are safely on the port section of the space station's truss, they are going to be making their way by hand to their main work site for the day, and his job is done.
Copy. Mine's in work.
Copy, Jessica.
For our next Ask NASA question, we have a note from 6th graders in Knoxville wanting to know how long Christina and Jessica have been at the International Space Station.
5306.
Christina Cook is actually on her 217th day today, and it is the 23rd day in space for Jessica Meir.
You are correct. Thank you.
Meir just launched in September.
I'm just going to reorient this PCU around the white target. Okay.
And she'll be staying until the spring. Cook has had her mission extended.
This next group, these next two folks are going to be fun. Now, you're going to have to hold your Snickers a little bit and not laugh out loud a little bit, but you're going to enjoy it. First of all, Dr. Jill Williamson. She's a PhD in chemistry, but she's kind of known for taking and turning pee-pee into coffee. You're going to hear about that. And then Destin Sandlin. He has a great web presence. Over 7 million people tuned into his website. And they're going to talk about what's it like to live in space. And how do we get rid of things and do things. And what's the environment like. And they're going to challenge you again. So without further ado, we got Destin with the Destiny. We got Jill with the PPP. Come on up.
Thank you very much.
Thank you.
Hello. How's it going? Everybody doing okay? My name's Destin Sandlin. I have a YouTube channel called Smarter Every Day, and this is Dr. Jill Williamson.
Yes, good morning. Thank you. I'm just going to drink my coffee here.
Yeah, I'm drinking coffee as well. Do you know what we're here to talk about? Gosh, you're in for a treat. Not to talk about. So if you had to guess what Dr. Jill Williamson does, what would you think I don't know, just guess. What do you think? She has a PhD in chemistry. That's what? Eclipse. Okay, whoever said that's not allowed to talk anymore. All right, so yes, the answer is Eclipse. What do you think you need to do when you go to space? Like, what are the things you have to consider and have to think about? What do you think? Like, you're going to go to space. What do you get a suitcase over here, right? You want to do it that way? You want to talk about the suitcase?
So you're packing for space. What do you need for your trip? Some clothes. Clothes. That's
clothes,
important.
Yeah.
Yep. Food, snacks, all right? Coffee, that's probably the most important one. Yeah. Water, yes.
Water, that's good. Hey, tell me more about water. Why is water important in space? You can hydrate, that's right. What about over here? You guys aren't talking. You're kind of just chilling out, letting all these ladies over here do the work. What's up? Think about water. What's the deal with water in space? Take a bath. Take a bath? I don't know. Do they take a bath in space? No. They do?
No, they actually don't.
So here's a funny story. My grandfather actually worked on the first shower on Skylab. Did you know this?
I did not.
So my
Go
grandfather
on.
used to work at Marshall Space Flight Center, and he helped make the first shower for space. And I read the reports from where they work. You know, the astronauts were talking about the shower, and they're like, "Yeah, you know, it was great being in space, but that shower was awful. Didn't work very well." So that's our legacy. You know, the San Juans made bad showers in space. Okay, so I would like to know more about what's on the table over here. Do you want to just let the cat out of the bag and explain what you do?
Sure, yeah. Okay, so I work with pee. I work with pee on a daily basis, so it's like I go to work and this is my life now. And so
To be clear, when she says pee, she's talking about pee.
yeah, not
Like
the fake
urine.
stuff. Like you don't buy it on Amazon. This is like the real stuff.
Can we talk about what's in the box over here? So let's do this. Let's talk about we are packing for space, right? Are these your things?
Yeah, yeah.
These are your things? Can you explain what they are to me? Because I don't know.
Yeah.
What does this represent?
You're just kind of messing
This is a
around with stuff
recycling.
here.
What do we have here?
Yeah, so really I'm going to try and be safe and come up to the front. But essentially, if I'm packing for space, I want to take everything I need to like stay alive, right? But I want to be comfortable. I want to like do just leisurely stuff. But I want to pack everything: clothes, food, snacks, all of my water, and all of my air to sustain, you know, life, to be happy and comfortable. So if I had to take all of my air, look how much space it is to take up in my suitcase. But as soon as, of course, all of my packing is coming out of the suitcase, but as soon as I can take some of my air and I can recycle it, then I don't take as much space anymore. So now I have room for all of this other stuff, my health and my space suits and
Oh wait,
and
let's
time for
pack. Let's
showers.
pack. So
Yeah.
what we got? What is
Yeah.
this? So here we're gonna pack. So I've got clothes. So can we put these in our suitcase
Yeah.
here? Okay, so Jill, you're gonna pack for us. What
gonna
else?
pack.
Let's just take everything out of our suitcase. Let's just
Yeah.
do this right. All right, so we got all the stuff. Let's literally pack for space. Okay, so I like to not be naked. So I'm gonna put clothes in there. Is that cool?
Yeah, that's a good.
Okay,
choice.
and so like I'm noticing these boxes are different sizes.
Right.
What's the deal with
So
that?
if I wanted to take all of my air,
Because you got to breathe, right?
yeah, but now I don't have room for it. This is all I needed to do my mission. But hey,
So how do you do that?
so now I can take some of my air and I can recycle it. Now I have so much more room.
Okay, wait. Okay, let's think out loud here. So we're breathing air in the room, right? What's in the room? When we say air in the room, what? Oxygen. What else? Carbon dioxide. What else? Nitrogen. That's most of it, right? So what you're saying is, if we were to take all the air,
Yeah, take all of my air.
then all of our rocket fuel would be spent getting the air up to space, right? Right? Okay, so we don't want to do that. We want to take just enough air. So this is just enough air, right?
Yep.
And this is enough air to do what?
To recycle it.
To recycle it. So we breathe our air. When you breathe in, what do you breathe out? So in goes the what? Out goes the? Okay, got it. So we're going to take oxygen and we're going to convert it. Once it goes to carbon dioxide, we're going to come up with something fancy to get it back into oxygen.
Yeah.
So we breathe in oxygen, breathe out carbon dioxide. Our spaceship is going to turn it back into oxygen, right? Okay, what else do we have? So
And
we're
then,
going to...
and then if I wanted to take all of my water, again, same story. All the water I wanted to bring, now I can't take anything else, nor can I actually take all that I needed.
Well, how do we do that? Do we use this again?
Yes, I actually have one dedicated just for the water, so now I can just take some of my water and I can recycle it.
Okay, so but that's kind of gross, right? So let's think about this. So this is, for example, my coffee over here, right? So Jill, if I take my coffee and I drink it, this is today's coffee. I drink it. Where is it now? Where is it? Stomach, and then it goes to my bladder. And then what? Then you pee it out. Oh yeah, you got it. You just figured it out. All right, so the coffee goes into your system, and then you pee it out. And so, drink your pee. Is that, well,
Yeah,
let's ask
well-
her. So ask her your question.
So you're not actually literally drinking your pee. I mean, you actually do, you're doing this process here terrestrially, right? We have our sewer management systems, but we're taking that urine, that pee, and we're taking the water out. And so essentially, yes, you are drinking your pee.
So think about this. When you go to the restroom here and you pee in the toilet, where does the water go?
In the sewer.
Okay, and it just goes away magically?
No, like it goes to the ocean and then they clean it.
Do you really? So you're telling me there's a pipe that goes from this building to the ocean?
No, it's like the center. It's like the center.
What's that? Dr. Jill, you have a PhD in chemistry. What happens when I pee in the toilet?
So you have your local water treatment plants. So every town and municipality will have some way to take your sewer water, your toilet water, and they're able to clean it here in gravity and make that kind of sewage water into clean drinking water.
So what you're saying is we take our water here on Earth and we recycle it here on Earth.
Yeah,
Okay, but we have to be more efficient with it though, right?
absolutely.
So when we're going to space, we have to take just a little bit of water and then we recycle it. So you're about to tell me, I think this is the punchline, that you pee and then you filter it and then astronauts are drinking pee. Is that what you're telling me?
Yes.
Who wants to be an astronaut?
Yeah.
No, I just want to go to space.
You just want to go to space? All right.
I'm not drinking water. Wait, isn't it true that they filter their water too into like when they pee, when they drink the water, it filters into the pee? So if they say they filter in space, don't we filter it on Earth? So that basically means when we drink, every single time we drink water, we drink our pee.
Okay, so the question for the live stream is, doesn't that mean every time we drink water, we are kind of drinking what used to be our pee, right? Is that the question? Yes, I think that's right.
Oh yeah, absolutely.
So I have a question for you, since you have a PhD in chemistry. So when I drink water and it goes into my body, the coffee is black, and I drink black coffee or black Coke or orange juice, and then when I go pee in the toilet, it's clear and yellow. What's happening there? Where does the color of my drinking stuff go?
So your body's really good at cleaning your kidneys, right? You have this special organ in you that really cleans what you're eating and drinking, right? And so then what actually gets released out of the body is going to still be majority water, but you're still going to have those little bit of everything else that you couldn't clean via your kidneys. And so some of that color is going to come from urea.
Urea?
Yeah.
What is urea?
So a big component of urine is urea. And so when you have that smell of urine, right, that's that compound breaking down into ammonia. And so there's these chemical reactions that go on within the urine.
Okay, just let me ask some simple questions. Is it safe to drink just pee?
I hear Bear Grylls says that you can drink your urine like maybe 3 times. You can.
Really?
Then after that, then you don't want to.
But I mean, obviously, I don't want to at all. We have a question here. Yes, ma'am.
Do we drink our
Okay, no, that's a good question. And so she's basically asking if we recycle, and she asked it in a very respectful way. She said, if we're recycling our water or our pee, can you also recycle your food, which is wherever who's got the apple? Tell me the apple. Can we recycle our food, like the things that poop?
Yeah. So during these like future manned missions and our current manned missions, obviously we're going to have to not go number 1, but we also have to go number 2. And so there is a way to collect that side of our waste, but just fundamentally we don't really want to do too much to us, too much energy to try to reclaim the vital sources, be it water or some of that carbon content. So really what we do for these manned missions is we just collect the waste, but we just kind of package it up and throw it away. So there's really no processing, at least for our manned missions.
So let's talk about number 1 here. So we want to collect our urine and recycle it. So I'm seeing some containers here and it's not yellow. This is not yellow. That's green.
Yes.
My body doesn't make that.
No, otherwise you need to go see the doctor.
Okay, so it says alternate pre-treated urine.
Yes.
You have a glimmer in your eye about this. I'm gonna show everybody here. I almost spilled the urine on you. Oh, you want to? Okay, so
Yeah.
Can you please explain what this is as I walk around?
Right, so I mentioned urine, right? Our pee has that kind of yellow color and it has that smell to it, that urea breaks down to ammonia. Well, on space station, our way of processing the urine, getting us that drinking water, is a relatively longer process. It takes a little bit, and so we have to stabilize the urine. We don't want that urea breaking down to ammonia, so like that gaseous, smelly bit. And so we stabilize it. So this color you're seeing is the chemical that we use to stabilize the urine. And so it's a strong oxidizing agent, something that really, really stabilizes the urine. And also we have to throw in a real strong acid in there to really drop the pH content. So you're seeing this kind of green color, so that's not what urine looks like in microgravity. That's just how we stabilize it until we can then process it.
My hands feel dirty now. Yeah.
Yeah.
I feel like I shouldn't touch myself on my face or anything like that. So you pee in what in space?
So we have kind of an equivalent to a urinal on space station, and so with the assist of a vacuum, because water or liquid fluid's just going to go wherever it wants to go. And so when you got to go number one, we have to have an assist. We have to have that vacuum to help put it in a direction that we want it to go. And so then we have a tank that will collect our urine. And meanwhile, it's being stabilized. This kind of green chemical is added in with the urine, so it's stabilized. So we have a tank that we then fill up. And then after that, we'll start processing the urine and creating this kind of clean water for you.
So I'm seeing some other stuff on the table here. What is this?
So this just represents some of our components. I can't bring my entire urine processor assembly. They're relatively large components. They're on the hundreds pounds type sizing, real big, but
it's heavy, isn't it?
But listen here. So what we have here is just one little part, and that was kind of heavy, wasn't it? Right? It was probably about 5-8 pounds or so, but it's kind of original design is something like this, and this is probably 15, closer to 20 pounds. It's got some weight. I mean, I can get some workout in here. And so just this one component is manufactured in a traditional way. I'm drilling out, we're boring out the holes, kind of a traditional manufacturing. But what we have rolling here is a additive manufacturing. So now I'm using that 3D printing to make this same component, same functionality, but now it's about 60% lighter.
You guys have heard of 3D printing, right? Yes. So this is done with metal. This is kind of what I'm studying at school. So you're dealing with the pee, and I'm dealing with the parts that process the pee. Yeah. That kind of manufacturing stuff. That's what I deal with. So that's cool. That's neat stuff.
And so what makes this particularly unique is in our system of processing the urine, right? We have to stabilize it. I'm using that super strong oxidizing agent that's given this green color, but I also have a really strong acid in the environment, very corrosive. This solution is. And so if I were to put aluminum in there, it wouldn't take but a couple minutes before it starts breaking up.
Wait. Okay, so you said a bunch of things really fast. Yes. So you're saying the pee, once it's been processed, you get an acid out of your, so if I were to take urine and boil it, I would get a very concentrated form of that urine. Is that correct?
Yes.
Is that what you're doing, or you're just treating it?
So right now we're just treating it, but
okay.
But that treatment is a real strong acid and a strong oxidizing.
So what do you do with that? So I'm on the space station. I just peed in this device. It's called ECLS, right? Which stands for what?
Environmental Control Life Support Systems.
So I peed in the ECLS system, or ECLS took the urine, and then I separated it out, and then I've got this stuff.
Yes.
Where does this go on the spacecraft?
So now we throw that in our urine processor assembly. And so what we do is we have a fancy still. I'm boiling away the water, and I'm condensing it downstream.
And so but where does it go? Does it become, do you have a brick of solid pee stuff?
We would right? So if it was a solid brick, no water, then essentially I removed 100% of that water. But right now, our technology is just fundamentally, we just cannot remove 100% of the water. We're down to about 86% recovery. So imagine this is 100% water in my urine, my pee that I'm going to process. I throw it in our system, and this is what remains. It's about 80%, 86% water removal. So this is like a visual representation. So how much is left over? So just fundamentally, our particular system can't go to 100%. If I get this to 97% recovery, like I'm really close to removing all the water, it becomes like molasses, like a real thick syrup. And in my technology, my pumps have little hoses and little pickup tubes, and I can't flow molasses in and out. And so it's fundamentally, I'm only getting to about 86% recovery of our urine.
So you said this stuff is an acid.
Yeah.
And you said that if you were to put something like metal in there, it would eat the metal away. So that part, where's that? Who has that 3D printed part? Where's it at? It's here somewhere, right? That valve.
Yeah.
So that valve assembly, is that called a manifold?
It's a manifold. Yeah.
So a manifold is like a place where you put a bunch of pipes in and you control flow out. So if this stuff is really acidic and it eats away metal, how do you keep that part from being eaten away and damaged throughout the process?
Yeah. So now you have to think about how compatible your material is. And so there was some studies done and lessons learned that, okay, maybe we can't make that part out of that type of metal. It's like aluminum, really no-go on this, but titanium is a fabulous material. It just doesn't react very much to anything. So that our new 3D printed parts that are in our urine processor assembly is going to be made out of titanium, and that will not eat away, will not corrode or get brittle in this environment. Yeah.
Like when you say you're only able to take 86% water away, so eventually will they run out of water to drink?
Excellent question.
That is a great question.
Can we repeat the question for the live stream? So what was your name?
Gabby.
So Gabby asked an excellent question. She said if I start with a certain amount of water and I can process and I drink it and I urinate and I get down to 86% water, she's in her mind, she's drawing this graph and she's saying, oh, eventually I'm going to run out of water because every time I do the process, I'm losing a little bit. Is that a good way to say your question? So, yeah, do you eventually run out of water?
In the long run, yes, you do. And so right now, space station, right, we have this technology, and we aren't at 100%, right? So a resupply is still necessary. So the idea of closing the loop, not needing a resupply, not needing our Amazon 2-day shipping, right, that we want to try and make our process more efficient at reclaiming all water, but this is just on the urine side at 86%. But what other sources of water is there? You know, it's not just about urine. Shower water, okay.
I have a question.
Yes.
Different question. Yes.
Do you actually produce this water? Like have an actual brand of this water?
Oh, that's an excellent question.
Oh, like do I make it to sell it? No, unfortunately we don't.
Why not?
Wouldn't that be amazing?
That would be amazing.
I know NASA needs more money, right? So maybe this is the route we need to go. Would you buy it?
Well, she asked a good question because I'm sitting here looking at a bottle of water. It says product water, 0.88 liters, 1.92 pounds. And can you read that number for me? What does that say? $48,000. Is this $48,000?
Yeah. So imagine this is how much one crew member on space station has to drink for one day. One crew for one day. It's just under a liter's worth of water to drink. If I had to ship this volume up space station, last time it was quoted for price-wise was about $25,000 per pound to ship something up space station. So this, not even a liter's worth, one crew for one day to drink would cost you $48,000.
So that means every drop of water we can squeeze out of yesterday's coffee is very expensive, right? So this cup of coffee right here, Dr. Jill's cup of coffee, that's probably $10,000 sitting there.
Yeah. So the more we can recycle, the more I don't have to ship water up, the more science we can ship up the space station. Because that's the point of space station. To do science.
So what you're saying is like, if I can save space, like I can recycle all this stuff, or I can't recycle the food obviously, but you know, I take sandwiches and then I've got my recyclable water. Now if I look at my, I'm just dropping stuff, sorry about that. If I look at my suitcase, I can stick other stuff in there, like my experiments or more clothes or you know, a real comfortable living space or something like that. Is that right?
Yeah, absolutely. So, and an exercise is also something else that you don't think that you have to pack, but for those long-term missions, you're going to have to do some exercise. You've heard of your your bone loss in microgravity, muscle degradation, so you have to exercise to maintain that you can still move your arms and when you get back to Earth. And so exercise. And so if I don't have to ship up water, I can add more exercise equipment.
Okay, so I have a question. So I interviewed. Thank you very much. I interviewed some astronauts one time about a device that they use to work out on the space station. They call it ARED, the Advanced Resistance Exercise Device, I think it is. And they found that in space, you don't use your muscles quite as much, but more importantly, you're not putting as much stress on your bones because you're not like think about right now. What's happening? All my weight's going to my feet and it's going up through my hips, right? So my bones don't have to resist all this stuff. And they found that they're peeing the calcium out of their body.
Yes.
Okay, so if astronauts on space station for, let's say, a year are peeing every day and their body's not using the strength of the bones, your body's smart and it's like, hey, I don't need this much calcium in my bones, and it starts getting peed out. Does that mean you guys see high contents of calcium?
So this was actually one of these real big lessons learned. NASA's very large and big in lessons learned. And so when our urine processor assembly went up space station back in 2008, we were using an acid, sulfuric acid. You know, sounds scary because it is scary. And when we were doing ground testing here at Marshall, we were collecting urine, like we weren't buying it, right? You go into the bathroom and there's this bucket and a funnel and you would contribute the science in. And we would run that pee in our systems on the ground, and we would run to 92% recovery, and it was beautiful. Ran well. We take it up to space station in microgravity. Now we were in a different environment. We didn't understand how much calcium came out, and so when you get into your chemistry classes, you learn about solubility. Can something dissolve in water? And turns out calcium with that sulfate. So we have two of these compounds. They see each other at high concentrations, and we precipitated out. We formed this crystal here. This came off of orbit, so this flew in space. And so this little chunk here failed a multi-million-dollar piece of equipment.
Literally that chunk?
One of the chunks. There was multiple of these chunks, but this was one of them. And so it's just something we didn't know. You can do all the testing you can here, and you just may not be able to mimic exactly the environment that your hardware or your technology will be in. And so we just weren't aware of how much of that calcium came out.
So, okay, we're not scripting any of this, but you're saying that this chunk of dried up astronaut pee messed up a device, part of the ecosystem in space, or something like this.
Yeah.
And we also know, I'm dropping pee over here. We also know that astronauts, can I pass this around?
I would rather not.
Okay. So astronauts pee out more calcium. So is this, in a roundabout way, is this parts of astronaut bones?
Yeah. Oh, yeah. That's a good way to think of it.
So astronaut bone goes into the urine and then goes through the system. You filter it out, and then it starts clogging up your machinery.
Yes.
Really?
Yeah, we were under a condition that we just did not expect. So that sulfuric acid was basically the contributor of what makes this piece here. And so now we switched up how we were pre-treating, so the chemical that we use to stabilize, we basically changed up the chemistry, so now we won't see this anymore. And so we can't really engineer it out at the hardware level, but we engineered our problem using chemistry.
That's pretty interesting. I think that's really interesting.
Yeah.
Should we start taking questions, you think?
Yeah. Well, you had a question right here.
Since they're losing like some of their bones, like when they come back to Earth, like will they be like candy characters?
Yeah. So they really do the exercise on a daily basis. They're really trying to minimize that kind of that weakness when they come back. And so they try that they can. Of course, they're taking supplements too. So if they know they're losing all that calcium, well, they'll take some supplements to kind of backfill what they're releasing.
Oh, oh yeah. When they put on the spacesuits, isn't it like really heavy on them, like when they put it on?
Well, when you're in microgravity, you have no weight.
So one thing, I got to try on a spacesuit one time at Johnson Space Center, and the question is, when they put on a spacesuit, is it really heavy? And yes, it's very heavy. However, in microgravity, it wouldn't be. But the one thing that I didn't expect is when you're wearing a spacesuit and they pressurize it, imagine being on the inside of a balloon animal, right? And all of a sudden what does a balloon want to do? You know, all the pressure tries to rush out and it fills it up. So one thing that I found very interesting is when I went to bend my fingers, I was having to bend the glove because it was filled, you know, like a balloon, like that. And so in order to close my hands, I had to bend against that. It was like being inside of a balloon. I thought that was really, really weird. Yes, but do you guys have any questions in the back? Yes, sir.
So machines break down over time. How do you fix it? And does that mean astronauts have to learn how to become plumbers at some point?
Can you repeat the question in the microphone for
Sure.
the live
So
stream?
machines will break down over time, and everything needs to be fixed at some point. Space is no different. So do astronauts now have to become knowledgeable of plumbing and maintenance of that type of system?
Yes, so unlike the movie The Martian, where he was on Mars for like 4 or 5 years, or however long it was, ecosystem never failed. That's not the case, right? We have limiting factors on our hardware, and really it comes down to your gears and motors, and you know, things do break down, and they do have to service our hardware. You know, if something does fail, these kind of critical components, they have to go in and basically take out the whole thing and put a brand new one in there. And they may have seen the procedure before they started their mission, but it may have been 2 years prior. And so they may have seen it at one time, but then when they're doing the procedure, they may have basically seen it all over fresh to them. But the procedures are written, you know, as clearly as we can. And of course, if they have questions, they call down and they can ask me, hey, I don't understand this procedure, and so we can clarify for them.
So we actually have a question from the YouTube live stream from Brett. He's asking, do you have any IoT applications that are linked to the water supply on the ISS?
Right.
IoT is Internet of Things?
Internet of Things is what I'm assuming here, yes.
Okay.
So Internet of Things, so...
I guess more broadly, what kind of sensors and telemetry do you have sort of attached to the water supply and recovery?
So just specifically to our urine process, our little pee machine, we have over 100 sensors that we can monitor on a daily basis. You know, so we keep eyes on as much as we can while it's running, and we have software that really helps monitor for us, so we're not 24 hours watching. That we have in the code saying, hey, if this pressure sensor starts going really, really high, something's gone wrong, and you need to tell the crew, hey, something's gone on, or to tell console that something's gone wrong.
I have a super simple question. So I'm here on Earth in 1G, and you've got this bottle here, and there's little lines on it, and it says, okay, this is 525 milliliters of water. That's easy on Earth.
Yes.
Because of gravity. If I'm in space and I'm in a 0G environment, how do you measure how much water is in this bottle? Because it's going to be floating around, and you can't weigh it, and you can't look at a line on the side of it.
Yep.
So how do you know how much fluid is in something?
A lot of the containers that we have are essentially little bags, so you don't really have a hard kind of walled surface. That you think of like a little bladder bag that when it's empty, you've basically sucked it out. So if you kind of suck in a container like your little vacuum sealer.
Like a Capri Sun kind of thing?
Yeah, like when you're sucking everything out and everything collapses in. So when it's empty, that kind of bag is really squeezed. And so just visually you can say, hey, it's empty. But then as it starts filling, it'll start filling up like our balloon, and you can kind of get a visual cue. And so, of course, that container says, hey, when it's full, it's going to be some max volume, 1 liter of volume when it's full. And so when you go, well, it's about half full, it's more of a visual type.
But getting back to what the gentleman asked back there, if you have a device that stretches and does things like this over time, does it eventually fail?
Yeah, so there are limiting cycles. So when you can collapse your bag and expand the bag, that there's so many times it can do this function. And so these are life cycle tests that we can do here on the ground, but typically these life cycles are like in the millions, we can say, for some of our hardware. But we have sensors that can track, so sometimes our bags aren't necessarily a bag itself, but think of like a metal bag, kind of like an accordion. And so this accordion bag, but it's metal, that it'll just accordion out and expand out and collapse down. And we can have a kind of a string gauge to kind of where's that position of that tank. And so we can do gauges on that.
That's cool.
Mm-hmm.
I'll ask one on the way up here.
Yes, ma'am.
So if the astronauts are, removing that much calcium from their body, are kidney stones a big problem in space?
Right, so we want them to be as hydrated as they can. And so the more hydrated, then the less likelihood of that. But I haven't heard of any.
I will say this, when you fill out the astronaut application, it is the history of kidney stones in your family is a big section of that. Yeah. So it's a big deal. They'll deorbit you, I think. Yes, ma'am. What's your question?
Will there ever be a first kid in space?
Totally.
Do you want to be the first kid in space?
Yes.
Then let's make it happen.
Totally. I think every astronaut, like deep down, they're all just kids. Like every astronaut I've ever met, they're really, really cool. And so, they get excited about the same things you get excited about, same things I get excited about. So I think deep down we're all just kids, right? It's just whether or not you take the time to invest in your education in school and learn things like how do I fix the pee machine on the space station, right? I think everybody up there is a kid.
Yeah.
Yeah.
I think we had a question back here.
Back to you. I got you.
So I guess I have 3 consecutive questions. So question 1 was, do they use water for the oxygen production? And then I guess question 2 was, because of the 86% efficiency, does that play a factor in the future mission to Mars? And then question 3, for the mission to Mars, if they're using aquaponics to grow their food, would water also be an issue for that also?
Right, so of course we've laid heavily on the water side of ECLIS, so environmental control life support, so water recovery, but air revitalization is also the other major facet of keeping our astronauts happy, comfortable, and alive. And so the oxygen generation is, yes, via the water. And so we do take the water and we'll do electrolysis. We'll hit it with some volts and we split the water. And so we split the water into hydrogen and oxygen. And so we could just vent the hydrogen overboard, but turns out I can react that hydrogen with our CO2, the carbon dioxide. And that reaction generates water.
Wait, what?
Yeah.
I'm not good at chemistry. So
yes.
H2, so hydrogen plus CO2, and you can get more water out of it?
Yes.
And water's like the most valuable thing up there, right? So you're saying you can go from this and somehow, no, that's air. So we can somehow go from water to, and we can get to air, and then somehow we can go back to water.
Yes, there is a path for that.
That's awesome.
It's chemistry, right? That not necessarily NASA developed the chemistry. They look in literature and they go and research what had been done, and turns out carbon dioxide, so carbon O2, CO2, reacts with hydrogen in a catalytic environment, so some magic happens, and my byproduct is water. And so it's a really neat, it's not like a whole bunch of water, it's just some water, but just the idea that we can take our byproducts and react them. So that's the oxygen generation, yes, we do via the water. And so that will take some water from our little bank of accessible water. And so the 86% recovery, and that's just on the urine water recovery side. We have the other source of water in the cabin via just your humidity, right? We have humidity control. And so your moisture from your breath, your perspiration, all that becomes in your atmosphere. And so the humidity, right? You know, we're in here in Alabama, we're very familiar with humidity, that we're able to condense, we're collect that water, and that's actually majority source of our water in the space station and for manned
so you're saying
missions.
like outside, you know, in a hot summer day, if I go to the air conditioning unit, sometimes there's a little pipe sticking out of your house?
And it's dripping.
And it's dripping water. And that's water that comes out of the air, right?
Yeah.
So you're saying Eclipse does that?
Yes, it's fundamentally the same technology. Your little AC unit at your house is basically what we have on space station. It's just a way we have a hot side and a cold side. You got your cold drink on a warm summer day and it starts dripping. You have your little water droplets on your cup. That's what's happening. That cold surface, the water's gonna collect on that surface. And so that's what we have on space station. So that's the majority of our water. It's about 60% is from the humidity side, and then of course the remainder 40-45 is from the water. So we have ways to reclaim most of our other water at the 86%, but what we're actually working on, right? So my technology, our urine, our pee machine, I can only go to 86% recovery right now. I still have a lot of water in here, right? I can see it. It flows around, it moves around. But what we're working on, we're partnering with private industry. So it's not all about the government doing the research, that we work in tandem with other companies, small businesses, larger businesses, that we're working with a private company out there who's working on a brine processor, brine. So when I start removing water from something, things become more concentrated. So this is just super concentrated urine with all of the calcium and my acids and all that's left behind. So this brine. So a company is working on a brine processor to get this to near 100%.
So you can use Eclipse to get down to 86%, and like your question earlier, this other company is getting us even further, so we can get closer to 100%. So we can have more solid pee and more water we can use.
So we're trying to close that gap as much as we can to help support, because we know how much it costs just to get to space station. How much is it going to cost to get to Mars?
I think
to support Gateway, support the moon missions.
I think you had a question, right? What was your question?
How do you like when the machine, the pee machine breaks down? How do the astronauts know that it's broke? Like, is it a computer in there that tells them, or like, do you contact them in a certain way?
That's a really good question.
Yeah, very good. So the crew, right, their purpose of space station is to do science. And so we try to minimize as much of their attention as we can. So when something goes wrong, typically people working console, like mission control, right? People are working console, that they'll be the ones that'll be notified. And primarily it will be via software, right? We have software that's coded in to help flag, hey, something's gone wrong. And so console will get the message. And then essentially at that point, depending on how bad that red flag is, then we will talk here on the engineering level here at Marshall to decide, hey, yeah, we need to have that component replaced. Or can we do it on our own end and do some troubleshooting on our own end? So we'd really try to minimize how much crew time to have them do, but it's right at the moment where they actually have to go in and do the maintenance to fix our stuff. Then we'll call them in and help support.
I just found something under the table, and I think it's what I think it is. It says, drink this when real water is over 200 miles away.
Yes.
Is this pee water?
That is for real, start to finish water. So we collected some of our pee, we collected some of our sweat, and we processed it start to finish in our kind of pee machine and our humidity condensate collection, and finally our water processor, that kind of final scrubber, that final filter. Start to finish, that's what you got.
Somebody has to ask the obvious question. What is the obvious question here? What does it taste like?
You want to try it?
I can try it?
You want to try it?
It says 2005 on it.
It's vintage.
So this is pee from 15 years ago? Really?
Yes, it is true to form.
Can I smell it?
Hey, you can smell it. I may have a cup for you to sample if you want, but this is our vintage 2005
I smell it. I can smell.
What's it smell like?
It smells, doesn't smell like pee. Can we drink it?
I'll take a swig.
Are you serious?
Yes.
I'm doing this. All right, so can I pour some and let people smell it?
Yeah.
So this is
Yeah.
very expensive, right?
Yes.
Okay, so I'm gonna let you pour it because I don't want to.
But there's like a technique, right? You kind of go.
You know how you
like
go to a
this.
fancy restaurant
Yes.
and like the guy brings
gotta,
the
yeah,
wine,
like,
it's
gotta
would
do
you
this,
like a
you know?
finest 2005?
Oh, sorry, I should have showed you the bottle first.
The bottle. Oh, it's just good.
Okay.
That's good. That's good. All right, so we can seriously drink this.
Yes.
I want somebody else to smell this. You guys want to smell it? We're gonna smell this pea water together. Let's just, hey, we're in it thick. Let's just do this, right? Just smell it.
You can do the technical wafting.
Wafting, yeah.
To
Do
waft
you have the
it to
microphone?
you.
Okay, so I want you to smell this. I want you to tell everybody in the room what it smells like. What does it smell like?
Like cleaning products, kind of? Like
Yeah?
bleach?
Like what?
Bleach.
Yeah? What does it smell like? What does
Like chlorine, with like
Chlorine? Is there any chlorine in this? No chlorine. Would you like to smell the pea water? You would? So do all fancy. Do you have to hold your pinky out when you drink this? No, she's no. You
also
just kind of smell
plastic.
it like that. Smelling thing?
Is that a BPA free bottle?
Smells like a what?
fresh code.
Okay, she says it smells like the cup.
Well,
Okay. All right. So, can I seriously drink this? Okay.
I dare you.
You dare me. All right. So here we go.
I'll do it with you. That way
Chug.
we both
chug,
go down
chug.
together.
All right. So here we go. Ready?
All right. Cheers.
I'm holding my pinky out.
Right.
This is so weird.
Who's ever gone camping
It's
and you had that iodine packet, that little pellet you put in your water? Kind of has that kind of medicinal, kind of metal kind of essence to your water.
I feel like the energy of astronauts is entering my body right now. Yeah, it's like,
And so what he
except you did this on Earth, didn't you?
Yeah.
Okay, this is an astronaut.
Yeah, this is an astronaut.
Am I drinking your pee right now? Did you work here in 2005?
I won't say.
Okay, so I've got
So basically, what you're smelling and what we're tasting is iodine. And so
Matt, will you take a
so
picture
so
of us?
we're
Here,
so we're doing
just come up close. I really want this picture because I don't think I'm going to do this again. All right, so picture number 1, yeah, and picture number 2, pinky out. Yep.
Fantastic.
It's kind of
I should have toasted it.
it's sterile.
Oh.
It's sterile. And I like the taste. The dodgeball reference. Yeah. So all right.
Yeah, so we're tasting iodine because that is kind of the way that we keep the little bugs from growing. And so you were talking about chlorine because that's how we have our water stay clean, is using the chlorine in our water. But we don't use that as our choice chemical. It's iodine. So he's tasting this iodine as a way to keep the bugs from growing.
Yeah, I'm going to be real with you. It kind of feels like it's just water. And it feels like there's more of a mental hurdle to get over. Yeah. And, once I started drinking it, I was like, well, this is surprisingly boring. Meaning it's just water and there's nothing, we kind of like to go, ooh, and stuff like that. But this is just how you stay alive on a long space mission. So go ahead.
Anyway, we got 2 questions from the live stream. One is from L33, which says, when you process the pee and the bad sludge comes out of the system, what do you do with the sludge? Is that shipped away with the rest of the waste?
Right, so at the end of the day, we're done processing. This is what's left over. We don't want to process this to any more water recovery. That we basically have a really big tank of all of this fluid, and that shooting star you made a wish on. Was that a star or was that?
Oh, you say they deorbit it.
Yes.
They deorbit, so they put it in.
So they put it in the vehicles that aren't meant to come back home.
And they burn up in the atmosphere. Yep. Wow, that's amazing.
And one more from Danny DeVito. I don't know if it's...
It's real. I choose to believe this is really Danny DeVito.
So the question is, with this technology, will the International Space Station ever become entirely self-sufficient?
I would bank on not entirely self-sufficient. We still have to have a human presence in there, just to help do the maintenance. Of course, maybe in 100 years our hardware will be never in a failing state, but we will still have to have some interventions.
Well, I think another thing Danny DeVito might be pointing out is, like, do we still need resupply missions? Will we always need to ship water to whatever spacecraft? Or
I think if we are at 100% removal, or sorry, 100% recovery, yes, fundamentally we don't have to ship up anything. But wouldn't it be nice to just have some fresh water?
Yeah, or like an apple or something like that. Yeah. I feel like I shouldn't waste this. Should I drink all of it?
Yes.
Because I can't put it back in that bottle, right?
I would enjoy it.
I'm pounding it. It's just water. That's pretty neat.
Yeah.
Any other questions before we finish here?
So is there any DNA left, and can you tell whose pee it is?
That would take some amazing science.
But it gets really stripped.
That's a legit question.
That's a legit question. It's interesting. I want to say that we probably aren't super, like, at microscopically DNA level clean, but we are really clean water. And in fact, what the astronauts and our crew are drinking, cleaner than what you drink here.
Wow.
Cleaner. Super, super clean. It's like that distilled water that you can buy in the bottles. That's at the level that the crew is drinking on a daily basis. Really, really clean. Maybe there's some DNA thrown in there, but I'm not a microbiologist.
There's a question in the back.
Yeah, speaking of working with other industries, what the thing that you are working on now or in the future to reduce costs or other thing, smart ways or anything?
Right. So our baseline for space explorations beyond lower Earth orbit is the technology that we have on space station. But we can be better. I know I can be better. Our hardware does fail. And can we improve to make it more efficient, more reliable, more maintainable? And so we're actually actively working on making our hardware better. We're making heavy components, to much lighter components, using new and upcoming technologies. That additive manufacturing, although it's not necessarily new, but what we can do with it is changing. And so we're working at our hardware level to do technology demonstrations. Space station will become the new test bed. We're going to test all of the new stuff, our new upgrades and new technologies, right? This brine processor assembly, this is going to be new technology. We're going to test it. Space station is going to be the new test development platform to challenge us to test. We want to test in microgravity because I know what happens if I don't test in microgravity, things going to happen. We have to test in microgravity, and the closest science lab that we have is going to be space station.
It kind of feels like camping to me. Space station feels like a camping trip. And, the moon, we just, when Apollo astronauts went to the moon for the first time, they were just checking out, like scouting out a new place. Mm-hmm. Space station feels like practicing to live in space. And then when we go back to the moon, to me, it feels like kind of like the Lewis and Clark expedition, where you just start going out slowly. But we're not even past, like, St. Louis at this point, right? And so we have to slowly go further out into the unknown. And it feels like we have to learn how to do things like survive with the resources we have on hand.
Yeah.
So we're learning how to do space, right?
Yeah, absolutely.
Yes, sir.
So going off that DNA question that she said, you're collecting all of this urine in a tank before processing. So is it all mixed together so you couldn't tell anyway?
Right. It's relatively homogeneous of all crew using our urinal.
Is there a difference in the urine collected on the American side of the space station versus the Russian side of the space station?
Right. So there are basically 2 toilets on space station right now. We have and space station, it's the International Space Station, right? It's not just the U.S. side. There's this international agreement. And so there is the Russian side has their own toilet, and we have our toilet. And so essentially, they're basically the same, but the only difference is when we collect our urine, we're using this alternative pretreatment that has the other acid, this phosphoric acid. The Russians are still using that scarier sulfuric acid to where we could get back to this if we process a whole bunch of the Russian urine. And so there are a couple toilets on there actually on the space station. Yeah.
So whenever you built that machine, you said that one of your machines stopped due to the P cluster, I guess. And so is there already a new machine so the old machine broke. So have you already came out with a new machine?
So what failed, so what did break was one of the multiple components. There's different functions within our P machine that just that one little part, that little 1 of 5 broke. And so we were able to take the broken part and put a new one in. And so we have extras of what we need to make our machine work. Just the one part, yeah.
So if you think about, it's a really excellent question, because if you think about how you make an engineering system, right? You have all these things that are working together, and you could go down to the part level on every single component of it, like the gear or the tube or the bag, or you could make these line replaceable units where you could take out a whole assembly and put a whole assembly back in there. Like when you do your code for the apps challenge, right? Are you going to start at line 1 and go to line 2000 or whatever? And just you're going to have chunks of code that do different things, right? I assume your machine's the same way,
Correct,
right?
yeah.
Yeah, so you can replace different parts of a machine like that, like little component groups.
What happens if the astronaut gets lost in space?
Lost in space. Didn't they make a show out of that? So I guess in the space station itself, you have little modules, things sticking off, and I guess they could get turned around and lost in the space capsule. But I guess when they're going on their long-term missions, I would hope they wouldn't get lost, but hopefully they have their GPS system to get them back home.
In the back?
Yeah, quick question. You mentioned a boiler as part of the process. So what's the cost of running the boiler? What's your energy cost of putting the kettle on?
Right, so our P machine, our urine processor assembly, when we're running full bore, it is about 400 watts. So it really doesn't take much energy to get it done. I mean, that's like a light bulb, right? 400 watts. So it's relatively efficient on the power front, but we know we can be better. Just at the level of some of the heaters that we need for managing some other byproducts in the system, that we have to have these heaters, and that's like half the power right there. So if we can fix some of the problems that are driving the necessity of the heaters, then we can drop that about half.
I saw them hand the microphone to Bobak for Dowski back there. He put a rover on Mars. Did you guys know that? Everybody recognize Bobak's Mohawk?
So you mentioned earlier about the Lunar Gateway and potentially further destinations. I'm curious how the fact that there's resources at those locations potentially affects the decision for how much more effort you put towards getting better efficiency versus extracting the resources more directly from those venues.
Supporting those missions. So if you want to have a more permanent presence on wherever you're going, Mars, the moon, an asteroid, wherever you want to go, if that landing spot has some of these vital resources, then obviously, yes, we will try to scavenge as much as we can for our purposes. And therefore, we may not have to bring as much with us.
So that's called in situ resource utilization, right?
That sounds great.
In situ, I think. So like this is Mars regolith, right? Like so if there was, so you're telling me you can convert hydrogen to water. So do you think, are you guys trying to figure out, or are you working with other centers to try to figure out how to get things out of the rocks or out of actual water on Mars?
So in this vial here is what it's basically mimicked Martian soil, this regolith. And so you kind of see the kind of red-orange color. It has a lot of iron in it, the rust, right? So this is basically rusty dirt. And so we're looking at how can we take advantage of this resource. And so iron could possibly be a catalyst catalyst for some reactions. And so can we use this iron to help us make our processes more efficient? Or can we use it as a building block and maybe make concrete manufacturing stronger? You know, all these different ways, how can we use, I think that's just part of human exploration and establishing a presence, is using your resources that you have. And that's what we're going to try and do.
That simulated Martian soil, does it have the same toxicity level? I think it's trichloride.
A good question. I probably has that chemical in there. I think it's more at the level of the size of the grains and kind of more of the macroscopic kind of constituents. I didn't make it. I don't know. I just have a vial of it. Yes, ma'am.
Okay, so as you said, so let's say that you. Oh, okay. So you have your. So somebody who works with like the same thing, studies the same thing that you are. Have you ever sent like anybody up to space to like do exactly like what you're asking them to do? Like have them test it, or somebody who works for you go up into space to test what you do? Like
sure.
Your
If there's a way that we can use space station for exploring new ways to do our processes, then yeah, we'll try and we may not be able to send our own engineer to go up and do the experiment, but these astronauts, they're just rock stars. They are so like Renaissance, like they can do a lot of it, a little bit of everything. And
So you hang out with astronauts.
I wish I did.
Do you ever train astronauts?
No, but we will try and develop trainers. And so when we develop some of our new hardware, we're building up the trainer. Like what will the crew actually be training on? So we try to be at that level, but we don't actually interact one-on-one with them.
Gotcha. So there's a lot of people behind the scenes doing
Yeah.
stuff. How about we take 2 more questions, and then we'll move on to the next thing for the day here. So, yes, ma'am.
I have a question about the helmets.
The helmets?
So, when like you have on the helmets in the spaceship, how do y'all communicate with each other?
When you have on the helmets for the spaceship, in the spaceship, how do you communicate with each other? Have you ever heard of the little Snoopy helmets? They call them the Snoopy helmets. So they have these little things that they put on the inside of an astronaut helmet. And what they do, I think one of these is my astronaut helmet. I forget where it is.
Maybe out.
But they have little earmuffs that go over the top, so you have speakers in your ears, and you also have 2 microphones in case one of the microphones goes out. That's how they communicate. And they have a little radio that they can talk back to a central radio that can distribute that information everywhere. Last question in the back.
So from a mechanical standpoint, I know you mentioned that you have to deal with acid causing wear on your mechanical components. Do you have to deal with wear from constant heat cycling, like when you turn the ECLA system on and then off and then on and off?
Yeah, so heat is a consumable. Also, it can cause harm, but we have those cooling loops, and so we have ways to keep the components that we know are going to get hot, that we try to keep them cool. But that is a factor of wear. Every time it turns on and off, on and off, on and off, that just adds more wear. And so we track how many cycles things turn on and off, just to understand, okay, yeah, this thing will probably fail in the next 6 months or something. But heat is a thing that they track, and they will monitor, and they say, hey, you're taking too much of that heat load. You know, you're taking all of our cooling from other components.
All right, so I know I learned a lot. Let's thank Dr. Jill Williamson for her time. Thank you very much.
Thank you.
Yeah.
Let's finish my drink.
Yeah. You'll excuse me, I'm going to go make yesterday's coffee into...
No, today's coffee.
Maybe tomorrow's coffee.
Now let's hear it for... Wow, Destin and Dr. Jill. What an amazing... Okay, is this incredible? I mean, this is awesome. And who knew? Because, you think about, okay, Mars ain't the kind of place you raise a kid, but their work is going to prove that you can. Anyway, because of all their discussions about, bathroom breaks, we're going to take a 20-minute bio break. So come back in 20 minutes, and we'll be ready for the next portion of the show. Thank you all so much. Say hey to the rest of the world.
when we're ready to go.
I'm just helping out. I don't really know myself.
Two, one. Hey, Matt Jones with NASA Space Apps Challenge. We are so excited to be sitting here with Jill, who was just on our main stage. And Jill, you had a chance to spend time with Destin. He asked you a ton of different questions, kind of going deep on that. But I want to go back a little bit farther. Tell me a little bit about how you got into science to begin with.
Right, so I've always loved science. I had a dad who always worked on the car, and he always brought the girls out. He never had any boys, so he's like, come on girls, come work on the car. And we loved to go to air shows and just always was involved in the sciences. It's fascinating. And then I wanted to be an astronaut.
Oh.
But then I realized I get motion sick.
No, that seems like that would be a problem.
So, well, how else can I be part of NASA and be an astronaut, be part of the astronaut kind of team? And so I decided to go and study chemistry. Because at the time, if I couldn't be an astronaut, I didn't really know what else I wanted to be, but I knew chemistry would open up a lot of doors. And so I got my bachelor's in chemistry, and I guess I wasn't ready for the real world, and I ended up going to grad school and got both my master's and PhD in chemistry. But while in grad school, I picked a NASA fellowship. And so I was like, wow, this could be a path.
Okay, so explain what a NASA fellowship is.
Right, so it's funding to go to grad school. So this program was able to pay basically stipend, a monthly stipend to help pay the bills, essentially. Nothing much more than that, but it was an opportunity to work on a project that would help NASA's mission. And then part of the program was to do NASA internships at any NASA center. And so we had a connection here at Marshall, where I was able to come in on the summers and work on my projects. And at the end of the day, I graduated with my PhD in chemistry, but I couldn't get hired on at the time. There was some hiring freeze. So I went around, and so I needed a job, and I was also interested in pursuing teaching at the tenure track level at the colleges. And so I dabbled, and I was a visiting assistant professor over at Bucknell University. Okay. And so I did that for about a year, and then I hopped over to industry and was in an analytical lab down in Birmingham, Alabama, and then shortly thereafter I hopped on board with NASA and started working on this team of environmental control, life support systems, and then hopped on.
So kind of full circle from the fellowship of NASA, a long road. So sometimes getting where you want to be is not a direct road.
Yeah, and then it's my research advisor, sometimes you have to go away from home to come back, and so I take my path as such a wonderful path. I got to experience what it's like to go teach, to go at the college level and go teach. And then I got to go see what industry's about and see how that is. Okay, now let's go see what the government level work is and kind of that impactful. And so I got to try out a lot of skills in a lot of different ways. And you really get to figure out what you really want, what kind of passion you want to pursue. To me, it's say yes to all those opportunities. It may not be where you want to be right now, but sometimes you have to go a little further out, gain some more skills and more worldly knowledge. And then when you come back, when you get that job opportunity, you're just that much more prepared.
All right. So it sounds like, I think that's really good advice. Even though you want to go into a very specific field and opportunities that give you the skill set that actually helps you to be successful later on in doing the very thing that you had kind of set your mind to do to begin with.
Right. So I have a degree in chemistry. When you think NASA, you're thinking engineers, right? You gotta have an engineering degree, but that's not necessarily the case. You can have a chemistry bound. You can have your liberal arts fields where you have to help market and push us forward. So it's just all sorts of facets, and whatever skill set you have makes you unique and it makes you that much more stronger.
Yeah. Well, you did a great job in there, and I know that everyone's very focused just on the recycled P aspect of it, but I appreciate that you brought in that there's a whole lot more to that. There's a lot of chemistry, and it really is, as you said, it's like the entire environmental system being processed through that, and so that's an amazing thing.
We'll all feed into each other. It's not isolated. It's not just water recovery. Well, we also have to help on the air side, you know. Yeah.
Well, great. Well, thank you for taking a few minutes and sitting down with us, and it was a great presentation, great interaction, and everything else. So I'm Matt Jones with NASA Space Apps Challenge. Thanks for joining us.
Thank you. Awesome. Yep.
Next round? You are, aren't you? Yeah, we got to have these students up here. You guys asked great questions. Okay, so how fascinating was our last session? It was really cool, right? It was. So now we're going to go in a little bit different direction. We've got Dr. Helen Lean and also Guire, I forgot his name. Yeah, thank you. Guire Sinclair, thank you. Guire Sinclair is going to join us next. They're going to talk about biomimicry. They're going to talk about the art of and STEAM and how science, technology, engineering, art, and math mean so much. They're going to talk about constellarium. I've never heard that word before. Have you guys heard the word constellarium? I think Guire is going to talk about that. They've got great presentations. Dr. Lean, come on up. Sorry, I forgot your last name.
All right. Good morning, everyone, and thank you very much for this opportunity to share something that I think is super cool and I hope may one day save the world. Before I start, I wanted to share an example of one of my favorite photos that comes from NASA. Seeing the world at night, and you see these spots of bright light, and they almost look like they're reaching out to each other. And it reminds me a lot of the neurons in your brain and how you have these central bodies that are just desperately trying to form connections with other neurons. And I feel like that's what we're doing here today, that through NASA Space Apps and my screensaver, we have this opportunity to reach out to each other, not just here in Huntsville, but across the world, and to tackle some of our world's greatest problems. And so when I was asked to come and speak today, I wanted to give you guys something you could use this weekend that may inspire a solution or even find a way to solve a problem, maybe even come up with a problem we didn't even have before, I don't know. So what I want to share with you is a resource. Where can you freely access novel and useful innovations backed by billions in R&D? So of course, we're here at NASA Space Apps, and that would kind of be the obvious answer, right? And you wouldn't be wrong. NASA has a wonderful publicly available database full of their innovative patents that you can use, and I recommend that you check that out. But I want you to consider this. That's our world. That's what makes us unique and amazing. And all of these organisms that just flash before your eyes have at some point inspired a new technology, a new design strategy, or a new innovation. This portfolio of nature's genius is backed by 3.8 billion years of R&D. That's where the billions came from. And the portfolio currently comprises 8.7 million species of organisms. Just to put that in context, if you had a 256 gig iPhone X, who wouldn't want one of those? And you took one photo of each of these organisms, you would need 100 iPhones just to capture the beautiful diversity of life. In looking at these organisms, we know that there are ones that are immensely small, like bacteria and archaea, that aggregate to form, oops, I am learning how to use a clicker, so bear with me. I might go right here. Sorry. So here's the laser pointer. So you can see these archaea and bacteria have formed these bacterial mats. These are some of the descendants of the earliest forms of life that we found. They're practically primordial. And here they are, right here at Grand Prismatic Spring in Yellowstone National Park. And you can also see some more recent species like us walking on the boardwalks right here. And we are hardly visible in this aerial photograph. So biomimicry, according to the Biomimicry Institute, is the conscious emulation of nature's genius. The idea that we can learn from nature and the innovations that we find in our natural world and adapt those solutions to our very human problems. So where to start? Well, there's two simple questions. The first is, what would nature do? Well, nature uses locally abundant resources. It doesn't waste. It's energetically conservative. It uses chemistries that are compatible with life. The second question we should ask is, what would nature not do? It would not waste energy. It would not waste resources. It certainly doesn't use chemistries that can cause us to die, because then, you don't have the next generations. And it does everything while still maintaining the necessary functions of life and perpetuating life. Contrast that with our current manufacturing methodologies from about the last 200 years, where we are polluting, where we're generating large carbon footprints, where we are sourcing our materials from all the way on the other side of the planet, and again, creating more carbon emissions. So I'm hoping what we can do today is share some ideas with you to create design strategies, manufacturing strategies that are kinder and gentler to our world and allow us to live more peacefully with the organisms that we share it with. Biomimicry can happen on 3 different levels. There's the level of form. Think of that as biomimicry on the organismal scale, as well as parts of the organism that are functioning. So I don't know if you guys could hear our students in the audience, but as we were scrolling through the pictures and they saw things like spiders and mosquitoes, they did not have very favorable things to say. But then, of course, you look at these beautiful flowers and you're like, oh, wow. All of these are forms that you're looking at. The second level of biomimicry is biomimicry of strategy, also known as process. Think about that as behavior. So when you see those gorgeous sunflowers, if you watch them in a field, you would notice that they follow the sun over the course of the day. That's a strategy that they've developed to capture as much sunlight as they can. Finally, by combining form and strategy, we have biomimicry at the system level. So that brings to mind things like a circular economy, where the waste of one process becomes the raw materials for another. So the elements of successful biomimicry are pretty simple. There's 3 of them. And the first is inspiration. So the best way to get inspiration from nature is to go outside. In addition to getting a great workout and doing great things for your body, increasing productivity, increasing your focus, increasing creativity, you also get to spend time and actually observe nature's R&D playbook for yourself. All right. Our second element of successful biomimicry is function, right? So you're here at NASA Space Apps. You are trying to create a functional product. So, and being an engineer, that's like a big thing for me. If it doesn't work, if it doesn't do what you say it's gonna do, you probably have to go back to the drawing board. And so here's a stone bridge that you can come across in Iceland. And I often think of the biomimic as this person right there. I will learn how to use this clicker at some point. And you've got your biomimic right here, crossing this bridge. And so the goal of biomimicry is to look at your design challenge and map it to nature's genius on the other side. The biomimic crosses this functional bridge by tying your design challenge to a specific function, mapping that function to a natural process, and trying to find the solution there. Oftentimes, these functions are solved by multiple organisms and not just one, so you've got a lot to choose from. All right, so if we stylize this out and we look at the 3 different levels of biomimicry, we have our function, and functions can be divided into several categories. A really great resource for you this coming weekend is asknature.org. Asknature.org has taken all these amazing organisms, created a database, sorted them by function, and it's completely searchable. And so, for example, you can say, how do organisms get, store, and distribute resources? And it will pull up literally hundreds of examples, including how these organisms do it, why they do it, and what the benefit of how they do it can give you. All right, so our third element of biomimicry is sustainability. So at the end of the day, what we're trying to do is to allow ourselves to live on our planet a little bit longer. Biomimicry is tapping nature resources as we recognize that these strategies are able to allow us to continue existing on our planet. And at the end of the day, that sustainability win is what we're going for with biomimicry. And I think you're going to find that's very applicable to some of the problems you're facing this weekend. At the heart of sustainability, what we have to be able to do is to meet our needs for today, but still have the ability to meet the needs of tomorrow and not compromise that ability. So I'm looking at our future right here. So those of you who are far away, they're seeing right here, they are the reason why we need to do this, because we want you guys to have a nice place to continue living, shopping, and going to school, and creating innovations, and cleaning pee-pee. That was really fascinating, by the way. That was actually a really great sustainability project, because you don't want your astronauts to die of dehydration, right? So I'd like to tell you a story that has a lot of these elements of biomimicry in it. And you've probably been wondering why I keep showing a slide of kids wearing Velcro shoes. Velcro was given to our world, invented in 1941, when a Swiss engineer went on a hunting trip with his dog, and he came home. And he noticed that his wool pants and his wool socks were covered with sticky burrs. Has anyone ever encountered sticky burrs? Those little pokey things, yeah, that like get all over you when you've been outside. So that's probably where the unladylike words came in. So after he picked them all off of himself, and he picked them all out of his dog's fur, he noticed that they did something pretty remarkable. After he unstuck them, if he wasn't careful, they would restick. And so they could unstick and restick over multiple use cycles, and they really never lost that adhesive property. And he thought, well, that's very different than traditional glue. Why does it do that? And so he put those sticky burrs under a microscope, and what he saw were thousands of little microscopic hooks. And these hooks were just the right size and shape to catch hair and fibers like woolly fleeces and dog fur. And he thought, well, that's really interesting. I wonder if I could use that. So he took that inspiration that he probably really would rather not encounter in nature, and he mapped the function to stickiness, and then he emulated it by recapitulating those structures in nylon. And once he did that, we had Velcro, a very useful material. So here's the sustainability component that I'd like you guys to think about. One thing I didn't know until relatively recently is that a lot of the trash we generate that we think is recyclable actually still goes to landfills. And the reason for that is they have been glued together, and that glue fouls the material for recovery. And so here's an idea. What if we could take Velcro and you manufacture it at different scales, smaller and bigger, and consider using it to put our products together? So at the end of its useful life cycle, we can ship it back to the manufacturer, and they can just pull it apart and reuse those materials. So if we can do that, think about how much less full our landfills would be and how much more conservative we would be with our resources. So I've got a few examples of some amazing biomimicry products, and this is one of my favorites. So anyone who's ever been to the Huntsville Botanical Gardens has been to the butterfly house, where you really, really hope a butterfly will land on you because they're super pretty. And while you're watching them flap around, you'll see they have these amazing, colorful wings. So some of you may know that blue is not a naturally occurring pigment. And the way that butterflies achieve these brilliant blues is through structural color. They have these little nanoshingles on their wings that manipulate light. And as that light is absorbed by the wing and refracted back to our eye, we see a beautiful color image. This idea has been adapted for TV screens, and it's currently being also explored for self-healing glass. I have shattered my phone screen a handful of times, so I will say that that would be a really useful feature to have on an iPhone. All right, our kingfisher bird, he's super cute. So a birder who has also happened to be an engineer on the bullet train project in Japan noticed that this guy here might actually solve a problem that he was experiencing with the bullet trains. As bullet trains go through tunnels, they create a compressed air wave, and as they exit the tunnel, it generates this giant sonic boom. The neighbors didn't like to hear it. The wildlife in the area didn't like to hear it. I'm guessing property values had something to do with it. You know, there goes the neighborhood. And so he noticed that when kingfishers dive into water, they do it nearly with no splash at all. And so he thought, well, that's interesting. And adapting the front of that train to mimic the shape of the kingfisher's head and beak, they were able to decrease drag on the train, increase efficiency, and eliminate that sonic boom. An additional biomimic that he had chosen was he also frilled the side of the train, much like the owl's wing. And as some of you may or may not have experienced, owls have this amazing ability to fly silently. All right, aquarium touch tanks are something my family really enjoys. Not that you want to touch this guy here, but he's got some smaller kinfolk that you can pet. And one of the fun things that you'll notice is they're not slimy. So when you go and you pet a shark, you'll actually feel a texture almost like wet sandpaper. That texture that you're feeling are the dentasoles on the shark. And these little dentasoles are just these little nanostructures, and they allow the shark to swim very slowly, but they don't foul. They don't develop bacterial growths on their skin. And so adapting that technology, anti-fouling surfaces can be created, and Sharklet Technologies is leading that particular charge. All right, I heard oohs and yucks and stuff like this. So those of you that know me know that I love to go hiking and that I will do almost anything not to be the first one down the trail, because we call the first person down the trail the web breaker. And I've even gone so far as to get my husband a GPS watch, so I had like a legit excuse to send him down first. He's in the back of the room going like, is that what happened? So sorry, honey. You still get to wear the watch though. So the question, though, is why are humans being the web breakers? I mean, you think about the early bird that gets the worm. I mean, in these forests are birds. They're flying around. Why are they not the ones that are crashing into these webs? So a group of really smart people decide to take a look. So as spiders are spinning their silk out of their little spinnerets, they can make different kinds of silk. One of them is highly reflective of UV light. And so birds see that, and they know, hey, there's a web there. Now, office buildings often have the problem of birds crashing through their glass or against their glass, often with fatal consequences for the bird. So Ornolux Mikado glass incorporates UV reflective strands in their glass in a pattern that signals to birds that, hey, there's something here, don't fly through it, or at least don't try to fly through it. All right, so I'll admit our family loves these Disney movies about lost fish, and oftentimes when we look at pictures of coral, we think of the beautiful diversity of places like the Great Barrier Reef. What a biomimic sees, though, is biomineralization in a way to use carbon and calcium in a concrete making process, which I think is super cool. So traditional concrete making goes back to that heat, treat, and beat philosophy of current manufacturing, and it produces a lot of CO2 emissions. For about 1 ton of concrete, you're generating about 1 ton of CO2 emissions. So if we can use seawater, capture the carbon dioxide in the seawater and the calcium, and precipitate that out through a process that's compatible with life, we're gonna borrow this recipe from coral. We can now make concrete, and instead of generating CO2 emissions, we can actually sequester CO2. This is huge right now, given that we are in an era of global warming. All right. This is the state bird of Alabama. I'm just kidding. I know it's not a bird, but it kind of feels like it. So the mosquito. Oftentimes, you do not know that you have had an encounter with this with this insect, we'll just say it nicely, you won't know that you've had an encounter until you have felt that telltale itch under your skin. And you do that really, innocent, like you just scratch it a little, and next thing you know, for like the next like a million days, you are scratching that same spot. But at the moment that you got stuck, you didn't know it. But think about when you got your flu shot, you definitely know you got stuck with a needle, right? So the structure of the mouth parts of the mosquito are really jagged. And you would think that that would actually generate more pain. But in fact, because it has a lower surface area, it's not rubbing along the nerves of your tissue. And so using electrochemical etching techniques that we use to make the chips in our phones, the chips in our computers, one group is starting to develop a painless needle. Not only is it painless, but it's smaller. So think about patients who may need insulin pumps, for example. They don't want to carry around a big device. What if we could make that smaller and make it painless for them? All right, so this one's my favorite. I take my family to the beach a lot. I personally find the beach to be really boring. Don't kill me for it. And the only way I can really stay focused at the beach is if I start collecting things. And so here's an assortment of things that we found at Cumberland Island National Seashore. And when you look at these beautiful structures, you'll notice that shells can be bivalves, like these giant Atlantic cockles, or they can be univalves like these lightning and knob whelks over here. And they all have this diversity of shape, and these shapes are really beautiful. Biomimics have been looking at these structures, and they have thought about habitats, adaptive architectures. One group has even taken the geometry of shells and their ability to be lightweight and thin, yet structurally supportive, to make pedestrian bridges out of a single sheet of metal. I highly encourage you to take a look at Tonkin and Lou's Saline Bridge. It's beautiful, and it is truly a feat of architecture. Also, notice that shells keep growing, but they also stop. What's telling them to stop? Well, there's a signal there. Can we capture that signal, use it to create anti-scaling materials, for example? And so this is really kind of where I started my journey with Huntsville Steamworks. So shells, their general geometry can be described as a spiral or coil moving down an axis. So imagine here, you've got this tube moving down this central axis. We can see it again right here. These are light bulb filaments, by the way. They're really beautiful. And David Raup decided, well, hey, I bet we can mathematically describe shells by modeling this coil going up and down an axis. And so he created 4 parameters. And the very first was the shape of that tube making its way down. And so think about shells like cupcake frosting. I know, everyone's like, oh my God, I'm hungry because lunch is up next. It's really hard being like the speaker right before lunch. So there's some cupcakes. And if you've ever piped cupcakes, have you guys piped cupcakes before? Okay, maybe I'm the only one in the room. There, I got a couple. Okay, so when you pipe a cupcake, you know that when you change the tip of that cupcake that piping bag, you can get really smooth frosting like this vanilla frosting here if you use a round tip. I know, right? And I'm about to say the magic word right before lunch, chocolate. If you change the tip to a star tip, and you'll get this nice corrugated pretty pattern like this chocolate frosting. Shells are much the same way. So imagine changing the shape of that piping tip as your spiral is making its way down that central axis. So the other 3 parameters, I'm just going to run through them really fast, is how quickly that spiral grows in diameter as it's making its way around, how quickly it's making its way down the axis, that's a translational point, and then how much it's swinging away from the axis. So by combining these 4 parameters, we can now use math to describe life. And so I thought, well, let's prove it, right? Can I actually pop in some mathematical parameters and manufacture life? And so I went to Huntsville Steamworks. I had this very, very awful 3D file. And I met a young man by the name of David Mercer, and I said, hey, I want to 3D print this. And he looked at me and was like, oh, that's a terrible file. I'll fix it. I'm going to print it. And so we printed this orange shell right here. And I went home and I was like, okay, cool. I have used math, I've designed life, and I've printed it, I've manufactured it, I am ready to go. I was about to put it in a box with some bunch of other shells when I realized that it looked almost identical to a shell that my grandfather had given me like decades ago, right? And I thought, oh, that's really cool. I want to do it again. And this time I had a model organism in mind. I wanted to make a nautilus. I thought, gosh, nautilus are so beautiful. Whenever people talk about golden ratios, you see this gorgeous spiral, and everyone talks about this feat of engineering, right? This nautilus design is really, really ancient. It's one of our most ancient creatures. And so again, I used math. I made a design file. I found David, who was probably avoiding me at this point, and he very nicely popped it back onto the 3D printer. And we printed the shell, and you can see it here in the bottom corner. It's still on its little raft, and it looks a lot like that nautilus shell. And that's when we thought, hey, we're onto something. And so what we've done at Huntsville Steamworks is to design a traditional engineering class around SolidWorks 3D CAD. And this is a skill that I'm sure any engineer will attest is absolutely essential to becoming a functioning engineer in our society. You gotta have this skill. But here's the thing, what if we taught you biomimicry at the same time? So as you're learning these design skills, you have the inspiration to begin developing your own designs and manufacturing them. I'm really excited. I can't wait till we release this class to the public. I think you guys are really gonna like it. And I'm gonna end on a fun note. So who here has heard of Burning Man? Oh, y'all are missing out, man. Okay, so Burning Man is this festival that happens in the middle of the desert. I'm not selling it really well right now, but it's full of art installations, and even what people wear is art. And one of the, I guess, marquee signature displays is right here. It's called a Shroom and Lumen. It is a mushroom that changes shape when you step on this little contact pad right here. And so I had the opportunity to see a Shroom and Lumen without going to the desert for a week in Cincinnati. And so I dragged my family to the art museum. And I was so glad this was here and that my daughter could jump on it because I had just dragged her to an art museum for the weekend. And so the Shroom and Lumen is based on origami, which is often based on nature. And I just love how nature has influenced an art that has influenced a piece of art that, again, now resembles nature. I just think it's fascinating. And so these folds that you see here on the Shroom and Lumen look a lot like the folds that you would find on lily pads. So giant Amazon lily pads they're massive. They can be like 10 feet in diameter. A lot of people will see pictures of like babies sitting on them, which please don't do it. That's my legal disclaimer. Do not put your baby on a lily pad. But they're massive. And how do they deploy from being underwater up onto the surface of the water? And the way they do that is that leaf is really well folded. And as it's emerging onto the surface, it then opens up. That folding, that packing, it's not random. And it looks a lot like the Shroom and Lumen. So I want to thank you guys for paying attention today. It's really awesome to come share something that I think is super duper cool. And I know that this weekend is all about looking up into space and looking on a global scale. But I wanted to kind of remind you of the things that make our planet so unique and so marvelous and so amazing. So as we look up in the skies, I'm about to share the stage with Guire Sinclair, and he's going to talk to you about constellations. Constellations are like one of the very first forms of art that combined our skies and the things that we saw all around us. We took stories in our cultures and we wrote them with shapes that we found around us, and we wrote them by connecting the dots up in the night sky that we saw. And so in a way, it's an amazing form of biomimicry in itself. And Guire is going to talk about the Constellarium project. Just a little bit about Guire. He is my Huntsville Steamworks collaborator. He's the one who's bringing in that SolidWorks component on this project. He is a local engineer. He is an artist. He is one of the most patient teachers I have ever known. And he's just an all-around wonderful human being. And so with that, I'm going to say thank you. Thank you to Huntsville Steamworks for inviting me up here today, and to NASA Space Apps for giving this life scientist some time. And I hope you guys stay in touch. Feel free to send me an email, even if it's just to be like, that was really boring, you shouldn't have been there, or if it was something like a question that you had, I'm happy to answer it. Do we have any questions over here? Yes. Make the pictures of space? Like that really colorful one? Okay, so what you need is a tripod and a camera with a long exposure. You need a lens that you can focus manually, and then you have to go to a really, really dark place. Bryce Canyon National Park is one of the darkest places in the world. Go in the summer when the Milky Way's up, and just be really, really patient. Try different camera exposures. Don't go past 30 seconds, and you can capture some amazing images. Yes?
So, for example, I went to a museum and
You went to a museum?
so it was this thing where you like pet the fish, like the sharks and stuff.
Uh-huh.
And things like that. And so you said on the shark, like there's no like slime on the shark.
Yeah.
But there's slime like on the stingrays. And so how does it like not wash off?
Oh, that is such a great question. I couldn't have planned a better one. All right, so the question was, I petted the sharks weren't slimy, but then I pet the stingray and they were. How did the slime not wash off? That slime is actually a protein that can bind like a whole ton of water and it expands. It's very similar to the protein that's found in okra. So if you've ever had okra and you want to make gumbo and gets that really nice, I hate to call food slimy because then no one wants to eat it, but it gets that thickening texture. It's a protein and it's absolutely fascinating. That was a great question. Thank you. Yes, ma'am.
Oh, thank you. So when you said something about hiking and knocking down the spider webs or
You don't really knock them down. You more walk into them face first, and you do this thing. I don't like doing this thing. That's what my husband's for. Yeah.
Oh, well, never mind.
No, I can.
Well, like if you know, like if it's part of nature, then why do it, and why not just go around?
Well, that's the thing. I would totally go around a spider web if I could see it, but I really can't. And it's kind of the same problem that the birds are facing with our glass. They can't see it, and so they fly right into it. Now, obviously, if I walk into a spider web, the spider's probably going to be more sorry than I am, even though I am still feeling really sorry. But a bird could potentially die or get hurt, right? And so the spiders have actually developed a cue for birds. It reflects the UV light that's coming out from the sun, and the birds can actually see these threads in a particular pattern, and the birds recognize that as, hey, spider web, don't fly through it. I wish I could see it too, like amazing superpower right there. And so if we take those threads and we embed a similar technology into glass, the idea is then we now prevent birds from colliding into our windows. And so we are borrowing that function from the spider, applying it to a really human problem, windows, and hopefully saving some birds' lives.
So I have actually a super quick question about the shell. So was that a script that you did in SolidWorks, or was it a Python script that you got to experiment with on the side? Like, what was the process of actually generating that 3D model that you then got to print?
Okay, I love that you assumed I actually could do all that. There is a free app online. It is called a route coiler. You can Google it, and you can play with all of those different route parameters, and then you export a file. And that was the file I took to poor David at Huntsville Steamworks, who then looked at the file and was like, this is a shell of infinite thinness. I'm like, can we fix it? He's like, yes, you just push this button right there. And I'm like, wow. But yeah, that is totally freeware available online. Anyone can do it. Guire has actually built, is it Python? No, Java. So Guire has actually used Java to build a very similar app, and that's something that I think he can probably show you at some point too. And it's super awesome. And he actually sent me a video. I just didn't embed it because I was sleeping.
Excellent.
So yeah. Yeah.
You have a question? No?
I promise I will answer almost any question. All right. The Nautilus only took about 10 or 15 minutes.
Wow.
Yeah. And then the orange shell took less time. It had less filler in it. So, but yeah, super fun. You guys should go to Huntsville Steamworks and print your own shells. Yeah.
Any more questions?
All right.
Thank you.
All right, thanks.
Yeah, I think you're fine. Spoken like a true engineer. I found the thing online, and it seemed to do.
Yay, let's hear it. How amazing.
My life is amazing.
It is, isn't it? It's what happens when you become a PhD in biomedical engineering and you have this great interest. But one of my favorite things she said earlier was, I said, well, your husband's a rocket scientist and you're a PhD in biomedical engineering. What are your dinner conversations like? And what'd you say?
Who's taking our daughter to school tomorrow, and what will we watch on Netflix tonight?
See, life happens. Anyway, thank you so much. We're going to take a moment here and switch out the presentation, and then we're going to hear from Guire Sinclair. Thank you.
And thank y'all for coming out. We've gathered a bunch of like-minded people who want to build things and use their ingenuity. It makes me happy to be in a room of so many folks who are as excited as I am to change the world with tech. I've bribed you with a little bit of a visualization here that you can watch while I introduce myself. I'm a creator. I like to employ a blend of technology and art to create things like the visualization you're seeing right now. This is called the Hilbert curve. It's a space-filling curve, which means that as you let it iterate, it'll eventually fill the entire space. And it makes a pretty neat animation. A lot of my art is geometric or mathematical. And even when creating in traditional media, I like to activate my engineering knowledge to help my process. I hope that this mentality will prove useful for teams that are hacking together some programs during this weekend's challenge. Today, I'd like to share with you my love of the night sky and a project that I think you'll enjoy. For thousands of years, people all over the world looked up at these stars. They put their stories, their feelings, their mythology into the night sky. It became a touchstone, a place where the oral traditions of the world could look and see the same stories night after night, year after year, generation after generation. Cosmic dramas played out in the sky. Here's Orion, one of my favorite constellations, and something that really helps me see the ingenuity of the ancient people. Looking at some dots and connecting them with lines, they saw something like that. Their heroes and mythologies lived out in the sky above them. Does anybody have a birthday coming up in the next week, month? If you do, you might find this constellation interesting. We see this as Scorpio. And if you're, I think, born between the 23rd of October and 21st of March, correct me if you like astrology, this is your star sign. Some constellations, like these on the zodiac, come up every single year during the same time, and people key their lives to them. They create stories that go along with the things they see. And it's more than just a story. It's something that they use to influence themselves and collect their knowledge about what they thought would happen. Other cultures see them in other ways. If you saw Moana, you might recognize this from that movie as the fishhook of Maui. In this way, different cultures have different stories for the same stars in the same sky. This is the Andromeda Galaxy, the closest galaxy to ours. Even ancient people could have seen this in the night sky. It's visible without a telescope. Today, we can see it in so much more detail, and we can see things that they never even dreamed of. Our views of the universe have expanded over time with our technology and our interest. Each discovery tells us a little bit more about what we know and opens up so many doors and mysteries for things we have yet to discover. This is why it's so important for people to be involved in space today. We have to keep learning. We have to keep exploring. And we have to show people that it's not just NASA, it's not just these world space agencies that can be involved. The sky and the universe is for everyone. And we can all interact with it. And that's what inspired me to create this project I'm going to share with you now, called Constellarium.
essentially all of the constellations we know today were seen through ancient eyes. These are the stories of people of past lives, their feelings, their memories. What we want you guys to do is tell us your stories from your lives.
We want everyone to know that they can contribute. Submissions are open now. Make sure you get them in before Space Apps on October 18th. So the idea here was to create a tool where people could go online and tell us their own stories. The ancient people looked at the stars and over generations wrote down and talked about what they saw. This is a way for all of us to contribute to a new set of constellations and tell our own stories. This is what the empty night sky looks like, except for Uniform Resource Locatorus, my favorite constellation. This is where you go to visit that and contribute your own stories. And we'll have that again later if you want to join in. Now I'd like to take a few minutes and talk about some of the stuff we've received already. This is one of my favorites, the Dancing Woman. As you can see, a little jaunty night sky experience there. This guy's name is Enkidu. That's all I know about him. These are, by the way, these are real stuff we've received so far. Once you put yours in, we'll have so much more to show. This one has a very interesting story behind it. I may slaughter this pronunciation, but Panchajanya Shank was the holy conch of Lord Vishnu. This is a conch shell, kind of like what Helen was just talking about. And it dispelled the darkness and ignorance to bring forth the illumination of knowledge. This one was just submitted last week. This one's a flip phone. Very ancient. Yeah, we wanted some modern stuff, but I guess someone was still stuck in the olden days. This one, this one's a shout out from Space Apps Cleveland. If they're watching online, hey Space Apps Cleveland, this is the Space Pizza. And as you can read, someone was getting together, doing some planning for an event much like this one, and all they wanted was some pizza. Well, now they can look up in the night sky, and there's their pizza right there for them. Pizza was actually a common theme in some of these submissions. Here's a woman, I think, trying to grab a piece of pizza after putting together a presentation. Helen, was this you? Yeah. All right. Everybody wants some pizza. And some pie. Wouldn't it be great if the whole world was made of pie and if we had it everywhere? I'm not sure where the pie is in here, but whoever put it in, if you want to send me an email and tell me, and send me your favorite pie, that'll be great. This one's a dog and a fish or a fish. This one I thought was super interesting. The giant sky kiwi, and you can't see it right now, but it's walking around Polaris, which is the pole star, or the North Star. A lot of the constellations have stories that depend on how they move in the sky, not just where they are and what stars they're talking about, because in different seasons they would rise and fall. And because of that, people saw stories. They moved throughout the sky, they ran towards something, they ran away from something. And this great sky kiwi walks around and gobbles up all the stars. I thought that was a really interesting concept. This one is a lot of fun. Does anybody recognize this? It could be a spaceship from the stars. This is actually a flag. This is the Brazilian flag. This is from, I think, Space Apps Sao Paulo. So bom dia, if you're watching. Somebody spent, it looks like, quite a bit of time going through to make that flag. I thought that was great. There are some that, unfortunately, I could not show you. And I'll leave it at that. And there's so much more space up here. So again, this link is going to be up at the end of the show. And sometime when you're hacking this weekend, or if you have some time, want to show your friends, put your own stories into the night sky. We would love to see them. There's a whole world of people that all have their own experiences. And we don't have to care about the Greek mythology anymore, all right? We have our own. Next, I want to talk a little bit about the process of turning your idea for a program into a finished program while maintaining teamwork and just using this Constellarium program as a case study. The first is a concept. What do you want to build? In this case, all I knew was make art that was interactive. Use real-life data, so you're interacting with the real universe. And make it about space. For your ideas, maybe something's going to be similar. When you're hacking together a program this weekend, maybe some stuff will occur to you, maybe it won't. But the first thing you want to do, like in any project, is write down what it is you're trying to do. Next, you can make a list of features. Expand on your concept and write down the things that you need to do to make this happen, and then later the things that you want to do. This is a very, very small time window for y'all to create your programs. You only have 48 hours to hack it together. So I recommend doing all the needs first and then working on the wants as you can get there. The next thing is something I like to do whenever I'm working on a project of any kind, either an art engineering program or an art project. And this is draw it graphically. A lot of people in the engineering worlds that I live with do not like to draw things graphically. They want to write it down or not do any planning at all. When there's a short time horizon, like today and tomorrow, when you're trying to put something together in 48 hours, sometimes the instinct is to rush. Get it done, let's just start working, just start putting code together, because that's the only way it's going to get finished. From experience, and I think everybody will tell you this, a minute of planning now saves an hour of work at the end. So if you spend your time putting it down graphically, you might save yourself a little bit. This is a plan of the user experience of your program. When they jump into this, where they're going to start, where they're going to go, and what things are going to transition them between these states. This is a good way to make sure your user doesn't get stuck. I had an issue when I first created this program. I did not include this step, which means that you could go to the title screen, start drawing, click the save button, but if you wanted to go back, you couldn't. You're stuck. You'd have to reload the whole thing. So by drawing it out, I could see that I had made a state that was not reachable. You couldn't get back to the draw mode. That helps your user with their experience and helps you make sure that you can create a flow that makes sense when you're writing down your program. This is another example of something that would be a bad idea. If you want to include an instructions screen, you have a way to get to it, but no way to get back. By writing out your program in a visual way, you can make sure your user has the ability to navigate through it and that you have the ability to create it in a way that makes sense. You can always get more in-depth with your diagram here. You can include the functionality you want to do. You can include what the user inputs will do. For me, I knew that in the title screen, clicking and typing and dragging could have options for the user to do something with. But I only wanted clicking to move the screen around. When you're drawing, clicking can do different things, but typing does nothing. And in the end, typing inputs your words. This is how you can start fleshing out your program. Once you have an idea and you start getting into it more graphically, you can actually make it into your code. And from there, you can create the whole thing from just the basic sketch. And one of the things I like about this as an artist first and an engineer second is that it's like sketching. You first create just the main idea, and then you start to add details. And each time you go around, you add more and more details until you have a finished drawing. Programming and art can work in the exact same way. You have a concept, you decide what your features are going to be, you start to represent it in a sketch, and then you fill it out further. If you take one thing from this talk, it should be go to Constellarium and put your constellation in. If you take two things from this talk, it should be to do something that you're not familiar with. If you're an engineer and you don't like to draw things out, try it. Try and represent your ideas graphically. If you're an artist and you're used to just doing things as they come to you, having a natural flow, try to understand, define, and explain your process in a way that's very discrete, that has all your steps written down. If you can do that, it'll help your ability to teach someone else how to do it or to understand your own thinking when it comes time to do it again. When different types of processes interact, that's when innovation happens. And when you do things that you're not comfortable with, sometimes you get your best ideas. Hopefully, using a process like this will help teams develop their own programs throughout this weekend's competition. The last step is something that you can certainly try your best at, but no one has yet created a user that will do the things that you expect them to do when they use your program. Probably 70 to 80% of your work when you're doing something for production is making sure that you quote-unquote idiot-proof it. Now sometimes you, the designer, are the idiot. Oftentimes you, the designer, are the idiot. Do your best, test. Sometimes it won't be enough, sometimes it will. So I want to extend my greatest gratitude to all of you for being here, and to all the teams who have decided to come and try and share their interests and create something new with them. Hopefully, since you have a cross-cutting team of programmers and artists and creators and user experience designers, you can create something that is greater than the sum of all of your parts. And I wish the best of luck to everyone who's competing to create something throughout this weekend. Let's keep the conversation going. If you have interest in anything that you see this weekend or during this presentation, feel free to give me an email. And remember to go to this link and share your stories on the Constellarium program. We would love to see input from everybody.
Thank you.
Yeah.
So when all this is over, are you going to take all of the constellations that you've received and put them in the same image?
Not all of them.
Not. You were the one that gave the internet a pen. So.
That's true. Yeah, that was a mistake. Yes, there's an idea to put them all in one image and have a whole new night sky, send a letter to the International Astronomical Union, and make them accept our new constellations.
Hi, you knew me so well. How do you make those?
Yeah, so has anybody ever used a spirograph? That little yeah. It's a fun childhood toy that I played with and myself. These are some of the things that you could create with a spirograph if it were also a calculator and a monitor and some other things thrown in. But it's the same essential process. Now, when you use a spirograph, you're spinning something around, right? And you're creating a circle that looks continuous. These are actually created in a very similar way. I created them with code. And you're tracing a line around and only keeping certain points instead of the whole circle. That's the bare bones of it. And then animating it by changing the size of the spirograph and things like that. I can show you the program later if you want. Yes?
On an average, how much time do it take?
To do what?
To make it.
To make the Constellarium program you saw, or any program in general? Yeah. So, I mean, any program, it does change. The Constellarium, hey Google, make this guy an appointment for a haircut tomorrow. The Constellarium program, I would say probably took 2 or 3 weeks. It was a little bit longer than your production period for the hackathon is going to be. Part of that was, whenever you make something new, you like to learn. This was, for me, the first project I did on web. So that was the big thing for me, was I was trying to learn how to put something on the internet and get a bunch of people to help. And, like I said in my slides, most of that is, at the end, trying to make sure that it's not broken. There's a lot of bugs. And you can only get so many of them out, but a lot of it was trying to fix some of those things that I had forgotten to take out when I made it. So thank you.
So what technologies did you use to build the Constellarium project?
Sure.
And is it open source?
You can indeed find the code online. If you go to that link right there and view the page source, you can find that code. I'm happy to email it to you if you want to ask for it in email as well. So I guess that means it's open source. And I used Java to build it, and a Java variant called processing, which is designed for quick visual programming. So it's got a lot of stuff that makes it easier to draw lines and stuff on the screen. In addition, some of the web stuff was done with PHP. If you are interested in programming, you'll know what some of these words mean. Otherwise, it was done with code.
In order to make the star constellation things, like, do you have to have a very imaginative mindset? Like, you have to think outside of the box in order to make something.
I think if you go to that website and put your constellation in, you could just tell a story about your life. That's what the old constellations were. It was just things that they thought about, stories they told, and some stuff they saw in their daily lives. If you want to just share something that's important to you, that's all it takes. All right.
Any more questions? All right, give him a hand.
Thank you all very much.
You finished, choir?
What's that?
You finished?
I think so, yes.
That's awesome, okay? This is really, I mean, these last two sessions talking about the importance of science and then including art into it for STEAM. You guys sitting on the front row right here, and you folks all around the world have got to realize you really can mash a lot of different ideas and thought processes in to really the betterment of mankind. So thank you so much. This is fascinating.
And thank you all, and NASA and UAH and all the other sponsors. All right, I'll get off the stage.
Thanks, choir. Appreciate it. So now it's time for lunch. And yay. And I understand probably the best place to go is the Charger Union, which is not too far away on Jordan Lane and University Drive. Or pull out your Apple Maps or your Google Maps or your Maps and figure out what is the best place you want to go. But we've got about an hour and 15 minutes. So enjoy your time. Thank you all so much. And say hey to the rest of the world, y'all.
5.
They're going to run the pole mics, and then we'll have to take those on you guys, just so we've got some good sound for the live stream. So I'm going to put the 2 extra that I have.
Literally just say anything.
You know you can do that with Mr. Expert.
Now, are you True 57 or are you?
We show that the battery charge discharge unit.
Lab, okay, Lab 87.
환영합니다.
Welcome Bay International Space Apps Challenge.
Добро пожаловать в международные космические приложения.
Space Apps के स्वागत है. International Space Apps Challenge में आपका स्वागत है.
Visualízate sobre el mismo tratando de esquemate.
Ласково просим до международных космических программ.
欢迎参加国际太空应用程式竞赛。Bienvenue aux applications de l'espace.
Волепатаро Space Apps.
Добро пожаловать в международный Space App Challenge.
आपको International Space Application Challenge मुबारक हो। Welcome people to International Space Apps Challenge.
Veio convidamos para a International Space App Challenge.
Bienvenidos al Reto Internacional Space Apps.
Instrumentos canastis, salve.
أهلا وسهلا في International Space Apps Challenge.
Herzlich willkommen zu den internationalen Space Apps Wettbewerb.
Selamat datang ke cabaran antarabangsa Space Apps.
Welcome to Apps.
International Space Apps Challenge. Yokoso.
We will nog willkommen heten to Space Apps Challenge. To learn more, go to spaceappschallenge.org and join the conversation at #SpaceApps.
Good afternoon. All right, it's time to wake up after that lunchtime nap, right? Okay, how incredible is this? Everybody here, I want to say hello to the 18,000 people around this great planet that are joining in International NASA Space Apps Day. What an amazing group, and I think that video has really highlighted that. Now we're going to hear from Dr. Bill Marks, who is the VP and Chief Technology Officer for Intuitive. And I just wanted to say thank you to you and your company for the great work and the great support you provide, not only Urban Engine, but also the Space Apps Challenge. So, Dr. Bill Marks, let's hear it for him. Thank you so much.
Thank you.
Good afternoon, everyone. My name is Bill Marks, and I'm the Chief Technology Officer at Intuitive Research and Technology Corporation. Intuitive is an aerospace, professional engineering, and analysis firm here in Huntsville, and we've been supporting the Urban Engine and the Space Apps Challenge since 2017. We proudly support the Urban Engine and this particular event because we believe in their mission of propelling ideas forward and promoting the growth of North Alabama's economy and space initiatives. Since its inception, the NASA Space Apps Challenge has become the world's largest global hackathon, engaging thousands of people each year across the globe. This 48-hour global hackathon was designed to work with NASA in building innovative solutions for challenges we face on Earth and in space using open source data. This year, because Huntsville is a main stage city, we can show the world what the Rocket City is made of. We're made of innovators, entrepreneurs, creators, visionaries, inventors, engineers, developers, hackers, problem solvers, and collaborators. This weekend, teams from North Alabama and surrounding states will come together through their passion for making a difference to develop real solutions for real challenges of interest to NASA. Intuitive is honored to be a 2019 Space Apps Challenge presenting sponsor this year. It's been exciting to watch the growth and evolution of this event since the first Huntsville Challenge in 2017. As a judge in the first Huntsville Challenge, I can say that our participants of all ages and all backgrounds are smart, outstanding individuals and teams with incredible determination and drive. Like the Urban Engine, Intuitive understands and recognizes the importance of STEM and STEAM for the North Alabama area. That's why we support the next generation of thinkers and problem solvers through events like this. Thanks for joining us today. I hope you enjoy the next 48 hours.
Dr. Marks, thank you so much. And thank you again for all that you and your company does to make a huge, huge impact in both Urban Engine and also Space Apps Challenge. Now, no one can sit quietly for this next improv, okay? We're gonna do an improvisation of a moon mission. And to show us and teach us about improv is Troop 87 from the Fantasy Playhouse. Come on. Yeah, let's hear it. So what they're gonna do is teach us a little bit about improv, and then it's really about team building, isn't it?
Yes.
It is. So we're gonna teach you, so you're gonna take us to the moon.
Yes.
Great, okay, let's go.
All right, so improv is acting without a script or props or set. So you're making everything up on the fly, which we do all the time in everyday life whenever we have a conversation, right? Hello, Dominic.
Hello, how are you?
I'm great. How are you doing?
Good.
Awesome. So I listened to him and he listened to me and we had a conversation. Improv. The second rule of improv is you have to say yes and. So you take someone's idea, you say, yes, okay, I hear your idea, and I'm going to add to it. So to demonstrate these two rules, listen and yes and, we're going to play something called Mr. Expert. Are you guys ready?
Yes. Yes.
Get your two chairs. Now, Mr. Expert, we've got experts who are experts on anything and everything. We could ask them all sorts of questions, and they would have no problem answering it. So when I ask the question, and I'm going to ask you to pick one of these cards. They don't know what we're asking them, because it's improv. Pick one of these cards. This one? This one right here. Okay, all right. So I'm going to ask the question, then I'm going to snap, and Bree here is going to start talking, explaining all of the answers for this question. Then I'm going to snap again. She's got to stop mid-sentence or mid-word, and Dominic will take over. And eventually, once this question's answered, we'll answer one more, and Davis will step in. Okay, are you ready?
Yes. Yes.
All right, so the question is, how can we map everything on Earth? You got that? How can we map everything on Earth? Good.
Well, we can be able to travel across the world with all these different
cameras, and we just lean out of whatever we're traveling in and snap
pictures of every little detail so that we can finally
map the entire world. Thank you.
All right, good job. Switch out.
Sorry.
Would you like to answer or pick a question? All right. You guys ready? When looking at a night sky, how can we tell if we're looking at a star or a satellite? Are you ready, Dominic? You sure?
Yes. Well, you see, satellites are usually in
motion around the Earth. And another good sign is that usually they have
antennae. So you need to use a telescope to
look really closely, and maybe you can see
if it's a star or a satellite.
Light.
All right, let's do one more. I'm going to pick this one for you. You guys ready?
Yes.
How can we bring the internet to desert islands? Out in the ocean, surrounded by nothing but water. You ready?
All right, so you just take a bunch of smart people and
An Eiffel Tower for us to build.
using computers. We just get hammers, nails, and computers, and we stack them on top of each other.
So that we can make a large skyscraping
tower for everyone to use.
All right, good job.
I've got one more improv I want you to do.
Okay.
Okay? This is my improv for you.
Yes, sir.
I want you to improv saying hello to 18,000 people turning in to Space Apps Challenge.
That's a difficult one.
Hello,
everyone.
How's it going? All right.
Excellent.
Hope you all do
Let's hear it for Troop 87, the Fantasy Playhouse. Thank you all so much. So now I would say we're at the rock star part of this, but it's more like rocket stars. Babak Ferdoso is quite an amazing guy. He came here all the way from the Jet Propulsion Labs from NASA to join us for Space Apps Challenge today. And he is kind of renowned for a lot of things. His brilliance, MIT, all the things he has done. But it was President Obama that kind of put him on the, shall we say, the map. I'll let you figure out what President Obama said to him. But didn't you also join him for the State of the Union address? Okay. Give it up for the rocket star and the team he's going to introduce now to improv a mission to the moon. Bye-bye.
Hi, guys. He failed to mention, of course, I think one of my more important contributions was I was in Sharknado 3, and I survived, so big deal. If you guys ever encounter Sharknadoes, please, you're welcome to contact me. I'm so excited for this panel today. It's going to be a really awesome insight into sort of how engineers approach problems, and I hope all of you guys will learn, those of you in the room with us, those of you guys streaming this on the web, of how engineers approach problems, and kind of getting a sense of the thought process and the way we sort of do things. So I'm going to introduce a few folks. We're going to bring them out. We're going to ask them a couple questions. So first is Sam Watley from ULA, United Launch Alliance. Welcome. All right. What got you into space?
So what got me into space, is my mic on?
It's quiet, a little quiet, yeah.
So what got me into space was I actually met an astronaut when I was in middle school at an event very similar to this, and just got totally hooked and kind of delved into it. And I've always been really good and fortunate in the math and sciences, and just kind of pursued my dreams and passions, and here I am today.
Awesome. All right, thank you very much. Well, we'll keep coming out. Have a seat, and we're gonna, yeah. So from Blue Origin, Keith Eaton. Welcome. All right, what was your favorite class in high school?
Physics.
Physics? What about it in particular?
Oh, just the application of what we were learning. Because math to me is a little abstract, but when you actually get into the heart of it and actually understand the application, I think that's pretty awesome.
Absolutely, totally great. All right.
Cool, thanks.
Let's see, next, Justin Rowe from NASA. All right, Justin, welcome. Favorite anime series? Oh, it's fine. You know, favorite sci-fi movie?
I mean, you got to go with the original Star Wars trilogy, right?
Okay. What about it? Like, Yeah, what makes you love it so much?
I mean, as long as you suspend disbelief enough, I don't know, it's the classic hero story. It's the, young kid, just a standard, normal kid that gets to go on a huge adventure and save the world.
Awesome, yeah. Did it inspire you to work at NASA at all?
Sure.
Yeah, just kind of a little bit? All right, thanks, welcome. All right, I guess I don't know what your representation is because I didn't write it here. Adele, Luda, come on down and you can describe to us who you're representing today.
I'm a Presidential Innovation Fellow here from Washington, D.C.
Awesome. All right, I guess for you, I'd like to ask you, you mentioned something earlier, so I'm very curious about it. What excites you about sort of space exploration?
I think, did I give you the answer?
A little bit, but let's keep, don't worry.
No, I think definitely both aspects of both the exploration, but also conservation for the Earth and being able to heal such a gem of a planet that we have. And I think those answers are going to be out there. And if we explore, we'll be able to find a way to do that.
That was indeed the answer you gave me earlier, so perfect. Thank you so much. Sure. All right, from Northrop Grumman, Dan Miranda. All right, which celebrity do you look like the most, and why?
That is a tough one. I actually get mistaken for Mark Cuban all the time. I have been stopped in airports. I have had people argue with me. No, I am not Mark Cuban, I promise. I wish I was. I wish I was a billionaire, but not quite.
Okay. So just on that note, though, if you were to invest in one sci-fi idea, what would it be?
One sci-fi. It's got to be a lightsaber, right?
Lightsaber? All right, yeah.
Everybody wants a
lot of Star Wars
lightsaber.
fans here. That's fine. I'm a Trekkie myself, so it's okay. No, it's all right. That's all right. Let's go. Have a seat. All right, also from NASA, welcome Reggie Alexander. All right, welcome. We didn't get a chance to talk before this, so this is going to be a wild guess. Okay, let me see. What I want to ask you. What book did you read that most made you wish you were part of that world?
Oh my God. That is a very difficult question.
Okay. You just tell me, what about a book that you read recently that you loved and why?
Well, I'm a big fan of, gosh, I can't even think of his name. He wrote A Time to Kill, some legal thrillers.
Okay.
Like legal thrillers. So, what's that? John Grisham. Thank you. Yeah.
John Grisham, for those of you listening. Yeah.
Yeah, so the last one I read, or several of the ones that I read, are Ford County, of course, A Time to Kill, things like that. And they're very interesting life stories and very difficult stories for the hero to extract himself from. So I always enjoyed those.
Do you put yourself in that role sometimes?
Absolutely.
Okay.
Absolutely.
I like it.
Thank you.
All right, and welcome a good friend of mine to the stage, Dustin Sandlin from Smarter Every Day, hometown hero. I don't know, is that right? I just want you actually, I don't have a question for you. I mostly just want you to tell the audience how great I am for a few.
Bob Eck is amazing. He's fantastic, and he puts things on Mars just for fun.
No, I'll be curious. I remember watching some of your earlier videos, but I don't know that I've ever seen you sort of talk about what made you want to go into sort of, because I know you're a super sharp guy, but what made you want to start creating stuff and explaining things, or just even poking around at it yourself?
I just like to learn stuff and ask questions. And I just, YouTube was invented right about the time that I learned how to make videos. And so I just went to smart people and asked them questions, and then I learn on video. Yeah. It's that simple.
That's basically what I'm going to get to do today, so I'm excited.
Awesome. Yeah, excited about it.
Okay, so we also have an artist in residence in the back there. I don't think we have anything displayed, but Dustin Timberlake back there, who's going to be sort of sketching out, there it is, we got a hello. Who's going to be sketching out some of the ideas that we draw, or that we come up with here on the panel today. And so we sort of have an architecture here. The idea is, I want to make sure I get it correct. It's a 12-person lunar colony in the not too distant future. The panelists have been told this information, but we were deliberately told not to sort of think about it too much in advance. I know, listen, there were people on the phone call who were like, let me ask 20 other questions because they want to solve the problem. The goal here isn't obviously to solve the problem. The goal here is to sort of get the kind of the thought process out there. Everybody here has sort of different backgrounds and different expertise, and we're all going to try to build on each other's ideas. So there's no wrong ideas. I'll tell you just a quick story from from my experience on Curiosity, one of the ways that we landed that rover, which was this kind of this wild, this jetpack helicopter sort of scheme, from which we lowered the rover to the surface of Mars. That came out of a sort of a brainstorming session in which we were allowed to all sort of propose ideas, and no idea was considered incorrect at that time. We basically put it all on the board, and then afterwards we did our due diligence to sort of evaluate each of the ideas for their merit and their costs, and basically how do we really go about doing them. And so that's kind of what I want to see here today is, I think we're going to try to hone in on a single idea, but I'd love for, of course, all the panelists to not, I know that some things might not be necessarily technically that feasible today, but let's talk about how we would make them feasible to sort of solve problems in real time together rather than sort of say, well, that's not how I would do it. So that's kind of going to be the goal. I don't have a great idea, so let's sort of start quickly around the room. Let's just get everybody's expertise areas real fast, and then we can sort of throw ideas to folks. We'll start with you, Sam. Just kind of go in.
So I'm a propulsion systems design engineer at United Launch Alliance. I've been working propulsion systems for about 3 years now on the Atlas V, Delta IV, and Vulcan rockets. We've launched over 136 missions with perfect mission success. So today I hope that I can bring some cutting-edge propulsion technologies to this discussion.
Great. Keith?
So I am an aerospace engineer, but systems engineer by trade. I work on the test stand 4670 now that Blue Origin is leasing from Marshall. So we're trying to get things up and running for the engines that we're going to bring over there and get some rocket firings back into Huntsville. So I'll bring some test stand perspective, some systems engineering, how things connect, how pieces interface.
Yeah, very practical, hands-on. All right, thanks.
I'm Justin Rowe. I work as a concept designer at NASA Marshall. So my day-to-day job is kind of a lot along this method. Get kind of fast turnaround on what the project managers want and what they want, or when they want it by, what we have to do in order to get there, how it all goes together, and we put together a mission plan.
And you sort of assemble a team, I assume, of experts as well. Yeah,
absolutely.
All right. Adele?
Adele Luda. So my core background is in physics. Right now I am working to help the government solve problems at a national scale, but in a previous life, which is probably why I'm on this panel, I was an astronaut instructor and flight controller at Johnson Space Flight Center for the spacewalks for the EVAs. So.
Yeah, someone who works in robotics, the humans are a lot more difficult to work with than our robots are. Squishy, they don't survive environments as well. Yeah.
So I work for Northrop Grumman. Most of my aerospace career has been with solid rocket motors, so I bring smoke and fire, the really cool stuff.
Awesome. Reggie?
Yeah, I have I had a varied career. I'm a manager now, but I spent the early part of my career doing conceptual design and feasibility studies. I was a thermal analyst, and so we did a lot of obviously thermal design and survivability of spacecraft, launch vehicles, et cetera. Later on, we led teams to do conceptual designs for launch vehicles, in-space systems, habitats, et cetera. So across the board, what we would need for a NASA mission.
Awesome. Destin?
So I'm an aerospace engineer, started off as a mechanical engineer, but I'm a father of 4. And so what I would like to bring to the panel is the ability for us to get along as we're on this, as we're hanging out here in this habitat.
Awesome. All right. I'm going to start, let's start with sort of, I would assume that sort of the fundamentals. We've got people involved. So there's some aspect of resources and all the things that associate with that. I'm not super familiar with this, so Adele, maybe you can give us like a quick overview of what are some of the things that people might need.
Oh, well, I mean, definitely if you were listening this morning, right, we need food, we need, pressure, air to breathe. We're also going to need some form of entertainment, right? So I think we were told 2 years there. So if you think about what they're going to listen to, if you saw The Martian, he only had limited music. So definitely music and what they're going to watch together. I think that's going to be really important. So they'll probably have some kind of maybe group area where they can watch movies together or entertain together or play games together, because that's going to be really important there.
And coffee, of course. Dustin, as a father, well, I don't think we're going to have kids necessarily on board, but...
Yeah, but we all, like I said earlier, we are kids deep down, but I think the challenge... So are we talking about on the trip to this habitat, or are we already at the habitat?
It's a pretty short trip, so I think it's building that infrastructure and then sort of what it looks like to live there for a couple of years.
Gotcha.
Yeah.
Okay. So the question specifically is...
Like what sort of, you're just talking about people, the people part of this. Like, it's one of the other things that people might...
You need to be able to chill out alone by yourself. I think you need to isolate yourself so that you can recharge yourself and not be on top. Like, Reggie's going to get tired of me after a while.
Absolutely not.
Yeah, so we need some solitary time, and we also need the ability to, like you said, do things together, but it needs to be structured, I think.
Yeah. So what I'm hearing is sort of like there's some, obviously the core things that we need to survive, the air, the water, the foods, things like that. And I think we're hitting on entertainment, private spaces as well.
Can I add one more?
Oh, please, yeah.
I think we want to give them a purpose, right?
Okay,
They need
absolutely.
something productive to do when they're on the move for 2 years. So give them a science project to work on, give them an assembly project, give them something to have purpose for what they're doing.
Do you want to try to give us one of those right now? Like, what about what's a good sense of
I think
purpose?
figuring out how to use the resources on the moon to do productive things to get us further into space.
So this is like what we mentioned a little bit in the earlier time, the in situ resource utilization.
Absolutely.
And then kind of building maybe as looking forward to future infrastructure as well. I think that's a pretty good goal. Everybody's sort of on the same page with that one? Okay.
And if that can work into a bigger picture mission, maybe we can all come to terms on like an objective of the mission, right?
Go for it.
Oh. Right, signed up for that. Well.
Walked right in.
I mean, I'm all about exploratory missions.
Okay.
So can we say that we have sent rovers in already and that the people are here and
I think that's a good,
established a good spot, right?
Okay.
Okay.
So I think we could say there's probably been some like precursor missions, certainly some robotic precursor missions. Probably, I don't want to jump ahead, but let's assume that people are going to the moon. It's not like we're not going to start out with a 2-year mission for the very first time. So I think that's a fair assumption to make. So okay, you got some base stuff there.
I think to build on that, one thing that would be really exciting to see is, right now the EVAs are 2 people, right? But in the future, there's nothing to say that you can't have a rover coming along with you. You can't have, things that are flying ahead to make sure stuff's safe or coming back bringing information. So as we do that exploration, I think you're going to see that team expand out really naturally.
So let's just go ahead.
Well, so there's a couple ways that we can do that too. Back in the toward the end of the Apollo era, when the programs were being canceled and pulled back, the canceled programs were actually to land a small pressurized rover that was specifically outfitted as a science rover, so that crews could go out in shirt sleeve environment and basically drive this pressurized RV for a week at a time across the lunar surface.
And you're saying we could bring it out of mothballs?
We could. I mean, it's sitting over at Space and Rocket Center.
There you go.
Give it a tune-up and put it on top of one of these launch rockets, right?
So I like that. So we have some sort of idea. I mean, we've got some past precedents, of course, which is, I think, like a lot of times you'll see engineers try to utilize what's already in our toolkit, right? Let's not reinvent everything all over each time. And so, like, working on the Mars missions, right? You see our rovers sort of fall like an evolutionary path of growth. So I think that's a great example. We build off some of the legacy stuff that we have. We're talking about a lot of stuff here, and we got a couple propulsion folks. Let's talk about how we would get it down to the lunar surface, because that's a big part of the challenge.
Okay. So one of the things that we might could do is we could have, currently the lunar surface modules use ion propulsion. That might be a way. We could use some type of solid fuel propulsion system to get it to the ground, or liquid fuel propulsion, right? There's different types of propellants that we could use. I think a liquid fuel propulsion is probably maybe the way we should go, because solid fuel, it's once you light it, you really can't stop it, and it's going to go, right? And if you can find a way to keep your liquid propellants at the cryogenic temperatures that are required for long duration space flights, your opportunities to travel multiple times across different places of the moon would be reached in that sort of mindset.
So what I'm getting at a little bit is like a little bit of you're talking about a hub concept, right? Where this sort of base is the starting place for operations, and maybe there's the hopping across the lunar surface or doing other things to sort of explore. We're talking about a buggy as well. We're talking about some robotic explorers kind of as part of this. You mentioned ion engines. I don't know if everybody's familiar. I don't know if you want to give a super short background. I wouldn't have thought that they were applicable in the lunar environment, but
Well, so what I kind of had in mind there is kind of like this cislunar environment where...
Well, just give us a quick background on ion engines first, and then hop in. Yeah.
So basically you just take ionized particles, right, and you energize them and then eject them out of your engine, and that every action has an equal and opposite reaction, right? And so those particles being shot out the back of the engine give you your propulsion. And so if you can harness some of the resources that are on the moon, you could energize those particles, the water, ice, or anything of that nature, and ionize those particles. And use that.
And I think actually the big advantage they often provide is higher efficiency.
Correct.
Right. So that's one of the reasons why we certainly use them in a lot of the deep space missions. Is when we don't need to get off the high gravity environment of the Earth, they work very well for us. Okay, so I kind of hear it. Oh, doesn't even. Oh, sorry. I thought I was like, oh, he's got it. All right. So I just kind of going back. So we want to land a bunch of stuff, not just one thing. So you sort of have a kind of an engine architecture, sort of a liquid propulsion engine. What sort of size of stuff do you think we could carry down to the lunar surface? Like, how much at a time are we talking about here? Because is it going to be hundreds of missions? Is it going to be tens of missions?
My thoughts would be hundreds, maybe a little bit much, but certainly tens of missions would likely be required to do it. I mean, you're going to be carrying, if you're indeed going to be having 12 people, they're going to need lots of stuff to support them. So you're going to need fairly large habitat items, and power systems and systems that will enable you to maybe capture some of the materials on the lunar surface to then turn those into other materials that you might use for drinking water, for energy possibly, who knows. But while you're there, you're going to have to do some exploring and have enough systems to enable you to create that life that you want to live there, or the manner of living.
So you bring up two really interesting things. One is, we haven't picked a location yet for our lunar operations. There's pros and cons to various locations, resources being one of them, and then of course the ease of landing things at those sites is also another challenge, and of course the thermal environments and everything that you see at all those. Does anybody have a good suggestion? We can just start with one and we'll sort of work with that idea. Anybody have a preferred? I could do a vote. We could just raise your hands. We could do, let's say, South Pole, equatorial are our two options. We want to do South Pole first? Raise hand, show of hands.
Let's do it.
All right. And that was pretty unanimous. I don't feel like that. We don't have to worry. Okay.
You gave us the option.
I did give you the option.
Made it easy on us.
Well, it's easier, right? But there's a cost associated with trajectories that get you to the South Pole. So let's.
And also power.
That's right. So let's talk about. So yeah, you want to explain some of the pros and cons of?
Sure.
Of that?
So on the South Pole, the way that the Earth and the Sun and the Moon interact, the Moon will basically go through a wobble period. It's called a precession. And on the South Pole of the Moon, that means that you either get a whole bunch of sunlight for long periods of time and very short periods of nighttime, or you can get long periods of nighttime with very short periods of sunlight. That is a very big, significant difference in the thermal environment. You're looking at the difference between negative 250 degrees Fahrenheit and positive 250 degrees Fahrenheit. And designing for that can be a very, very big challenge, especially when you have radiators and equipment that's creating energy, heat energy that has to be dissipated, and you have the metabolic energy from the 12 crew, as well as the power required in order to be able to do things like ISRU, being able to take lunar ice and turn it into water, for being able to even take it further and turn it into rocket fuel, oxygen and hydrogen. So the power is going to be one of the biggest limiting opportunities there.
I mean, but it would be anywhere, right? I mean, generally speaking, you can pick locations. Sure. So we also, right, the resources, generally speaking, have been in the permanently shadowed part of the lunar craters, which is, right. Now, would you kind of how close would you try to put your base there? Because putting it in there would, of course, mean almost no power.
Right. So it depends on what kind of power you want to be able to use. If you're looking at using this as an opportunity to prove hardware before going to a further exploration mission like to Mars, then you're looking at your two basic options are going to be nuclear power, or you're going to be using solar power. The problem with solar power, in my opinion, is because there are those periods of darkness. You have to have batteries in order to store the sunlight energy for when you're in the darkness. And the peaks, the points that you get the most solar energy, limit you to only 3 or 4 different landing sites for being able to do a buildup. You basically have to go on the near mountain tops right next to the deep craters in order to be able to do it that way.
So would that be your proposal? Go ahead. Sorry.
Well, I was going to actually build off of that. So I think instead of looking at that as a disadvantage, I would look at that as an advantage in the fact that they could live somewhere and we could have testing like a solar panel farm with different types of solar panels that maybe that energy does go towards something else, right? So it's another module, and they go and they visit and they check on it, and it doesn't all have to be in one location. Ideally, it's not, right? Because if you put all your eggs in one basket in one location, that could be kind of dangerous.
So again, for the sake of this argument, let's try. Let's say we're going to put it on sort of on one of the steeper walls of a crater. Does that seem like a reasonable assessment? Sure. Near, let's say, I don't know, Cabeus crater. I don't know, one of the craters with some resources in it. What we hope is largely water ice. I mean, we know there's a lot of water ice there. There may be some other stuff in there. But okay, so that's a pretty good assessment. We talked about now tens of possible missions. Give me just a quick sense of what do you think are the key missions that have to happen, and how much would you do to sort of attempt in parallel versus would you try to serialize, meaning would you send a bunch of precursor missions over time and then send humans last, or would you sort of opt for, well, we got to launch a bunch of stuff at once?
Yeah, I would suggest you send several precursor missions. Obviously, you want to scope out the site, send some missions that can overfly and understand, or even land and understand what is there, what the resources are, might be, but how difficult the terrain is to navigate so that you can start prepping for that. And then later on, maybe you would send some other missions, other craft that could start prepping, maybe landing locations for your other spacecraft, doing some things such as that, and then bring in your power systems, because I think you want to have everything fairly well in place for when you humans get there, because we tend to like to breathe and eat and be able to move. And so getting there with very little infrastructure could be very difficult.
So it's an interesting trade-off, right? Because we're talking about potentially robots either using telepresence or something like that, right? And with the moon, like the Soviet Union demonstrated that you can operate a rover on the lunar surface with the lag time. There's a couple second lag time between us and the moon. But you can reasonably operate one with a human in the loop. But the con is, right, robots cost more money if you want to have them prefab, for example, housing or structures for you. Where do you guys sort of weigh in on those trades? How do you sort of evaluate a trade like that in your everyday? It doesn't have to be that specific trade, although we're obviously going to try to answer that one. But I'm just curious. Anybody of you guys sort of like have?
Well, I have a question about our habitats that we're making here. So it's my understanding that we're here on the Earth and we're shielded from radiation from space, right? But once we're hanging out on the moon, we're going to have issues with that, right? So what do we do about that? We have to build something into our habitats. So what do we do? Are we piling rocks on top of ourselves? Are we using water to shield ourselves? What are we doing for that?
Lava tubes.
Yeah. No, that's great.
What is it? Well, I was just saying lava tubes, right? So, I mean, we've got these built-in structures on the moon that are basically doorways to underground tunnels that provide this existing infrastructure. That's one option anyway. We're talking about trades.
Yeah. So I mean, right, that we start encountering the issue, like, can you find a lava tube on a wall of a crater that is also near all the resources?
Can you tell me about lava tubes, because I want to draw that.
Oh, okay, let's go into lava tubes. Nature's skylights, as they call them. So yeah, I mean, you have these collapsed lava tubes from the prior lava flow on the moon, and right there's essentially these holes that form in the top of them, right? And they're larger on the moon. One of the advantages compared to the Earth lava tubes, which you can see pictures of here on Earth, because of the lower gravity environment. So these things can form somewhat larger than on Earth, but they essentially look like large caverns with a giant skylight. So right, one proposed mission architecture, and this is for Mars as well, is you would cover that up and you effectively have a nice sort of enclosed environment that you can kind of operate tolerable loss of things. How do you guys feel about those?
Yeah, I mean, I think it's very viable. I think to build on that, right? Nobody's building skyscrapers or even tunnels overnight. So you could have crew that go for a shorter period of time that are, scouting this out and maybe even stabilizing or checking out different things, kind of like civil engineering on the moon. And then you have crews that are eventually able to stay 2 years because we've got all these different types of options and features for them. So, you have to really look at it as like a long-term construction project, really.
Yeah. You talk about building test stands. Go ahead.
I was just going to ask if you could design a robot that could do like a snowblower type thing. You just drive it across the desert and blow regolith onto the...
I mean, the issue with the blowing, right, of course, is you want an atmosphere to blow things. Now, there are, like, some sort of planetary stuff. There's a planetary vacuum.
We're going to fling it.
That's right. But, yeah, I mean, you're right. You could just, right, it'll just be like a snowmobile where the treads are just shooting it out behind us. So I'm kind of hit at the testing, because this starts getting into really interesting things. A lot of the stuff we're talking about involves some sort of test program here on Earth, and then the trades off between these very complex sort of engineering undertakings. How do you sort of approach a problem like that? How often does the ability to test certain things, play into the decision of what you're building?
Yeah, that's a great question. So you can start with the launch vehicle, right? So we have to figure out a way to ascend and get up there in the first place. So testing of that is kind of where I live, and the engines specifically. So it takes a lot. It takes a lot of testing, and it takes a lot of of understanding the environment, or simulating and analyzing the environment that you expect to see up there, because it's not always available to you, right? You're not always able to test in vacuum as you expect, to fly in. So that's just for the vehicle. When you're talking about infrastructure on an environment that you've never, you can't really simulate here. yeah, I don't know. I think it's a lot of trades. It's a lot of concept of operations and looking at a lot of different pieces that play into the puzzle, right? So we haven't really talked about communications. I'm looking at this because I'm like, this is
that's fascinating.
We haven't talked about communications yet, but I think that's going to be a huge piece of this, because if we have people there and we have infrastructure and we have a site established, we're going to need a way to talk to each other and talk to folks who are en route and talk to folks who are on Earth, right?
Yeah.
So just pieces to think
All right,
about.
so yeah, I think this is good. So we kind of iterating, I think, a lot, obviously, on the resources. And we talked about the very, maybe more obvious ones, about the living conditions and things like that. But you're right, right? So let's talk about the larger stuff. So there's telecommunication orbiters. There's maybe reconnaissance missions as well, right? One of the things that we sort of talked about. What is kind of the gamut? Do other people have other kind of concepts for maybe other infrastructure that we haven't sort of discussed so far?
So I don't really know if I can answer that, but I was going to say in the near future, there's going to be a lot of launch providers out there in the USA and across the world, and so why not take all of those different providers and test different things out at the same time, right? And I think you get to your end goal a lot faster in that regard. So I'm just going to kind of add that.
And to that point, I mean, right, we also haven't discussed, I would assume this is going to be a multinational, international collaboration sort of thing. How many of you guys have had sort of experience working in that domain? Yeah. So let's throw it to you, Dustin. What sort of challenges sort of await people when you talk about people from different backgrounds and different, maybe even sometimes different technologies as well?
And languages.
Yeah.
Yeah, you have to be able to speak to each other and communicate. And another issue is units, or even the wall sockets. For example, the wall sockets here are different than they are in Europe or in South America. So we're going to have some type of standardization for these tens of spacecraft that Reggie's sending up there. Reggie's going to have to tell us what our standards are for each one, so that when they get there, we can all mate our ductwork together, or our power cables will plug in, so that if somebody gets low on water, we can go plug in our port and we can fill them up or something like that. So, Reggie, you got a big job ahead of you there, buddy.
Well, and that ties in actually, I mean, to what we're, right, the apps challenge as well, right? I mean, people are going to be working on different parts of things. You've got to make sure they all play nicely together at the end of the day, right, to make something much bigger than the individual components work. So it's
to kind of get to that, that's one of the bigger challenges in anything, is when you have all of these varied systems. Now they have to all play together, and Keith mentioned systems engineering, and so it's a kind of a boring term, but man, it is one of the most...
I take offense as a systems engineer.
That's me too, but that is one of the more difficult things, right, is you have to make everything play together, which means the interfaces, whether it be communications, whether it be how things plug together, whether it be how they just simply fit together physically, are incredibly important.
Yeah. So I just want to do a quick recap just for a couple of minutes here of what we have so far, because I think it's starting to add up to quite a bit of stuff, right? We just talked about, but at first it just felt like a little house for 12 people, and now we're talking about a much larger sort of system. So we've got communication infrastructure, we've got power systems, we've got multiple launch vehicles, landing, descent vehicles as well. We've got a bunch of missions that are sort of either pre-delivery of some critical resources and or the in-situ resource utilization that we talked about as well, so using the resources that are already there. Am I missing any stuff? Is there other things that, the home entertainment system, which I think is like how much subwoofer is too much for the moon. Service mobility, so once you're there, of course, like being able to get around, suits, things like that.
Yeah, safety protected.
Safety. Food, yeah, we have all the delivery of some pre-food, and I'm assuming, right, one of the things that we'll have to work for is a system that allows you to produce food as well, in addition to just, right, shipping it from the earth constantly at some enormous cost.
So that's one of the questions that I have about this is, are we using this as a test bed for future exploration? Are we saying that
I think we are. We said we'd like to use, right? Absolutely.
Okay. So in which case we have to assume that because this is our test bed for future exploration, our astronauts are on their own once we say this is day one of your long-term mission, right? Yeah. So they have to have, once we set them on the surface and once they close the door, they have to have everything they need for that entire mission. So we're talking medical suite with surgical capabilities. We're talking all of these, including all of the food from day 1 until day 1200 or whatever it is, and the capability of being able to keep that food cold, to heat it, to reliably get the nutrients they need from it. It's a massive undertaking, and we have to have, we're in the well over tens of missions to be able to do that.
I know you mentioned some really interesting things earlier too about the kinds of people. There was one specific fact that I think was particularly fascinating that I had never really thought of before. But there's, right, kind of speaking to that as well, there's a skill set associated with all this. I don't know if you wanted to bring up some. I thought that was fascinating. It's something I hadn't thought about.
The skill set of.
Well, I was talking about the blood types. Was
the blood types. Okay. Yeah. So, I think some ways it's interesting because people go back to these like early explorers, right? And what does that mean? And if you go back and study these case studies, some of the things like food becomes so critical, right? And how they celebrate the holidays and being able to match up to the holidays that is their culture that was back on the earth, right? Because when they were exploring, it was really important what those days were. And even though on the moon it might seem random. So the culture, the international food, also the fact that they are going to have to be independent in some ways, just like in the West or in the poles. And so there's different medical things they'll have to do, like they'll probably have to be all compatible with their blood types. There was an article I just read about, right, generating bovine cells, right? And we were talking about like, could you generate then hamburgers because you can't take a cow. So I think there's going to be, so we'll have them, instead of drinking urine, they're going to have to be like, how'd that cheeseburger taste, right? Like, how was that? So I think there's going to be all kinds of really interesting things that they'll get to do.
Yeah, I always think about the pet thing is always funny to me because I'm, as a proud parent of 2 lovely kittens, I always think about this is, we're talking, we are potentially generations away from bringing pets with us, but the idea of robotic pets already exists, right? And the ISS had a couple of very cute Japanese robots for a while that felt more pet-like than they were practical in terms of their use. So a lot of this stuff here is kind of interesting. We're sort of at a mix, as far as I can tell, of things that are somewhat implementable with what we have today and things that we sort of need to develop. So maybe we could just go around real fast and people could talk about, of this components, what do we have right now, sort of, I'm going to say kind of off the shelf, and what are the things that we need to build? So why don't we start with just the basic, what do we have today? This is the classic, right? What can I use that's already existing out there? We'll just kind of go around real fast.
Sure, so there are companies out there today that have, I know in particular a company called Astrobotic, that they have landers in these habitats that are completely collapsible. And then once they get into low Earth orbit or in transition to the moon, they can expand those out to something the size of this room, for example. And so we've got technology like that that's already in work and in development that we can use to save space so that we can get more of that stuff up quicker.
Yeah, there's a Bigelow Aerospace, right, which had the module on the ISS recently.
So we've got additive manufacturing technology. I mean, folks on the station are already using that. I think.
Can you explain that real fast? Sorry.
I think it's 3D printing, right? So if small handheld tools can't fit in the payload accommodations, then there's the capability on the station now to kind of print these things. So kind of expanding that and scaling it to a system or an architecture like this would not be too far-fetched, I don't think.
Yeah, from a habitat side, we learned a lot from just the 23 years that we've had ISS running. We've got a lot of experience and a lot of people that have been up there for long duration. And I think that if we want to be able to do longer and longer class missions, then we're going to kind of start pushing even further into the boundaries of what we know and what we don't know as far as what the human physiology and the human psychology can handle for tight quarters and small numbers of people living together for long periods of time.
Well, and you were mentioning, I think the other night, the sort of requirement as well on like some sort of personal spaces as well.
Yeah. So it's when you get a small group of people, we normally as humans we kind of like to have our space, but we're very social creatures. And the problem is if you're in a vehicle, especially something that's designed for deep space exploration, like a large Mars transit vehicle or something like that, the engine guys will say you need to have everything in line with your engine so that you're thrusting along your center line. Well, that's great. The problem is now you can see the entire habitat all at once. So if you get into an argument with me and I'm like, I'm done with you, I need my own space, we're always going to be in constant eye contact with each other no matter where we go in this vehicle, and we're just going to continue to hate each other.
Yeah, this is why
Kind of like we are now, right? I mean,
That's exactly right. This is why when I drive by Mom, I tell her, roll up the window on the limo so I don't have to talk to her. Yeah, so yeah, sorry.
Yeah, so like the design of vehicles and habitats is oftentimes not necessarily the most optimum for one particular input, but it has to take into account all these other inputs. And like you were saying, squishy payloads are notoriously difficult to launch and keep happy.
Yeah.
So to build off of that, I think there's actually some really interesting work that's being done in virtual reality environments to give, especially going to Mars, right, the ability for them to be able to put on a visor and just actually,
I hadn't even thought of that. That's very
right,
cool. Yeah.
and they are thinking about like pre-recording their families and other people with messages to them so they can actually go into that environment. Or one of the environments I got to see was they were walking down a hallway that looked like a museum or their house, and there was all these things and pictures and everything that was just, calm them down, or even just walking along the beach. And that's some stuff they've experimented with on ISS, but I think that's going to be so critical in the future. And it's a technology we have now, but the potential of what that's going to offer, just like how important food becomes, the potential of these technologies is going to be really interesting for those people.
Yeah.
So capabilities we have today, launch vehicles. If you look at the companies represented here, we have a suite of launch vehicles ready to go today, and we'll have even more in a couple, just 2-3 years from now. We can get anything we need up and out of our atmosphere and over to the moon. So I think that's capability today we can start taking advantage of right now.
Yeah, absolutely.
And adding on to some other things that have been mentioned, nuclear power, which is no matter what we do, we need power. I mean, we like our TVs. I see a nice television. We like to be able to communicate, eat, cook, what have you. You still need lots of power. And so some things that we have at our fingertips with a little more work is nuclear power that we can land on the surface.
Yeah, I think we're going to have to eventually have a communication satellite network around the moon that's probably beefier than what we do now, right? So you would know what we do now. We have Mars Reconnaissance Orbiter up there taking pictures, right? So to see how we grow our habitat and make us feel good about ourselves that we're growing. But do we have a relay communications satellite network at the moon right now?
So no, I mean most of those aren't really designed with the cross compatible. For Mars, we somewhat do, but we've always talked about whether we would have a telecommunications orbit dedicated for the rovers. So the orbits for the science orbits is not as ideal as for the communications aspect of it. So that's a trade-off as well, right? Which is
so we could certainly make something that would be a dedicated, internet uplink,
right.
downlink.
Yeah.
We have that technology now.
One nice thing that I think compared to the ISS, of course, is like the fact that there is gravity there means we don't have to deal with as much of some of the hard work, which is specifically with the ISS. So I want to kind of take this. What about the stuff that we don't have? And we'll start maybe this way and work our way around.
Oh, no time to think. Okay. Yeah. What do we not have right now?
Well, let's just start with the base. Let's not worry about some of I'll call them accessories, but required accessories. But like, what do we have for that base? We're talking about. We've settled on maybe the ideal, maybe not possible at this moment, but we're going to say some sort of cave on a cliff near the South Pole where there's a crater with resources. What sort of stuff do we have what sort of stuff don't we have yet for sort of assembling that?
I think we need more rugged spacesuits. I mean, NASA just came, they just publicly announced, the next gen suit. I don't know that it's been tested yet in lunar regolith and things like that for wear and tear, because I know one of the most precious commodities we have right now are spacesuits, the torsos, the hard upper torso and things like that. So I would like to see a lot more research and development go into more long-duration spacesuits.
Yeah, that's a big, of course, environmental concern at the moon, which is the regolith is very abrasive, yeah.
Yeah, and building on the in-situ resource utilization piece, as we start to want to move around the surface more, we might need spacecraft or vehicles that are not rovers, but vehicles that can transport us rapidly. So we need fuel production, the ability to capture material from the regolith and then turn that into something that we can fuel our rocket systems.
Yeah.
We talked about the in-situ resources, but we don't actually know how to extract and use that stuff. That's not actually technology we have yet. So we know there's resources there, but truly understanding how to use those resources, we're still working on.
Yeah.
Yeah, I think you kind of took mine with the suits, but I think also to build to build off of that, I think not just the rovers, which are going to be important that they'll drive, but also the suits. We need some kind of garage or maintenance. We need to go into there. You know, a lot of the stuff that I've seen designed, it's like, oh, it's a suit and everything's sitting outside, even on the Martian surface. But the reality is, even if the suits are connected to the kind of vehicles, you're going to need some kind of garage outside to be able to take them apart, do things, maintenance things. And that was a lesson learned we had from shuttle, was that we didn't necessarily have enough maintenance kits that we had flown to allow the astronauts to be able to fix things. And I think that's something that we have to make that main technology, but also understand that they need a maintenance kit too.
That is, yeah, she nailed it. So for things like long duration space flights out to Mars and such, the spares that we have to bring along for EVA and for ECLSS actually outweigh the systems that we bring along for EVA and ECLSS. Just the number of filters, the replacement pumps, the hardware that we have to bring along. So a lot of that is going to, we'll be able to buy down some of the risk by being able to put it onto the lunar surface as a test bed for the Martian surface and things like that, putting hours on the hardware in a harsh environment. But yeah, the reliability of the systems, if we can get across the board, but especially EVA and ECLSS, is definitely a big question mark.
Yeah, I mean, like, who's going to do the first oil change on the moon, right? Yeah.
I mean, and very appropriate of today, right? There's a spacewalk. The amount of resources required just to maintain space station and lunar infrastructure is going to be a significant chunk of these astronauts' time. Right, will be largely centered around just getting the systems to keep working, and then the bonus time will be some of the other fun stuff.
So building off of what y'all said, maintenance is super important, right? But we're going to probably get to a point where we'll want to test and explore on the surface, right? Like we'll want to push those boundaries and say, okay, well, we're here talking to your purpose and people feeling like they have this valuable contribution and they're giving this meaningful whatever they're doing to the community that they're establishing. We've got to be able to push forward and say, okay, let's test this new thing. Let's kind of take a new path. We've been using this suit for a while. I'm having an issue with this glove. Doesn't fit that well. I don't want to say, I'm here, it's day 2. What am I going to do? So can we find different things when we get there? And how do we do that? And then I think also greenery, right? Like we're going to crave that earth feel and the vibe. And virtual reality, I think, is huge, like you said. But can we somehow establish early on that connectivity back home to make us feel like we're in this together, we're this family now, and everybody has their spot, but let's connect back to our roots, sort of thing.
Yeah. So I think we might need to do a little more research in materials. So what if there's a material out there or some combination of materials that is kind of like an all-in-one? Maybe it works for our robotic spacecraft, our habitats, our transportation, our spacesuits. We always want stronger, lighter things when we're going to space, but what if there's some material that we just haven't discovered yet, or some property out there that'll help us in that realm?
I think we hit on something really interesting, and we're talking about depots and sort of things. One of the things I hadn't thought about yet is how do we organize all this stuff? So there's a garage, there's a cave, there's robots sitting out there. Anybody have any ideas how you I'm not even sure, right? We have not been able to necessarily demonstrate pinpoint landing on Mars yet. I know that we're working towards that kind of stuff as one of those future challenges. Like lunar landings are still not exactly what we call pinpoint. How do you get all these things down near each other? And what sort of can anybody sort of paint me a picture of how that works, and then what it would look like if I was standing there on the lunar surface?
So that's actually one of the biggest problems that we have as far as being able to do a build-up, because what we've got currently is we've got a standoff distance between each of the landers, where when the new lander comes in, it's going to be kicking up debris and it's going to be kicking up rocks, and we don't want that hitting our habitat that we've got sitting just to the side. So we can't bring them down next to each other and just inflate a little hallway in between or anything like that. So a lot of these components we're going to have to offload and actually have surface mobility, move it to a dedicated location.
Like a space tow truck.
Right.
Okay.
So the problem is,
I volunteer to drive that.
if we're talking about 40, 50 landers, are we going to have the carcasses of 40, 50 landers in this semicircle arc around our habitat buildup? And the more that we bring, the more hard it is to get through that graveyard of space junk, or can we create almost a space tug that uses lunar surface materials and lunar surface fuel to go up, grab the components out of the trans-earth or trans-lunar injection, and brings it back down on empty tanks.
Mm-hmm.
And if you can do that, you can prove reusability
Right.
with that. Then you can pinpoint land at the same location over and over and over again.
So that's a big enabling technology sort of for this, right? I think that's a kind of a way to think about this. So why don't you? I feel like you have a picture a little bit in your mind. Why don't you describe to us? You land there. You're the first of the 12. What do you see when you get to the surface?
I don't know. I think it's going to be boring compared to what we want it to be.
Okay.
Nope, disagree. We're on the moon. It's awesome.
Yes, and.
Yes, and.
What I would want it to be is like get rid of the aluminum. Let's make it all out of Lexan, so I can look outside from day one. There's no neighbors to have to hide from or anything like that. And I can like have a 360-degree panoramic view of the moon from my own personal little hub bedroom on the side of this spoked environment that we all share or something. I don't know if we'll have that. I think the practicalities of spaceflight definitely would put a damper on that opportunity. But I think what we strive for somewhere between that and man in a can, where you just send the bare minimum and the bare minimum environment and the just enough room to be able to take your suit off, and that's about it. And say good luck. We'll see you in 300 days.
What I somehow thought of. Oh, go ahead. Yeah.
Well, I was just going to comment. I do think it will be somewhat of a brand new campsite. You show up there, and you and maybe one other or a few people will be the only ones there, right? And there's almost no activity until you start to create that activity. You're going to be the ones helping to set up all of this new stuff. So you will have some semblance of a habitat that you may have to finish the assembly. There may be some parts of a garage that you will have to help finish the assembly. So though it will look plain, it won't be boring because you'll have lots of work to do, but there won't be a whole lot there that will look like a fully developed city, if you will. But that will be ultimately where you'll end up.
Yeah. What came to mind when you were talking, weirdly enough, it was like an ant farm. I weirdly believe like we're we're talking about like you wanted zigzags and like spokes, and I'm like, oh, underground, that's just like basically just a giant ant farm that we're gonna live in. I'm just sort of fascinated by this because I try to picture this in my head. I think it's really cool. The this assembling things yourself. When we talk about like robotic missions to Mars and stuff, the time lapse, the delay between the signal from Earth to Mars is on the order of minutes. And so we have to build in a lot of stuff that the spacecraft have to kind of do themselves. With the moon, we're close enough that, like, I would say humans are pretty cheap. I can put a human on a console and have them drive a rover on the moon with relative ease, because it's definitely not easy. How much of the assembly and things like that we haven't really talked about is, do we delegate to people that are still at Earth and using maybe the communications network that we mentioned earlier, and doing telerobotic kind of stuff, versus the sort of the 12 people that go down to the surface? Anybody have thoughts on that?
We've been incredibly, advanced in what we're doing in ISS, right? So in the beginning, we were kind of hesitant to do robotic stuff, even though we talked about it. And now there's been R&Rs that they've done while the crew was asleep, right? And they woke up and said, thank you so much, because that saved us the risk of going out and doing a spacewalk. And there was sections of the commands that were sent up, and then, you had a console person responding back. So there's nothing to be said that you have a crew on the surface that's sleeping, and then you have somebody back on Earth that's sending at least so much, and they got rovers going around and things processing, while they're sleeping. So I think that's very feasible.
I'm thinking like Space Roomba. Like somebody is a space janitor who's like, I have the robot that cleans the interior of your ant farm. Okay, I think we're supposed to take a quick break for a second improv thing. Can someone in the back of the room correct me? Yay, nay? Am I off the mark here?
1 minute? That says yes. 1 minute? Okay.
In 1 minute? As a vamp for a minute? Okay. All right, so just kind of to get back there. All right, what are the things that we need to, so let's talk about the very first mission now. So we've sort of kind of assembled our generic architecture. I think there's some details in there. I like that there's a space rainbow being drawn right now. It's very exciting for me.
Except
What's
you drew a dog instead of a cat, so he's obviously a dog lover.
That's fine. That's okay. I like that it's barking at a robot. This is just delightful. What's the very first mission? We've had the precursor missions from humans, whatever, that are short stays on the lunar surface. What is the first mission where we assemble this campsite, Reggie? What does it look like? What do you send down?
Besides people, right?
Well, I'm going to say people are last, right? We talked about we were going to start putting stuff on the surface first.
Well, let's see. I'm trying to think in order of what we might do. Obviously, you want to prep the surface, so you will have already done that for all your landers and rovers that might be there. Maybe the last thing before humans get there will be the things that are most perishable. So your food stuff, the supplies that would help keep your humans alive.
Yeah.
I figure it would be the last thing, and then the humans would
So
show
the niceties sort of first, get those in there. If they don't work, you've got some chances to fix it in the future.
Yep.
But the leading up to the very the go no go for sending humans is we've landed these critical supplies
your
on the
consumables,
surface.
whatever you need. Obviously, you're going to need air, so those things I guess you want to have enough time before the humans come, before to know all those systems will work. But those would probably be some of the last things you would do.
Yeah. Sam, you mentioned multiple international partners. We were talking about on the order of 40-ish launches. What cadence can we support for launches? Because I certainly know that for some of the stuff we've looked at, there's limited opportunities, and you can't launch stuff super fast from one site.
Sure. So with reusability, you can launch on the order of, at a minimum, probably a launch a week. So, do the math on that. And that's just one launch provider. If you had, 10 launch providers launching, let's throw a number out there. Let's say 25 launches a week. So you could have a lot of launch support.
Yeah.
To help you out.
So you really could just imagine an armada of sort of rockets going at one, which just sounds awesome to just imagine just tons of ships burning towards the I know they don't actually burn the whole way, but I want to picture that in my head. Maybe they're all ion engines and we're it's great. It just sounds really cool. But what you're saying is with the international capability, we have, essentially really could do most of these launches. I don't think operationally we could feasibly support a week. So what do people kind of think is a rough timeline from, if you were to start assembling this, let's say, we're going to say you're going to start this in 2026. How quickly is it, January 1, 2026, how quickly can you start putting 12 people? Wow. Realistically.
I think it's the triple constraint of space travel, right? You have cost, you have technical capability, and then you have schedule.
I knew you were going to bring up cost.
I'm a program manager, it's what I do.
Yeah, this is great. This is the age-old dilemma between engineers who are we can definitely do everything, and then people are well, you got to pay for it.
Yeah, so but theoretically, if you have international partners across the world, all the different countries with space capability, all launching together and working in unison, you now have tremendous resources, tremendous capability, so now you can start getting launch rates that are way higher than anything we've seen today. So I think the ideal is you get a worldwide effort to go forward to the moon, and now you have capability and resource beyond anything any single country has ever had up to this point.
To Dan's point, I was just going to mention that, aside from launch vehicles, which obviously many providers, right?
It's the most important part, right?
Right, yeah. We're done, I think, yeah. No, but there are, people, these companies have different strengths that they bring to the table, right? So I think focusing on the fortes of the companies, whether that's a spacecraft or whether that's focusing on the spacesuit or the consumables piece or the expandable HABs, So it's the identification of the companies and understanding and figuring out how we can all work together way before we kind of get to the point where we're sending things, right?
Yeah. So we're 7 years away from this mission starting.
Right.
All of a sudden, we've got a multinational collaboration, and we're going to start playing this as soon as we get back from, I think, the break here. I'm really excited to hear what everybody comes up with. So let's have the improv team come up here real quickly, and then do you want us to stay here, or do you want us to exit stage? We're going to exit stage. All right. Remember where your seats are. Good.
And the song?
Do you use the handholds here? We don't need it.
Okay.
Thank you.
Not smart enough to do this. Oh, locks. Whoa. Whoa.
All right, so we're ready to talk about the third rule of improv, and that's just to say it. Just make the statement. Don't worry about it being perfect. So to demonstrate that rule and the other two, which are listen and yes and, thank you, we're going to play Because I Said So. All right, so which of you are going to be the adults? All right. Dominic, you're going to play the kid, yes? All right. All right, so what's going to happen is I'm going to give Dominic a question that he doesn't know what it is yet. And he's going to ask this question of his adults, and they're going to respond with one sentence. Then he's going to ask what all children ask, which is? Why? Correct. And then the next adult is going to say a statement. And this is going to go back and forth until they can't take it anymore. And then they will say? Because I said so. Because I said so. That's right. All right, you ready?
Yeah.
All right. Yes, this one.
Why won't you get me a robotic puppy?
Well, you see, son, robotic puppies are quite expensive.
Why?
Because money is hard to work for.
Why?
Because it's green.
Why?
Because the dye to make it green is also expensive.
Why?
Because it's made out of fairy tears.
Why?
Because fairies cry every day for their long-lost pet butterflies.
Why?
Because they can't find them, they're fairies.
Why?
Because they can't fly back to them.
Why?
Because butterflies are way faster.
Why?
Because they're as fast as jets.
Why? Because I said so.
All right, good job. Rotate.
This is mine now.
So cool. You guys ready?
Yes.
All right.
Why do I have to do this?
Because I said so.
Why are there so many stars?
Because stars are beautiful and they light up the sky and we love to explore them.
Why?
You got me trapped there, friend.
So
because I said so.
There you go. Good job. Rotate.
Why is space so dark?
Because space is so old it doesn't need a nightlight anymore.
Why?
Because it's not afraid of the space monsters.
Why?
Because the space monsters are nice, actually.
Why?
Because that's how they were made.
Why?
Well, they were actually made that way to be on your TVs.
Why?
Because watching them is very entertaining.
Why?
Because they have weird faces.
Why?
Because I said so.
All right. One more. Oh, thank you. All right.
Here's this one.
Oh, thank you. You ready?
Yep.
All right. Are you gonna?
Nah.
No, you're okay. There you
My
go.
child's gotten older.
He's got.
Why are shooting stars so fast?
Because they love to fly across the sky to show us how important they are.
Why?
Because stars are full of themselves.
Why?
Because they love to show off all the time, just so that we can appreciate them.
Why?
Because they're so bright.
Why?
Because they're so smart, too.
Why?
I don't agree with that science station. But because I said so.
All right. Good job. All right. Thank you very much.
Thank you.
All right, we're going to let everybody get their mics back on. In the meantime, I'm just going to remind you guys where we are. So we have sort of designed this architecture. It's this cavern sort of main building, and then surrounded by a series of various sort of robotic and or inflatable structures that support this. So there's a garage, there's some sort of, like food production plant, there's some critical resources. Do you have a question? We can certainly, yeah, if the audience, yeah, absolutely. If you have a question, let's wait till everybody, yeah, come on. As soon as you get mic'd up, just come on down. You can sit in the same place or new places. It's really up to you. Yeah, it's up to you. Totally, I know. I'm just saying, like, whatever you guys want to do.
We're creatures of habit.
Yeah, no, I would have done the same. I'm standing almost exactly in the same place. All right, so let's go ahead and have some questions while people are coming out here.
See how they did it.
Why did I dye my hair color that way? It's because I wanted to look older, and I want people to take me more seriously. Sorry? There's a little purple and gray, yeah. I just get bored very easily of hair colors. Sorry, yes?
I just had a question or a thought about astronauts from having a mutiny. Like, that's a lot of micromanagement from a long way away for a long period of time.
That's what Netflix is for.
There's only so much Netflix.
Oh.
There's a couple of things. They do a lot of psychology profiling it beforehand, right, to make sure. So there's a lot of testing, a lot of really great people that have seen multiple astronauts and multiple different types of operators that evaluate before they're even selected. That's another reason why they also look for people who have applied that have been in some extreme environments or been in stressful or isolated conditions ahead of time, because if they've done it before and gone through that and they want to do it again, then it probably wasn't so bad for them. And the third thing is they do a lot of training before they ever fly, with each other, with cross teams or whatever, so they get a lot of coaching to make sure that when they do go up in space, it just rebonds even more, right?
So because of the distance and time, would they be allowed some like autonomy or self-governance, or would it still be sort of like the way the International Space Station is?
So the International Space Station actually does turn off the cameras out of respect, and we can actually see when crew members wake up. We can see that on the shuttle too. You can see it from the motion, right? Because just them moving around, touching, they can see that they're awake. But they do ask them before they turn the cameras on, just to give them a chance to have privacy. They also have their own quarters as well. But yeah, we do try to make sure that is their home, their living environment. Yeah.
All right. So I want to start. We're 2019. We're going for a multinational collaboration to do all this. I'm going to give. We don't have to I'm not going with specific countries here, but let's just sort of pair two of you guys off at a time, and I'll pair up with you. Let's have each of us sort of represent various factions in this sort of wanting to build this multinational coalition and figure out who's going to do which parts of this. And let's kind of start with that, and let's start plotting forward in time with this next little bit and sort of figure out how we'd work through this problem.
So are we America?
If you guys, I was trying to go for a nation.
Non-political entities.
So it could just be like different. Could be companies.
So
could be.
Let's pick a color.
Countries.
Yes.
What do you pick a color?
Blue, red,
maroon.
We're maroon.
Okay.
Yes.
Chartreuse.
Chartreuse. We're very fancy. Yes. Orange. Okay.
We're cerulean.
Cerulean. All right.
Oh my God.
This is a lot fancier than I'm used to. Okay. So we're talking about. Do you have a part that you particularly interested in building, some component? Go for it. Yeah.
We decided to work on laws and policy.
Laws and policy. Okay.
Yeah, so we've decided that if there's a conflict up there, like for example, one of the habitats runs out of water or food, and Chartreuse comes over and knocks on the door and tries to take the food, well, there has to be a way to settle that dispute, and we're going to work on an overarching set of laws and ways to handle those disputes.
Why?
So we all stay happy, right? Right, Reggie?
That's correct.
Do you have a preference? I'll let you pick for us.
Oh boy.
Yeah.
I'll go with the spacesuits.
Spacesuits? Okay, great. So we're in the spacesuits mobility system. Yeah.
I think we're going to be the civil engineers.
Civil engineers. All right. So that's structural sort of stuff. Cerulean over here. Do you guys have a?
Cost.
Cost?
Who's going to pay for what?
I think we're going to have to divvy up this with. We don't have enough groups up here to do this little work. Also, I noticed no one wants to.
There?
Sorry,
you're the rocket engineer.
Yeah. So let's add some more things. So let's take a second step. What other areas are you gonna need to work on? Space policy and
You do life support systems.
Life support.
Life support
Okay.
systems.
Does that start conflicting with your civil engineering? You guys still good with that? Okay. I like to do robotic stuff, so maybe like the robotic companions to our suits. All right.
Okay. Robot kittens.
Robot kittens. There it is. That's my $1 million idea.
We'll be the DJs and entertainment.
Okay. Like a social
Y'all are so fun.
aspect.
I guess we'll do rockets.
Rockets?
I
Okay.
get it.
So we represented a fair amount.
That's a cool stuff.
Yeah. Let's talk about what first steps are. So you've got 2 roles over here. What are sort of your first steps in sort of approaching those problems?
Go ahead, Reggie.
This is tough stuff, yeah.
Well, I obviously there has to be some sort of, I guess, hierarchy in the decision making. How do we decide? And also, if disputes do occur, who is the ultimate decider?
So we got 4 teams, so we have an even amount, which makes it hard if there's actually it's not a voting system.
We get 2 votes.
You get 2 votes. Okay,
We get 2.
You personally get 2.
We do. We wrote that into the policy.
Why?
But obviously, you know, if you've got an international or a national team, we've got to decide on how things get done, how resources are managed, who ultimately, or how if there are disputes over how much resources should be provided or who should pay for various things.
Yeah.
Because obviously
We got to hammer that out up front.
Yep. You got to work that out up front. So we are going to do that.
All right. What about life support? How are you going to get started on the life support?
We think we should support our lives on this habitat.
Bold policy
We are
choice.
pro-life support. No, we think we should manage we should have a certain amount of resources allocated at any one time for each habitat, and then we should also have a margin above that for each individual group, so that in the event that we have an unexpected depressurization or something, and we lose a tremendous amount of air, how do we backfill? Or we have to repair, obviously, but how do we have our required amount, but then we have the safety margin on top of that? So, go ahead.
And I was going to add, as much as possible, it needs to be regenerative, I guess, or recyclable, however you want to say that, because there's only so much you can bring.
Sure.
I mean, you've got these tens of launches, or it will be hundreds, if you have to bring all of your oxygen, your water, all of your food. So as much as you can, you want your life support systems to be able to regenerate themselves.
Yeah, we talk about consumables a lot in space flight, things that you can only, or essentially have a finite life.
Right.
That you start wearing down or you start using up, right?
And I know that what we've done on Space Station has taught us quite a bit about how to recycle air, recycle our liquids, for lack of a better term, so that we have potable water.
Yeah.
So those are big.
I mean, Dustin tried some of that this morning, so.
Yeah, you missed that. That was great.
He tried the recycled water.
Yeah.
Tasted like water. All right, what about us? So we got the suits.
Suits.
What are we like? Let's just start with some real basic. We've got existing suits. Why? What makes them not good enough, or what can we use from them?
Well, I think when you're going to have a long duration mission for multiple years, you're going to want more than 1 or 2 kinds of suits. So the suit you're going to fly in to get there is going to have one set of needs. The suit you're going to wear in the garage when you're doing your oil change for the first time, that's going to have different needs. The one that you wear while you're walking around out on the Martian or the moon surface, again, it's going to have different needs and different capabilities. So I think to start off with, let's start breaking down how many different suits do we need. Just name 3 and we're just starting. So that's, I think, where we start.
Okay. And the robotic stuff, I'm going to say I'm going to advocate for a high level of reuse, right? So we sort of understand mobility systems in these environments. We understand solar power, so we have a lot of the needs. I think the big things will be if these are sort of high slope, or let's say, for example, lunar relicus is very slippery, and we have do we need to design kind of different traction systems? But I would say we can leverage a lot of what we've done before.
Can I hear some kind of specific ideas about the vision for the suit?
The suits. Yeah, let's start with the suits.
Specific ideas for the suits.
We got to draw some. He's got a start of a sketch of a suit. New suits.
So I think let's go with the mechanic shop too. You need tools, right? You need to have accessibility to a lot of different tools. You don't have a lot of space. So I think you're going to have a mechanic suit that's going to have access to a lot of different tools on it. I think would be very helpful.
The rover has a turret arm, which just spins in place. Do I have like that? Or just like this?
More mobile, you might have more of a more athletic, leaner suit that doesn't have these 8 hours of consumables, right? So you might only need like 2 or 3 hours, which gives you a smaller, pack. You might have different gloves that you switch out. You probably have different shoes, right? Because you're going to just be leaning down and moving, so you're not going to need necessarily bigger boots. So all of that, you can have this kind of, you can think of it like a mechanical or athletic kind of leaner version. You'll have that one on orbit that is just really for, in case you lose depressurization, and then you're going to have this more robust one when you're actually going out to do, surface activities.
Yeah. No, it's good. I'm just want to make sure our artist has some idea. I like this a lot. What's happening here?
What does the helmet look like?
What does the helmet look like? Well, we keep talking about we would like more visibility.
All clear.
Yeah, as I think as clear as.
You won't need visors. You probably won't need lights on the top. Like the other one, you had lights. You'll have lights in the garage probably, so you won't need lights. So just a more smaller, more visible helmet.
Yeah.
Definitely.
You just have a little space kid that can hold the flashlight for you.
Yeah. That's what the space robots are. The little cat. Space
Robo
cat
Kitty and
there.
Robo Puppy.
Robo Kitty holds the little flashlight in its mouth. It's very cute. All right, let's go on here. So civil engineering. What's your approach to the problem here?
Well, we have one of two different options. One, we can land everything prefab and stick them together. Or if we put a lot of effort and time into it on the front end, we could send robots that could use the lunar regolith in order to build a 3D printed habitat for the entire crew.
So this is you're hitting on I feel like every person's ever problem, which is, if I just work hard today, I can make this one-time thing happen for me, versus if I put in a little bit more effort right now, I could have something that's reusable for multiple things. How do you approach that problem? What's your thought process for figuring out whether it's worth it to make regular 3D printers or whatever versus...
We ask Congress if they'll give us the money for it.
All right. So, but let's say you're in the challenge today. You have a finite time, so that might be one of the reasons you're not going to necessarily maybe reuse something versus... You're looking forward to, I really want to be able to reuse maybe this code or some aspect of this design, right?
Yeah. So a lot of it just kind of depends on how much time you're going to put into it total. Is it going to save you the long term in order to front load more work now, or is it going to cost you more and not pay for itself in the long term?
Well,
if you do.
we have a specific context, right? This is a 2-year mission,
Right.
but we talked about the long-term purpose was to enable us to do longer-term missions, potentially to other destinations, right? It's both a sort of a tech demo place for us as well. So how would you, again, given those new constraints, or whatever existing constraints,
So a couple of the things, basically we kind of look, when we look to land something, we try and say, what is the largest indivisible component that we would need to put to the surface? And for the most part, for human habitation, it's the habitat itself. It's the component that's got to be pressurized. It's got to have at least 1 or 2 docking ports for the crew to come in and out of, and it's got to have components in there for being able to recirculate air and water, things like that. So if we can shrink that down by saying, rather than sending all of that volume, we can send it as components that can fit inside of a volume that's made there, then how much mass can we save there per module, and then how much mass is it going to take to send a robot with all of the components that it needs, and then how many missions are we going to leverage this new capability if we do decide to go that route.
Okay.
And you kind of end up with a total mass cost and a total development cost that you can usually get a pretty decent idea of where that break-even point is.
All right, so the second part, you said you guys are doing the entertainment system here, or whatever the general, we would call it well-being. What's the approach to that problem?
Well, I think, it gives, if you kind of have a movie release date, or you have hey, this week is going to be Beatles or something like that, I think you kind of create a new kind of camaraderie and something for them to look forward to, and kind of a fun way to, if we do these different teams, they can put requests in, like a DJ request night or something, and I think that makes it a little bit more fun to be there.
So there's
But you have to have something that controls
a
that.
themed party every week is what I'm hearing.
There's a lot of that happens in other areas of very tight, very small groups that are isolated, like at McMurdo down in Antarctica. They'll have a movie night, like the first night or the last night that all the summer crew leaves and the people that are wintering over stay. They watch The Thing, which is all about an alien that slaughters everybody at McMurdo. Because why wouldn't you if it's dark all day every day and you're alone there for the rest of the next 6 months? That's what you do. But that's it's a team building, it's a camaraderie, it's an event that you look forward to as a social interaction.
But you have to have someone that kind of group that controls that, so that
space out.
Yeah, so we'd watch Apollo 18 or something like that.
No, right. Not a good movie though. All right, Cerulean.
So we were going to, work with our lawmakers over here to determine who's going to pay for what. Why should one country pay 10 times more than the other, and then just working with those guys on who pays for what would be important. And then we were going to work on the rockets a little bit.
Yep, it's important. I think reusability is a huge piece of this, right? So figuring out what the accommodations look like for crew is also a big piece. I mean, we're sending up a lot of payload, obviously, to get ahead of this, but also making sure that the people who are heading there, I think, are in the right state of mind is probably a good idea. So kind of thinking through what that looks like for the trip. Yeah.
So let's kind of break down the rocket problem. You got multiple providers.
Mhm.
Some are human rated, some aren't human rated. What are the other things? How do you sort of make, again, a decision between, do you need a new rocket, or do you sort of, again, use existing infrastructure and potentially have to build more things in place? I mean, the two of you guys are now starting to talk about things that have some overlap here, right?
Mm-hmm. Yeah, I think it sort of comes back to having the capability for maintenance and testing on site, and kind of pulling pieces that need to be reworked or refurbished. If there's a specific valve that we need to pull to to make the rocket work again, it's sort of.
So I'll throw it right. I mean, let's just say right now I have this issue. The two of you have a conflict. You've got a structural piece that you think is integral. It's too big. Let's say it's larger than the fairing diameter of the existing rocket systems that you have at your toolkit.
Mm-hmm.
How do you guys sort of work through that problem?
Battle Royale.
Okay.
Yeah, we take it to the lava
All
tube.
right, we go to the Thunderdome, and just one person leaves with the answer, and we have one fewer engineer to help us. No, seriously, I'd like to. I mean, can you guys kind of work through that challenge in real time? What would you sort of do? You're looking at a big systems picture here, where a lot of moving parts.
So what if we sit down and we have a couple of meetings throughout the week, and we go through kind of like an iterative design, conceptual kind of process. Well, this works for me. Well, that doesn't work for us because of this, and then kind of maybe make a graphical representation of that and cross things out, and then highlight that don't work, and then highlight the things that do work. That'd be a good starting point, I think.
Yeah.
This is a problem that happens in the real world all the time, though. We actually had a very significantly long design that ended up coming to a screeching halt because they didn't check the fairing diameter, and the vehicle that they wanted to launch on couldn't handle it. So I mean, this is something that we deal with on a regular basis in the real world from a design point of view, and generally what it means is you have to find another provider, or you have to go back and redesign.
Yeah.
Okay.
Either
But
subdivide.
You guys are talking
or,
about 7 years away,
Yep.
so you guys have an opportunity to either rewrite to potentially design. I'm going to say, let's say, as easy as just designing a larger fairing,
sure,
which is not trivial, or breaking your component down, or designing your piece in a different way. I'm trying to get at this because I think people are inevitably going to have conflicts as they design sort of things today. I want to sort of see that conflict resolution, if you guys don't mind sort of just playing it out in real time.
So walking, if you can walk backwards from that situation, I think the first step is to kind of understand the requirements. I mean, it's sort of boring, but this is what we need, right? And this is why I need it. And I think that rationale behind the requirement is the important piece, right? So
it's okay. I'll just give you a very specific example. It's the giant movie screen that you need. It doesn't currently fit. Now, you could either watch all your movies with just like a giant seam down the middle, or you have to build a bigger rocket. Fight it out. Let's see what two of you.
So the cost and development of building a bigger rocket, it's generally not. That's a non-starter. Normally when the rocket folks, and I say this politely knowing that I'm outnumbered here, when the rocket folks design their rockets, they don't really pay much attention to what the payloads are going to be. They want a class of payload capability, but they're going to fit what they think that their standard payload is going to be. They're going to design the rocket to that. So it's a launch capability, a mass capability, and a volume capability. We as designers of the hardware have to kind of either match that or find a vehicle that can.
To be clear, but it's you locally, right? Because we're talking about the long-term prospects of humans on Mars or some other place, and they all need very large screens. And so at what point do you, again, make a decision between So one or the other.
So I think when you talk about conflict resolution, how does it really happen in the real world, aside from reviewing the requirements, right? It's also a matter of something like, what can we deal with short term? You know, if it's an ongoing thing, right? If it's a one-time thing, it's more difficult. But if it's a short term, it's like, okay, like, all right, the screen's not ideal right now. How long can we deal with that? And then while you're dealing with that, we're going to try to figure out something longer term when either the budget comes through or the resources and materials gets delivered, right? And usually then people can find workarounds and they can kind of get through that, or they can delay launching, you know, something initially and saying, okay, yeah, I can do this other thing first and then reorder it. And that's how the conflicts that I've seen usually resolve.
Yeah, that's a great point, Adele. And too, during those conversations, sometimes the innovation, the creativity comes out, right? So it's like, well, maybe I don't need a screen to watch this movie. Maybe I can watch it on the side of a
I mean, yeah, you can do it
tavern
with
or something.
VR, right? I can create
Right.
like screens that look very large in a virtual environment. So we're sort of, we've all sort of settled on these initial cuts of things. Tell me what you sort of need to do your jobs, right? Because we're talking about 7 years, you need some budget. I'm giving you a timeline, so that part's fixed, just like everybody this weekend basically is going to have a timeline. How do you decide to sort of spend those resources, and when do you start making the decisions between, I'm done with the sort of the conceptual design and moving forward into I've got to build things, I've got to test things, I've got to operate things eventually?
Well, if just coming from the life support side, I mean, that's I would say, a fairly difficult technology and capability to create. So as soon as you understand your requirements for how many people, how long, you're going to start working that technology or that capability right away. All the testing that's associated with it. So you're starting from day one thinking about your life support systems. On the policy side, right, I mean, we've determined we've got a budget. We know what we're doing. We will probably assemble a team of all of the stakeholders, the various nations that would be involved. I would declare myself supreme leader.
Okay.
Yes.
And
Why?
Yes and
because I'm
no.
the supreme leader.
I like that a lot.
But you would have to have some sort of, I guess, legislative structure around which that body would operate to enable the decision making and making sure the missions proceed as needed.
And I would also like to canvass the entire organizational structure that we're going to be interacting with, and make sure that everyone brings their, for example, the docking port design. I want to see what everybody does currently.
Right.
What types of fittings and hose connectors do they use? And why do we have 2 toilets on the space station right now, right? Because if parts are needed from this one to this one, we're not standardized. That's why we eventually went to 1 toilet design on the space station, right?
Right.
And so I think that sort of stuff is important. We should, as we're generating these laws, we have to also take all the engineering aspects into account as well. And then the supreme leader can make the decision on, what direction we should go, right?
Absolutely.
So it's interesting, right? So let's just kind of delve in a little bit more, though. You're talking about life support. It's a complex system. We've done it in some places at some level before. You're talking about new environments. Where do you sort of make the decision to kind of spend a lot of time up front on the design and versus trying to prototype more early and often and sort of figure out what works there? Because I'm thinking for spacesuits, it's something where we might want to try to do more prototyping, right? It's such an interactive aspect of things, whereas maybe life support is something that you really need to just a heavy infrastructure investment, kind of like, so to speak, up front.
Right. Well, I don't want to get on, but I certainly think in the area of regenerative, I say consumables, but that's probably, if you consume it, you can't regenerate it. But the elements that are needed for oxygen or air replenishment, water, those things, I think you want to be as light and as small as possible. There may even need to be some revolutionary approaches to it as compared to how we do it now. So I would think those are areas where we spend a lot of time maybe throwing out the drawing board and starting all over again.
And I think we need to interact with our brethren in the civil engineering world and the rocket world.
We're brethren.
We're brethren. So, for example, like you talked about these carcasses of rocket landing things. Like if we're clever, we can use those pipes. That let's say we use legs on the landers that are pipes. If we cap them off on each end and put a port on there, then magically we have tanks up there that we could use as some future far off time to store oxygen, air, whatever. So if we could, all work together early to get our information into your designs, then if you have a structural, remember, if we're clever about it, we can also double dip and use your structural entities for life support systems.
Reusability thing, right? I mean, essentially on a very practical kind of level. So let's talk about our spacesuits and our robots for a little bit. Spacesuits, right? We're talking maybe prototype early and often.
Yep. Yeah, I think we've identified what kind of suits we want to have. Now let's throw some ideas out there, prototype them quickly, get an astronaut in them, see if, is it comfortable? Does it work? Do they like it? I think it's also important to take a step back and say, what do we already know about spacesuits? What research is out there? What information is available to us that we can use? If we've already got a glove design that works great, you said it before, no reason to reinvent the wheel. So just take a look at what we have available to us and let's start building pieces and have people try them out.
I have a question about the suits. So if my if my hand is a different size than someone else's hand, how are you going to account for that sort of thing?
You can cut the tip of your finger off. It's fine. I think that's something you have to make sure you understand. Hopefully we have our astronauts identified ahead of time so we know who our 12 people are. So that's one of our design constraints, right, is what size hands do we have to accommodate? I think that's important when you're starting to talk about long duration and having a very set group of people is taking that into account.
So do we constrain the number or the physical attributes of the people that fly in order to have them similar enough that they could potentially exchange hardware? Because at the moment, like we try and fly 5 percentile female to 95 percentile male, right, which encompasses a huge percentage of the population. But back in Mercury, it was 5'7" to 6 foot even, and that was about it. So do you try and do you restrict it in order to make it?
If he gets to be king of the world, I'm just going to make this answer up as I go. So I'd say let's get the 12 best astronauts for the mission. Adele talked about how much research and testing goes into picking those 12 astronauts. Let's figure out who those 12 are, and then we'll design the suit around those 12.
I have a question.
No.
What can I draw down here?
Is this in the cavern?
Yeah.
Tentacles.
Well, my vision, like I said, was the weird ant farm version where there's like little housing units for each person.
What if you have ports? What if you had ports that go to different lava tubes or something, and that's where different things are? That's a question for the panel. That's not a.
We also did discuss space cows.
There were space cows. We did talk about that.
It's suspected.
I don't know if I draw the space cows.
It's suspected
but
that
that's
there's water in the crater. So you might, I don't know if there's small pools.
Little water skiing.
Yeah.
Or some type of water reclamation industrial site.
Yeah.
So that's a good. Yeah. So we haven't talked about the processing of some of the resources. I mean, that's something they could draw. What does that look like? We could draw. What does a processing kind of plant look like? Just like a giant manufacturing
pipes.
Pipes. A lot of pipes. Yeah.
Drill.
Okay.
Are we gonna have a traditional backup ladder that's a worst case scenario?
Yes.
A ladder.
Well, that's another problem. So, I'm going to totally derail the conversation here for a moment. I'm sorry, but the Shackleton crater right now is one of the big candidates, and most of the slopes coming into Shackleton from those 4 points of majority sunlight are about 20-degree slope going in, and it's not a small crater. Like you can fit, I think, 6 Grand Canyons side by side down in the bottom of the Shackleton crater. It's absolutely massive. So we're talking a multi-day, to get down to the bottom, and then a multi-day coming back up along this very, very steep slope. So yeah, climbing up and down a ladder might be a little bit
very big ladder,
very long ladder.
I don't know.
No.
There's some emergency thing.
I like ropes.
Yeah, rope. Yeah.
Or jetpack. I don't know.
Oh, there you go.
Jetpack. Yes.
I'm not too worried about the entertainment system in terms of your development timeline.
Well, that's just because you're not going to be an astronaut.
That's true. That's fair.
Oh, he's the boss. See, we wrote a law that says Bobak is part of it.
But I'm curious about the civil engineering. So how do you sort of approach that challenge? We talked about a bunch of different concepts, just even in just the last hour, right? But where do you sort of decide it's a lava tube, it's not a lava tube? I'm going to throw, let's say hypothetically, you go, you do higher, resolution observations of those sites, and you don't find any candidate lava tubes.
Right.
What do you do?
So yeah, I think a lot of that goes to like the lava tubes or the regolith on top of the crew cabin. You ask yourself what's the reason for that, and if the answer is the space radiation, basically you have to take a look at the amount of space radiation that the crew is going to have and say what level of tolerance are we going to have toward risk. And then if this is a mission in order to develop the capabilities for being able to go deep space and out to Mars, then is our 300-day surface stay on the moon, is that any different than a 300-day transit to get to Mars? And then the 300-day transit back and the 500 days on the surface, like are we really putting them into any higher significant risk relative to the missions that we are already planning beyond this?
I would also build off of that one of the this is a great opportunity to, like we just brought up, like not, while we might select the best astronauts to go to the moon, it's not going to be the best minds necessarily of all of these different domains that are going to be there. So this is an area where it's going to be such a huge long-term project that we're going to want to have tag-ups, we're going to want to try to like 3D image and be able to share that and maybe even walk in a VR environment with the civil engineer that's on Earth and say, hey, what do you think? Like, can you see this? What's going on? And I think it's an exciting, great opportunity. You think about the ships that they had to redesign to, because of the ice and the way they had to cut things, and you can go in. Oslo has this great museum where they actually cut ships and show like evolution of that. This is just going to be a collaborative, huge, wonderful thing that I think is going to be really neat.
So do you invite multiple sort of styles of engineering? What is the thought process for you, how you sort of approach this?
Yeah, so I think that it's definitely a multidisciplinary approach. We have to have industrial design to figure out like best layouts and most efficient utilization of space. You have to have design engineers for it to look like home, or to look like it's not overly sterile or not overly whatever. You don't want to live multiple hundreds of days in an environment that feels like you're in a steel can. So there's a lot of inputs that we'd have to take into account, and I don't think that any one entity or any one country is even going to own the design. I think it's going to have to be a collaboration.
So we're talking about that kind of compatibility earlier that Dustin was talking about, is that you're going to have multiple, each serving maybe potentially a unique purpose, right, but not necessarily implementing it the way that I would say, for example, implement each of those things.
Right, and if we are multinational, multicultural, then it may be that my design for what a home would look like or what a comfortable space would look like for myself might be different from somebody that's from the Far East or somebody from South America. So taking those inputs and trying to find a good working environment for everyone is definitely important, especially early on in the design process.
Yeah. There's a ton of stuff there that could go wrong. I mean, again, it's a short timeline here that we sort of, I've I guess levied on everybody. How do you sort of make the decision again here, and what you try to inherit, and that's mature enough that you feel confident you can make 7 years from now, versus what you push on and try to develop on your own, right? But at risk that it doesn't make the schedule.
Right. So assuming that tomorrow we got Space Act agreements with every country that was interested
now, so we
in
can
flying.
Do that.
Yeah, we got the best men on it, top men. Assuming we've got Space Act agreements with international partners coming through tomorrow, and we can start divvying things out. So the European Space Agency says yes, we'll do surface mobility, and we'll do we'll assist with some lander technology, and we've got multiple commercial partners that are taking chunks out of the problem. I think even then, 7 years is pretty ambitious.
Oh,
you
definitely.
don't have the ability to do a whole lot of from the drawing board, through design, through test, through iteration, through PDR, through flight demo, and then onto the surface for actual crew usage in 7 years. So most of the stuff is going to have to be lessons learned, hardware used, adapted if possible. But
yeah.
Most of this, I think a lot of this we've already kind of done with ISS and Orion and all the other space flight.
So I was going to say, kind of arguing about the apps challenge. Of course, I don't think they're going to have to worry about redundancy in the code. Obviously, I don't think that's going to be a thing. But in terms of redundancy of skill sets, right? I mean, how do you, again, I guess maybe a broad question to the audience, how do you decide that if one group is, for example, going to do the habitats, would you also put a second group there as a always have a sort of a back burner solution to it, even if it's more conservative? Do you do that all within house? You say, no, we've trusted Cerulean to do their job, and if they don't, then the whole thing falls apart? Or like, I guess how do people sort of approach that problem? And I guess, and I'm sure everybody has a real life example that they could probably draw from.
Well, I was going to offer that. I mean, in any mission, redundancy is. I mean, we always consider redundancy at some level, no matter what. And so I would propose that we would have that. Maybe not at 100% at some level, but if someone is bringing a habitat, we want to be sure to have some ability to either help secure that capability, whether it's with another country or another capability, another business opportunity, however. So I definitely think those required assets, you want to be sure that you have some backup.
Yeah, and maybe get everybody, all the stakeholders on board with defining what a critical spare is, right? Where do we need that redundancy, and where is it a nice to have?
Cerulean, your economy has tanked, and now you're no longer able to build all the things that you said you were going to build.
So what if we took some of our launch vehicles that were launching something to the moon on? What if we took those expended launch vehicles and were able to cut them open and make them into some type of habitable environment?
Right. Yeah. So I mean, I think there's a lot of examples here, of course, of trying to leverage, of course, what we have existing, right? Like, so if we're building structures, or we have, I mean, Saturn V is right, essentially a reuse of its own components, essentially. We can kind of keep building and try to reuse things that are maybe not as efficient or ideal, but we can it works well enough that we can just kind of apply it to multiple domains. So if you have like large structures, you can reuse them. We're sort of wrapping up here, so I guess.
One other thing to add to the conversation about redundancy is, in some cases, and especially as you take it forward to the apps challenge, you may not have that opportunity, or you may not have the resources to dedicate to redundancy. So some of the things that I think would be important for us to do for our mission is have touch points, have communication, and make sure we set up a method to touch base to say, are you guys falling behind? Are you done early and you have extra resources that you can come help us because our spacesuit's falling apart? So,
yeah, that's a great example. I mean, we do that at work all the time. When you're talking about what are the things that are the biggest challenges in the near term, and sometimes you recognize that even though my thing is going very well and I could keep making progress, there's another aspect of this that needs more help at this moment than I do, right? And so you volunteer to pitch in.
You start balancing resources that way.
That's
true. People too.
Absolutely.
We keep thinking of like actual resources. You may get to a situation where you need to pull someone off of some other mission or some other task because you really need their help somewhere. That'll have to be all kinds of compromises.
Yeah. Dustin, I want to give you a moment to sort of describe to us what you've drawn here, because we're going to head back to the improv stuff in just a moment. But
yeah.
So
you have did they give you a mic? All right, it's a little.
Yeah. So I've just been following the conversation, making a very cartoony version of some of the ideas.
I love it. We've all been. I think I've noticed everybody up here is sort of just like, okay, you're talking to me.
But yeah, I don't know too much about space or what. I don't have a expert design, but yeah, these are just some of the ideas that you guys convey.
Yeah, so I see some suits. We've got the cavern. You got the garage over there. You got some hidden gems, I feel like. Do you want to quickly point some of those out?
Obviously, we have a Roomba.
Yeah, thank you.
And near the Roomba is a cat, because those two things go together, even in space.
Definitely.
You got your.
I feel like we're ripe for the internet on this. It's great.
We're on the South Pole. We've got our TV with Netflix.
What show is that? Could you quickly? Yeah.
It's just it's Spaced Invaders. Anybody remember that movie? Greenhouse, we got like our landing pad for supplies, and I guess some underground water and cool tube system. And then real quickly, I was going to put something in here, like this is a see-through room, so just tell me what to put there and I'll do it right now.
Does anybody have any suggestions? Like last chance to get something into this drawing that you want to see in the secret
Gymnasium.
Area. A gymnasium?
Absolutely.
All right.
Space gym.
I'm in. All right, well, I want to thank the panel, everybody, and then we're going to turn it back over to the improv folks for one quick more exercise I think they're going to demonstrate for us. Thank you guys so much.
Thank you. Yeah, thanks for hosting the panel.
Yeah,
Wow. All right.
No, that's the moon.
Thank you. You okay? Okay, so our fourth and final rule for improv is to have a really good time. When you're doing improv, there are no silly ideas. They're all great, wonderful, creative ideas. So, and that works for creative brainstorming as well. So if you can't tell, we've been tying improv into creative brainstorming when you're working in a group. All right, so the 4 rules were listen, yes and, no. That was the game. There are no mistakes. Just make your statement and have fun, right? All right, I think it was 5. Okay, so we're going to play a game called What You Doing? And what's going to happen is we're going to have someone up here doing some motion, some activity, usually moon-based, and someone's going to come up and join in that activity and say, what you doing? And that person's going to say something totally different. And that person has to do that new activity. All right, it'll make sense when you see. All right, who's going first?
I guess I'm
Excellent.
going first.
What you doing?
Modeling spacesuits.
What you doing?
Being lifted by my dumbbells.
What you doing? Oh, wait.
Popping balloons.
What you doing?
Inflating balloons.
Inflating balloons.
What you doing?
Fixing my broken space cat.
What you doing?
Declaring myself supreme leader of the moon.
What you doing?
Oh, just dyeing an alien's hair with Cheetos.
What you doing?
I'm drinking moon water.
What you doing?
I am reading a brand new space novel.
This is really confusing.
What you doing?
Getting in my new spacesuit.
What you doing?
Just recycling.
What you doing?
Drawing the moon.
What you doing?
Scavenging dead moon rovers.
You.
What you doing?
Getting in my new space rover.
What you doing?
Buckling up to go to the moon.
What you doing?
Using the whiteboard.
What you doing?
I am pruning the trees in the greenhouse.
What you doing?
Leaving the moon.
What you doing?
Meeting the artist who's drawing this amazing picture.
Awesome, good job. All right.
Okay.
Thank you so much. I hope our ideas have helped you guys come up with new ideas, and it's been fun. Goodbye.
Bye.
Go. Okay. On or not? Yeah, there you go. All right, before we take a break, I have a couple of news items here. You know, breaking news. This from Buzz Aldrin just a little while ago. Looking forward to watching these 2 patriots make history. Their can-do spirit and unshakable confidence will inspire millions of young girls to go to space. Congrats, Astro Christina and Astro Jessica. Let's hear it for these 2 women who did a spacewalk today, and we watched it live. One more little bit of information. We have now broken the record for the number of people tuning in as registrants for the International Space Apps Challenge. 25,236 and counting. Yay! Let's hear it! All you folks around the planet Earth, what a great job you've done. Now, let's go take a bio break. Thank you.
check, check, check. 1, 2. Check, 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 check. Check, check. Check, check. 1, 2. Check, check, check. Check, check. Check, 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 check. Check, 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 check.
I won't make this as awkward this time. Great. Woman. You are. Are you nervous? Are you excited?
Oh, I was nervous.
Me too.
They say that's a good sign. Test 1, 2. Okay. Yes, that's great.
Good with you?
All right.
You need to keep going? Just say your name.
Oh, hi, my name's Adele Luta. Test, test, test. Test, test.
Okay, now try that.
Test, test, test,
Moved
test.
it up. It's better.
Okay.
Hello. We're now down to almost the end of the day before the hack starts tomorrow. So we have one more presentation, and it's going to be amazing. Right, Adele? Yes. Adele Luda is going to talk about coding challenges in space and what we need to do to work on the challenge apps and everything. But one thing I've discovered about her is that she's an Avengers nerd. Is that right? Skip the spinning rims. We're on the clock. Is it time to get on the clock?
Yeah.
All right. Without further ado, Adele Luda.
Hi, so I just want to start off by saying thank you, and to everyone who's out there, I'm going to try to do a little bit of a hello. So hello, bonjour, buongiorno, hola, dobry den, to the people who are a little bit later in the day. Thank you for joining us. And it's really exciting to have everybody here in the room and then everybody out there as well. I put up my Twitter handle here, so if you want, you can tweet questions while we're going. I'll also make a commitment to you guys to get a rapid response back for any questions you tweet in the next 24 hours to me. If you can't think of something now and you think of it later, I'm happy to get you a response. So feel free. All right, so to start off, I wanted to start this presentation off with skip the spinning ribs, we're on the clock. There's a sense of urgency about space right now. And there's this question that we talked about in the previous panel about what is minimum, what's enough. And I want you to know that out there, whether you're in middle school or high school or college, there is going to be work to be done. Even if we design some of this or we pull from older designs, there's things that we're gonna need to still improve and work on. And this talk's gonna talk about some of the coding challenges that we're gonna have specifically in relation to spacewalks and how we're still gonna need your help, all right? So this is from this morning that I pulled, the first all-female spacewalk. We had 2 females out there for the first time. This is a little bit better of a picture. Pretty exciting. Yeah, and so my role right now is I'm a physicist by training. So code for me is a way to do the job that I do, right? So if coders in the room, you might consider yourself a coder. You might consider yourself a programmer. People who consider themselves developers, right? However you name yourself. And then there's hackers out there, right? I'm definitely not cool enough to be a hacker. But I use code, and just like I use physics and I use math to do the jobs that I do. And the job I do right now for the federal government is addressing issues at a national level, but a previous job I did was training astronauts to do spacewalks in mission control. So I had a lot of friends on console this morning, really cheering for them, and it was very exciting to see. So I was very honored to do that job, and I'm gonna just take that story forward a little bit to talk about the coding challenges that we're gonna have. All right, so one of the things I need is a volunteer, and since it was the all-female spacewalk, I'm gonna bring up a female, but guys, I'm gonna need you later, so hang tight. So do you wanna come on up? Yeah? All right. So I brought a little bit of a prop here. You wanna come on up? So I'm a scuba diver. This is my regulator, and I'm gonna give you an idea of how this kind of works. So if you'll come over here and kind of face that way. So this piece of equipment hooks up behind the diver to a tank. If you want to hold this, you don't have to put it in your mouth, though. Just hold it in front of your mouth. And that is a regulator. So there's a first and a second stage, and she would breathe whatever was in this tank. We can do all kinds of mixtures and she would breathe that. And she also, for emergencies, has this yellow one. Can anyone think of why you would have the yellow one? Do you think why is it such a bright color? What does that usually mean?
Extra, like.
You're right, it's a backup. And what are our backups usually for?
If the first thing breaks.
For emergencies. So we want that to be super bright. And because we have buddies, we also want them to be able to see it if they need it. So thank you so much. You did great. Thanks. All right. Good job. So the reason I bring up a regulator, right, this is a picture of me diving. So you can also see right here, this is the tank that's on my back, so same kind of setup. And for regulators, right, they're basically getting a higher pressure gas flow down to where it's feasible for whatever environment or breathing or whatever, our lungs especially, right? We want to store that gas at a much higher pressure, but then allow it to do something at a lower pressure later. That's great, okay, regulators, right? Well, regulators are really important in the future. So this was earlier where NASA announced, right, the suits that they've been working on for the moon and Mars. And these suits have regulators. So the way that she was able to stay pressurized was because of a regulator system that was there. And so when you think about these really hard problems in space, they come down to fundamentals, and that includes coding. You want to know your domain in your area, and you want to know that from the basic standpoint all the way to the difficulties in space. So don't get overwhelmed by space. There's fundamentals that we build to there. Okay, so talking a little bit here, what do the flight controllers do? I mentioned that I was a flight controller during the spacewalks. This is me in the back room. It's called a MIPSR position, which is a multi-purpose support room. And this is me in the front room when I was working with the EVA console. So the front room people, if you know the flight director, the Capcom, right, capsule communicator, they're talking up to the astronauts. The back room people are the people I want to talk about. Because in the future, when we're at Mars, this person, this job can't exist anymore. The delay is too long. So I'm going to need to develop some kind of coding to be able to replace my job, right? And that's a good thing. It's a good thing. We haven't done that today because we have this job, right? So I'm going to take you up from just like a regulator. I'm going to build up what I did in my job and what we're going to need code to do. And there may be multiple people that have to write this code, right? So it's probably not just one person. And then just to show you kind of what it looks like, this was a picture from this morning, from them actually on console supporting the spacewalk. So really exciting things, and you can absolutely work here, right? It's all there. Okay, so what does a regulator look like? I'm not going to talk you through this, but what I wanted to do was show you that there's engineering drawings. So that means that it's really important in your jobs in the future that you work with multiple disciplinaries, right? You're probably not going to wear one hat. I've worn multiple hats in my job, but you're probably going to have to work with engineers. You're going to work with people who are machining things. So as a coder, right, or a software designer or a developer, you're going to have to talk and speak all kinds of different languages. Because at the end of the day, they're thinking about this, and you're thinking about what's the input coming out of the sensor, and how do I make sense of that data? All right, so let's get into the actual EVA activity. We talked a little bit earlier. We heard about what makes people need to be alive, right? So in a spacesuit, it's its own vehicle. I was talking a little bit about gases there, but there's going to be multiple sets of data that we're going to need to look at. So what are some other sets of data you think in a spacesuit we would have to look at besides just breathing? What are some other ones that anybody want to jump with anything?
Heart rate.
Heart rate's one, yes, absolutely. Anything else? Yep. You're right. We have to have a way to keep the humidity down at the right level as well. So, and then that involves cooling as well. So yes, very, very good. Removing CO2. Yep, go ahead. Yes, so introducing oxygen, absolutely. So there's a whole bunch of different sets. So I'm going to talk about one set of data, right? But really, there's many, many sets of data that the code's going to have to look at to talk about how we plan an EVA. So when I talk about predictive data, we want to go into any situation with as much data as we can prepared for that. So you're going to have a set of predictive data, and you're like, what is that? All right, so does this look familiar to anybody? I took this at the gym. Yeah? What is this? So this is a profile for running, right? And we would probably have a similar profile. We do this now for the space station. We'd have a similar profile for what we think the EVA on the Mars or the Moon would look like. So, it may provide different types of elevation. It may have a certain amount of distance that we want them to go. At a certain point, they may actually get on a rover. So there's going to be some kind of, we call this like a task list that we're going to have them do. Okay, so you're going to have that set of data. It's going to have a workload function. Then we are able to do some of the training on the ground. And this is a picture of the Neutral Buoyancy Laboratory. The Neutral Buoyancy Laboratory at Johnson Space Flight Center is a large pool that the astronauts train underneath. Now, right now, when they're working on an ISS EVA, we weigh them to be in microgravity. But they've also done training recently to where they've actually been weighted, and we can weight them to be either 1/6 or 1/3 their weight under the water on the ground. So they've started walking under the ground. We also have other missions in which they're weighted as well, and some of them are out on the ocean floor. So this is really good information for us, right? Because they're wearing a spacesuit, they're down under the water, we're able to weight them, and then we can get measurements here. So I can kind of see how they're doing based on those tasks. So this gives me a predictive profile. And one of the things that's kind of interesting about this profile is how that leads to what we're gonna move to in the future. And that's that I'm gonna, so this is part of my run data, right?
And you can imagine that someone may not look the same in space that they do on Earth. What might be some of the reasons that we think someone does better or worse in space depending on how they did here? Yep. Exactly, their weight. So there was an actual situation that happened where we had 2 crew members. They were both in shape, but one was in really good shape. And when they went on orbit, that one that was in a little less good shape, actually, their metabolic rates just dropped amazingly. And we got a long EVA time out of them. And the one that was in really good shape, we still got a good EVA duration, but it didn't look as impressive, which was kind of backwards, right? Because they actually were already in good shape. So we have to be prepared for thinking about how Earth is going to align then with Moon and Mars. So if we load in just the profile data on Earth as a predictive capability, we have to have a way to tell the software, hey, there's got to be some factor to interpret this for space, right? Or long duration. So it's going to be interesting. Plus, if they're really in shape on Earth, and then it takes them 6 months to get to Mars, this profile may be different too, right? Even if they're exercising. So this piece right here is going to be really difficult, right? And that's just predictive data. That's data we have. So that's going to be what we estimate for the duration of the EVA. Now, let's get back to eliminating my job, right? So part of what I would do is I would have these numbers ahead of time, and then I would sit on console and we would get real data from the spacesuit coming down, okay? And when we got that real-time data, then I could take a look and start adjusting real time what I think was going to be happening. So that was something, it was an art and a science, right? It was kind of making these calls. We'd be listening to their voice to see how tired they were. But there's a component to this where they build together. This part of them building together is they're a team, right? So right now, what is the minimum number of people we need to do a spacewalk? Anybody know? Yep. All right, it's close. It's a good answer, right? We do have 4 people ready for the next set of EVAs on station because there's so many of them. But when we go out the door, we need half that. So what's half that? 2. All right, thank you. So 2 people is the minimum because you have a buddy system. And so in a buddy system, if you have one person that's phenomenal and the other person that's tired or having a hard time, it doesn't matter. They come in, they go out together. And there's probably a pretty good chance that we're going to do that, at least initially, on the Moon and Mars the same way, right? Because if something happens, another person has to run and put a spacesuit on and get out to that person. And so we're probably going to at least start with 2. Hopefully, maybe we have 4 or 6 or 8 people all outside doing different tasks. But we're definitely going to have to start with 2. So now the software not only has to track what was the predictive capability and what are we looking at real time, but it's going to somehow also have to tie in to the other person, right? Can you think of some other things that might be challenging besides this? What might be some other difficulties as far as processing these sets of data? Latency or loss of signal, right? So if for some reason the astronauts are out and they don't have line of sight, or they'll be able to and they miss 10 or 20 or 30 minutes of data, that's going to throw things off as well. So there's a lot of complexity here and a lot of kind of what ifs that you have to write into the code, which is going to be very interesting. So you take all that into account, and that gives you your estimate that goes to your actual. And because we don't have a person on console watching them, right, we're going to need to do this again in the software. So now this software, right, is going to have to make a recommendation that gets updated real time to the astronaut team. So it's going to say, okay, I think you have 2 hours, or I think you have 4 hours, or hey, you just worked really hard. Based on this combination, you only have 30 minutes left, right? So it's going to be really complicated. And one thing I can tell you for sure is, even if we think that the people who are working on this problem right now get this really, really well done, it's not until we get real-time, I have raw data here, but real-time data that we actually get a good feel, right? There's nothing that really is in place of real data. Getting real data as a scientist or an engineer is what makes all the difference. So we have a whole bunch of people that are working on this problem right now, but until we set foot again on the moon, this whole thing may have to be reworked with different assumptions. And then when we go to Mars, it's going to build even out to different places too. So there is so much work to be done. There's so much help we need with just this one problem, this tiny one issue, right? And you could even say this is just one consumable if we just look at oxygen compared to all the other consumables they're going to have to look at in the suit. There are thousands and thousands of problems, right, that need to be addressed like this. And we need really smart people to help the scientists and engineers figure out how to do these capabilities, okay? So please, even if you don't say in this domain, any other problems, right, that you have on the Earth or in space, it's so complicated. But when you break it down, it's definitely feasible. So I just wanted to give you that example. And to kind of just remind you, right, this is thanks to Curiosity, a gift we got from Curiosity. This is the Martian surface. And that's Earth right there, that tiny little dot, right? So sometimes it seems like Mars is so close, but really it's really, really far away. And we're going to rely a lot on the code that we write, the code for the environmental control system, the code for the power system, the code that does the telemetry, the code that does the suits. That's going to be incredibly important, especially if we have people living there, much less robots or other things. So, it's a call, really, to help us. All right, so in closing, sometimes I get questions on, like, what do I need to do? Like, what makes a difference? I will tell you from my experience, get a solid degree. Don't get a tech degree or one-off degree. Get a solid, good degree. That does not mean you have to go to an expensive university, but just make sure the program you're going to is a foundationally good program. It means you're going to have to work a little bit, but it's important. Secondly, know your stuff. Because when you're out there and people's lives are on the line, you need to make sure that you know what you're talking about, right? Because otherwise we have mistakes that happen. So get a solid degree and know your stuff. Now, say you start down one pathway and you figure out whether it's a job or a degree, you kind of want to change, I'm not sure. That's okay. There's nothing wrong with that. If you can, do something that you believe in, because when this stuff gets really hard, it's important that you're passionate about it. So it's okay if you change your mind. It's okay if you don't know right now. But if you're not sure at all, at least start off with getting a solid degree. And know that it's probably going to take work, right? I've found that anything in life that really pays off or is exciting or interesting, I was very lucky in the case that as an instructor, I got to do we call runs, so actually be in a spacesuit in the water doing the same type of tasks that the astronauts were going to do. That was amazing, right? But it took hard work to get there. It took me getting my degrees. It took me knowing the things I needed to know to certify. And then you get to do some really cool stuff. It can be tough. And a lot of times, you're going to have to make little choices to do your homework, little choices to try really hard on that test, little choices to give things up. Unfortunately, I feel like we're in a world that only acknowledges big things, right? Nobel Prizes, or you finally got a degree, or you finally made a big discovery. But the behind the scenes in that, don't let social media fool you. It took many, many, many little choices to get that far. And it takes many little struggles, right, that you have to overcome. And the world's only going to count these big successes. So if it feels hard, it's okay, because it's probably going to be worth it in the end. And the last thing I just wanted to say to you guys, and especially everybody out there, is that this is a place for you. We need you, and you can absolutely make a difference. All right, so anybody have questions, or we'll take questions online?
Oh, I could talk loud.
I'm sorry.
So when you're on Mars or on the moon, how do the astronauts use the bathroom? Do they have to take off their gear?
In the spacesuits?
Yeah.
So they do have a diaper in the spacesuits, but one thing that's kind of interesting is the suit is really good at removing a lot of water. And so what their body does is they actually almost dry out a little bit. So, they can use the bathroom if they need to, but a lot of them say that when they get out of the suit, instead of using that, they're actually drinking a lot of water because they're really thirsty.
Why do people just go to the moon? Do they do it for fun or for money or for both?
Why do they? I missed the first part. Why do they what?
Why do they go to the moon?
Why would we go to the moon?
Yes.
Oh man, so I'll just tell you my answer. So my answer is twofold. One is because I think by nature, we're an exploratory species. I think it's really cool to explore and understand more about the world and the universe around us. I also think that we're very, very, very lucky to be on planet Earth. We have a lot of resources here. It's a beautiful world. And unfortunately, if we stay here long term, I think we're probably going to use up all those resources, and it's not going to be as beautiful as it could be. So being able to explore allows us to be able to hopefully one day repair the Earth and not put as much demand on it as we are right now.
Do you have to train before you go to space?
Do you have to train? Absolutely. Astronauts do years and years and years of training. In fact, when you become an astronaut, you're not a full astronaut yet. You're what's called an ASCAN, astronaut candidate. It takes 2 years of training before they let you become a full astronaut. So even when you get selected, you still have to work really hard. But it's important because space is a hard place to work, so we want them trained.
It's like a weird question, but you know, like since there's like global warming and like most of our Earth is more coming water, if the world were to end, will everybody go to space?
If we were to have a catch-up thing, I mean, we would have to go to space pretty fast if the world would end. I don't think we have the ability to all go right away, but hopefully one day we can protect the Earth as well, and maybe it won't end, so we'll see.
So I just had a question about some of those analytics that you're doing are very kind of probabilistic or statistical in nature. How do you balance that, or how do you square that with the need for like really deterministic safety critical systems for the astronauts?
Yeah, I mean, absolutely, right? Like if you leverage machine learning, you can go learning in the completely wrong direction, and then you need historical data. So even if you are somewhere and you have what you think is a good model, if it's all relied on the wrong model, you're just gonna keep getting bad numbers. So I think it's a balance of both, right? I think we're gonna have to have good statistical backgrounds, but I think we're also going to have to be able to have the astronauts sample real time to add to that machine learning, right? So it's not just passive machine learning that I think that's going to help, but I think active machine learning. We see a lot of that with human-machine teaming, where we might ask them out in an EVA, hey, every time that you feel exhausted or tired, you know, input an additional thing on your suit so that that's a better machine learning in the long run. So I think there's going to be a lot of different models we're going to have to look at.
As a follow-up, is any of that data like publicly available, or is it like, I guess because it's bioinformatics, is it private and personal to the astronauts?
Yeah, so I don't know of any of the data that's like publicly available. It is private. Even when we were sitting on console, there was data that we could see that even the flight surgeon couldn't see, and then there was some data the flight surgeon could see that we couldn't see when astronauts were working out and stuff. So we probably need to move beyond that, at least within mission control, and be a more communicative domain. For learning, though, I think that some of that stuff that I talked about, like the exercise algorithms, you know, we can learn from a lot of different domains. So there's nothing to say that we use an algorithm that, or kind of weights or whatever you want to say, that come from a totally different domain, but still applies to space, right? So I think there's a lot of data sets out there we could use to really help space out.
So, like, when the astronauts go to space, like, do you have little cameras on them so you can know how things look? Or do you ask them to draw something or take pictures to see?
Yeah, it's great. So, yeah, absolutely. So right now they have cameras that are actually on their visor. So that's very, you know, it's passive collection. And you can, if you watch the spacewalk, you can see them like walking along the space station with their hands. We also allow them to actually take digital cameras, and they can take pictures, and sometimes both inside and outside the station. So we'll ask them to take pictures of things, especially if they're broken or look funny, and then they send them down to us. And I think that's going to continue the moon and Mars. We're going to ask for pictures all the time. So,
oh my goodness.
Follow up, how do they carry those digital cameras when they're out on the spacewalk?
Yeah, they're tethered. So they're covered with like a thermal protection as well, but then they're tethered to them, or sometimes they have bags that they can put them in and then pull them out to protect them. Yeah. Yeah.
Hi, thank you for your presentation. Why is it important to learn how to work on a team if you want to have a career like yours?
Oh, absolutely. Well, teamwork is important because the job by nature is more than one person, right? So there's no way you could be everywhere all the time. Specifically for console, right? You can't work 24 hours a day, every day of the week. So being part of a team means you have to learn how to hand over the job to someone else, and then in turn, they learn how to hand the job over to you so we can continue working. So it's really important.
You mentioned you had a background in astronaut training.
Yeah.
How do you get access to such a cool position? That sounds really interesting.
Yeah, so that's a good question. So how did I actually get that job in the first place? So I had to have the people, I can talk to that group specifically. So to get hired in the EVA group, you have to have a solid background in either engineering or science. Most people are engineering. There are a few physicists within the group. And then it was interesting for me because when I was looking for a job before I got in that specific job, I thought I was going to go in a different area of NASA. And somebody passed my resume to Trisha Mack, who was the group lead at the time in EVA. And I get this call, and she goes, "So I see here that in hobbies, you scuba dive." And I was like, "Yes? Like, does that?" I was scuba diving for fun. I'd grown up in Florida. I loved the ocean. So it was something that I had in my little hobbies section of my resume. They tell you, "Oh, put down a few couple hobbies." And she said, "Yeah, I'd like to come talk to you about being an astronaut trainer." I'm like, "For scuba diving?" Like, I was so confused. And she goes, "No, actually," she talked about the neutral buoyancy laboratory, and she said, "We get people that apply every day, but you'd be surprised how few of them scuba dive. So once we see someone who's a scuba diver and has the technical minimum requirements, we reach out to them." So I would encourage all of you guys that if there's something you're passionate about, if there's something you're interested in, put it down on your resume for sure for your hobbies, but stay passionate about it. Don't assume just because it doesn't align perfectly with your career, it's not going to come into play. Like I'm not sure I would have gotten that job or even that call, right, if I hadn't just been a diver. So.
How do you the astronaut suit that they wear? How do they go scuba diving if it's really heavy?
Oh, it's a great question. Yeah. So the suits that we wear in the neutral buoyancy laboratory, and I'll go back to that slide because I love that pool. That pool is amazing. It's an amazing, amazing thing. And this is actually an older picture when we still had a shuttle cargo bay here, but now the whole thing is filled up with the space station. It's really neat. So the suits are still pretty heavy, which is why we have these cranes here that actually lift the astronauts into the water. We don't have the full PLIS background. We just have what's called umbilicals, which are like hoses that go out to the surface. You can see them right here. So they're only wearing a partial suit. They're wearing a suit that actually is the pressurized garment, so they actually can work in that environment and get the endurance to work in that environment, but it's still pretty heavy. So when they go into the water, because we have a lot of air, we actually use a sense of the weight and then all these little foam pieces that they put all over, and they make them neutrally buoyant as much as possible in the suit. So it's still a pretty heavy suit, though.
Is the weight evenly distributed so like your arm actually feels heavier? Or is it just like a weight belt that holds you neutrally?
Like a harness? Yeah, so that is one thing that's interesting is even though what you're working in the pool, you're still 1G within the suit, right? So you still are kind of like weighted. So we try to do foam pads and so forth inside the suit so you're kind of centrally located. But in space, right, we can go inverted and work upside down and it doesn't make any difference. And in the pool, that is not the case. So we can only turn them upside down for so much time, and then we have to revert them back over. So there's a few things that are more difficult and a little challenging, and they actually say that on orbit, the EVAs get pretty fun because they are truly floating and they're working all over the place. So.
How deep is the pool?
How big is the pool? The pool. Oh, how deep? It's 40 feet. So they dug out 20 feet underneath the ground, and there's 20 feet above. It's 103 feet wide and 303 feet long. And if you want to dive in this pool, you actually have to take a swim test where you start to do so many laps, but then you also do a test where you start in the middle, and you have to swim underwater in one breath all the way to the end. And that's for an emergency in case you were actually at the bottom and you had to come up. So if you're not a good swimmer and this is something you're interested in, you should definitely work on your swimming.
I can go? Oh.
I think we'll take, maybe this will be the last one, then you would take one more either online or not. Do we have anybody online or no? We'll check. Okay, no worries. All right, that's fine. Then we'll take the last one in the room. Go ahead.
If an astronaut get lost in space, what happens? Talk in the microphone. If they get lost in space, not face.
So sometimes at night, the astronauts do get a little bit lost. They get disorientated. The space station is really large, and at night it's very, very dark. And so we have lots of different labeling to help them go the right direction. But when they're up there in the dark, they can actually only see what's lit they can see the Earth below, but they can only see what's lit within their working area. So
do they stay constantly tethered as well?
they are always tethered. Well, we tell them to always be tethered, like, right? So as far as I know as an instructor, they're always tethered. Right.
All right, thank you.
Yeah, thank you.
Thank you. Adele, thank you so much. What a great way to end the day, because she gave you so many opportunities to think about the hackathon tomorrow and the challenges that lie ahead. So we really appreciate, what an amazing panel discussion today, the improv, the moon mission, all the people that contributed. So we're going to close out today's Space Apps, the Space Apps Challenge, with one caveat to think about. 50 years ago, we did put 2 people on the moon, okay? Over 400,000 engineers and technicians worked on the Gemini and the Apollo project. When you talk about teamwork, when you talk about intellect, when you talk about hard work, and those weren't ass cans, those were full-fledged astronauts that committed so much of their lives to fulfilling almost the impossible mission. And we only had one chance to get it right. One chance, and we did it. So I want to inspire everyone who was part of the International NASA Space Apps Challenge all over the world to think about how you and your teammates are going to get that one chance to get it right and do great things in the future. Thank you so much. We'll see you tomorrow.